And the plan is that we'll make all of these talks available to the public after the conclusion of the meeting, unless you don't want it to be recorded. But otherwise, we'll plan on sharing those slides.
We should bring your own links.
Yeah, or I'm happy to use mine if you want to just share these slides with me.
Well, literally using your thumbs.
Yeah. Well, that's not mine. It's his.
Andrew's his problem.
Yeah.
Andrew, need to know whose fault it is. It's me, Andrew. What is the link to this?
Yeah, it's written up here on the paper, so when you come up, you'll just log in to give your talk.
If you don't go rough. It's too hot for the blast. Yeah.
Ah, here you go. You're getting it.
What's for me?
What's your file? Reminder.
Okay, you got it.
Hey.
Thank you.
Thank you. So Joseph, I'll give you a warning of 10 minutes. I'll give everybody a warning when it's 10 minutes. So it's a 40 minutes talk, but including questions. So we'll try to keep the discussion.
May I go forward? Use the arrows.
This way, okay.
Yeah, it works.
Okay. Fine. And thank you again for this opportunity to share with you these reflections. This is the first talk of the conference, so it is a bit more general in character. I will not speak on quantum mechanics. I'll speak on general dialogue on science and theology, present and future academic dialogue. The organizers wish to help participants get to know one another and lay the groundwork for future collaborations, possibly including forward-looking program. For this reason, I was asked to open the sessions entitled The Interface Between Quantum Science, Philosophy, and Catholic Theology, with a general talk aimed at examining the present situation and supporting ongoing work. Accordingly, I will not focus specifically on quantum mechanics, though I will naturally refer also to it. Instead, I will address the present and future of academic dialogue on science and theology, highlighting some key questions for developing ongoing research and expanding the agenda, as indicated by the subtitle. Among the participants in this conference are scholars and colleagues who already have extensive experience in academic work on science and theology. I ask you then to consider my reflections as a personal proposal, not as a normative summary. The backgrounds in the academic context in which we operate are very different. Europe is not the United States, as you know. As we know, in European countries with a Latin tradition, such as Spain or Italy, the academic dimension of interdisciplinary studies is still underdeveloped compared to the many Anglo-Saxon countries, particularly in the United States of America. In Europe, we don't have chairs of science and theology, but in Anglo-Saxon countries here, in the United States, we have Berkeley, Chicago, and so on, but also in UK, Oxford, Cambridge, not in Spain, not in France, not in Italy. So situations are a bit different each other. Bearing this in mind, and given the time constraints I have, I will structure my talk into 6 brief points. For more details and bibliography, I please ask you to refer to the future written text of my presentation. Let's go to first step on the role of philosophy in the science and theology dialogue. This role is quite strategic, and unfortunately, in my opinion, it is underestimated. Contemporary dialogue between science and theology seems to underestimate the traditional mediating role of academic philosophy. As a result, many scientists adopt their implicit philosophies, shaped more by their own cultural view than by strong philosophical traditions. Rigorous reflection on concepts such as being, truth, causality, or God are then undermined or even compromised. In my opinion, this is a source of misunderstandings and confusion in many science and theology debates that need clear philosophical concepts on God and the nature. I feel that the future of science and theology dialogue will greatly depend on the role that philosophy should play, mediating between empirical inquiry and theological reflection. Philosophy remains the privileged context where scientific and theological knowledge can be critically interpreted and explained. Thus, a serious engagement with major metaphysical traditions and their conceptual tools is welcomed. Classical philosophical sources deserve a renewed attention. Aristotle still offers a valuable conceptual resource through his doctrine on causality, potency and act, matter and form, and his philosophy of being. Recent interest in Aristotelian metaphysics has even led some scholars to speak of Aristotle revenge. As known, Thomas Aquinas reframed Aristotelian thought by interpreting nature within the framework of creation. Thomas Aquinas is not the same as Aristotle. Aristotle doesn't have the idea of creation. Thomas Aquinas, yes, he has. His metaphysics, Thomas' metaphysics, continues to provide important tools, in my opinion, for discussing the philosophical presupposition of science, divine causality, and the relationships between different disciplines. See, for instance, the work of Mariusz Tabacek. In Aquinas' view, scientific inquiry can be interpreted today as part of humanity's natural desire for knowing truth and ultimately for knowing God. Thomas Aquinas spoke of our natural desire of knowing God. Science, scientific knowledge, participates of our natural desire of knowing truth. At the same time, classical metaphysics must confront the challenges posed by contemporary science, including emergence, complexity, non-locality, systemic causality. All this kind of causality didn't exist at the time of Thomas Aquinas. Aquinas cannot simply be repeated naively. His concepts require profound interpretation in the light of modern scientific frameworks. Finally, the dialogue between science and theology would benefit from broader philosophical cross-fertilization. The thought of authors such as Teilhard de Chardin, Michael Polanyi, Charles Sanders Peirce, Maurice Blondel, Henri Bergson, Antonio Rosmini, or Pavel Florensky remains, unfortunately, scarcely used in science and theology dialogue. A fresh contact with these and other thinkers can stimulate innovative approaches to a theology of nature and the richer integration of scientific and metaphysical thought. Second chapter of my presentation is entitled Upgrading the Dialogue from the Epistemological to the Anthropological Level. My personal feeling is that we continue to dialogue at the epistemological level. What does it mean, this concept? How you use this concept? How I use this other context? Are we able to understand each other? Okay, this is necessary. But there is also another level of dialogue, which is the anthropological level. Most studies on the dialogue between science and theology focus on epistemology, methods, reasoning, compatibility or conflict between scientific, philosophical, theological claims. This emphasis has often marginalized the anthropological dimension of the knowing subject. Yet the key question is not only how do we know, but also what are the ends and the aims of scientific knowledge. This is the anthropological level. Thinkers such as Michael Polanyi, Thomas Torrance, Antonio Damasio showed that personal beliefs, tacit commitments, and existential context shape scientific inquiry. Science involves freedom, purpose, and the search for meaning. Scientists and theologians are engaged in a common search for truth as human beings. As Maurice Blondel wrote in The Action, 1893, science transcends itself. It's very similar to that other motto by Blaise Pascal. Man transcends infinitely man. But also science transcends itself. Research depends on ends and motivations that science alone cannot provide. Scientific inquiry opens toward philosophical and theological questions that cannot be considered mere private opinions. Wonder and reverence before nature, the quest for ultimate ground of physical reality, the ethical responsibility of scientists. All these are not private opinions. Art and spirituality also play a role in inspiring scientists' work. Scientific activity is not only in search for logos, but also a commitment to ethos and an experience of pathos. Scientific research is this. Theology is asked to increase the anthropological perspective when debated with the sciences. Also, theology can give the error to be confined to the epistemological level. Also, theology is required to upgrade to anthropological level. We need a theology of the logos understood not only as ratio, but also as verbum, personal word, according to the two meanings of the word logos, as ratio and verbum, word. Nature is the effect of a personal divine word, appealing to us through the intelligibility and beauty of the cosmos. This means to take seriously God's revelation through nature, an issue, unfortunately, largely neglected in 20th century theology. Nature is not merely an object of study, but also a witness to creation, capable of generating contemplation, awe, beauty, and prayer. A particularly innovative proposal is the program of scientific humanism, especially as developed by Enrico Cantore, an Anglo-Italian philosopher. Scientific humanism interprets science as a profoundly human activity, involving creativity, imagination, purposes, and even religious inspiration. Science is not as a neutral device, but a source of human dignity and social solidarity. According to this perspective, philosophy of science should be replaced by a philosophy of scientific activity, because the word activity put in lies the personal subject. Good insights may come from the philosophy of action as developed by Maurice Blondel, Edmund Husserl, and also Karol Wojtyła, who has a very nice essay on philosophy of action. In this case, scientific action, scientific activity. In the light of a scientific sapiential humanism, scientist's personality is not far from the profile of the wise man at work in the wisdom books of Bible. Finally, when upgrading from the epistemological to the anthropological level, science and theology are no longer seen as competitors or disciplines in conflict, but rather as allies in promoting authentic human development. chapter 3, I suggest also to encourage historical studies. Historical studies help to overcome misconceptions and oversimplifications on the interaction between Christian theology and scientific revolution. Good work was done by many authors, Rodney Stark, Stanley Jackie, and many other people. Also, increase the number of studies on the characters and personalities of scientists. Good works were made on great scientists such as Kepler, Newton, but we have many scientists with a very huge personal history, which influenced very much his way to do science. And we didn't go in depth in these authors. We need to do this. Increase the number of studies on the characters and personality of scientists to show whether and how their religious belief, if any, influenced their view of nature and consequently their way to do science. There are nice studies also on Maxwell's way to do science. Thomas Torrance studied Maxwell's activity, and Torrance concluded that the idea of incarnation, that God became man, is very present in the idea of Maxwell that electromagnetic waves can be incarnated in equations. Okay. And encourage historical studies, investigated the role of imagination, metaphors, creativity, personal worldview in the work of scientists. We have a nice work made by Tom McLeish. Unfortunately, he passed away 2 or 3 years ago in Cambridge. Explore the way in which Hinduism, Buddhism, and Christianity offered philosophical categories to quantum mechanics. For instance, this is a question of mine. I ask myself, why Eastern philosophies are so present in quantum mechanics philosophical reflection and not Christianity? Why? What happened? We have many philosophical perspectives in Christianity that can nourish quantum mechanics. Trinitarian God is relation. Okay. Fourth chapter, practicability of a theology of nature and of a theology of science. This is, in my opinion, one of the most beautiful, most important new horizon of science and theology dialogue. In the coming decades, serious efforts should be made to determine whether a theology of nature and a theology of science can be established as new theological disciplines, having a clear epistemological status and solid theoretical and also biblical foundations. Although some authors use them as synonyms, theology of nature and theology of science are not the same. Theology of science emerged first, beginning to develop in the 80s of the past century, having an impact in the local Polish philosophical milieu, thanks to the works of Michael Heller and Joseph Dzieciński. Theology of nature received important contributions by authors such as Jan Barbour, Michael Heller, Alexander Ganozzi, Alistair McGrath, John Ott, Bob Russell, Dennis Edwards. However, more systematic proposals are still needed. Once implemented, these disciplines shall be truly theological in character, in terms of sources and methods. Let me just mention, as an overview, a number of topics within a theology of nature that could lead to fruitful dialogue with the natural sciences. God's revelation through through nature. I have here a number of suggestions. No? God's revelation through nature. Theology has traditionally focused on God's revelation in salvation history, paying less attention to manifestation the divine logos in the natural world. It is important to remember that the one and the same nature, object of the natural sciences, is also the one and same nature, place where God reveals himself. God's revelation in nature belongs to fundamental theology and must be distinguished from natural theology. Natural theology is a kind of bottom-up movement. Revelation of God through creation is a top-down line, top-down movement. A theology of nature may also regain the metaphor of nature as book, long shared by theologians and scientists, and still rich in meanings and implications for a dialogue between science and theology. In relation to God's presence and manifestation in nature, the panentheistic concept of God has recently gained importance and popularity among many authors. Authors sympathetic to this perspective suggest that this way of relating a God with nature is more in tune with the current scientific worldview and more apt to frame the problem of understanding divine action in nature. This is an interesting example of how the dialogue between theology and science can stimulate new reflections on the Christian concepts of God. Another issue, very strategic for a theology of nature, is creation, information, and finality, the relationship between these three concepts. In relation to God's revelation in nature, and as part of a theology of the Logos, a theological reflection on the presence of information in nature should be a priority for a theologian's agenda and dialogue with the sciences. In a cosmos created in the word Logos, as stated by the Judeo-Christian revelation, information can be seen as an original component of the world and the source of meaning for the evolution of cosmos and life. A world created in the Logos possesses a positive amount of information. Along with matter and energy, information seems to be a necessary component of the natural world. Thanks to the primordial role of information, all natural entities are something given. They have a quidditas in Latin, a specificity, specific formal properties. The attention the natural sciences give today to the notion of information is promising to address a meaningful dialogue between science, philosophy, and theology. Gregersen, Paul Davies, and so forth. Indeed, the search for the origin of information opens to the idea of a personal intentionality. The philosophical meaning of information opens to the idea of a formal causality. Both of them provide a fruitful context for discussing the presence of finality in nature. This could also be the place for a new, more philosophical, rigorous approach to the anthropical principle. Another issue for theology of science is theology of nature, pardon, is the natural world between promise and fulfillment. In the first half of the 20th century, biblical theology interpreted the creation as part of the covenant between God and humanity. While such a view has the advantage of promoting a unified understanding of the divine plan of salvation, it runs the risk of diminishing the ontological consistency of the created world. Often, the books of dogmatic theology ends by absorbing creation within covenant. Everything is covenant. So creation, in my opinion, runs the risk to be deprived of this strongness. Indeed, the Hebrew term for covenant, berit, also admits the meaning of oath, commitment, promise. And the history of creation is the unfolding of a dynamic from promise to fulfillment. So if we replace covenant by promise, we can understand creation, history, as a promise which goes to a fulfillment. The Christological dimension of the physical cosmos. Among the Christological dimensions of the created world that have some implication for the natural sciences, I mentioned the following. Created by an intentional and personal world, and in the sight of the Word made flesh, the whole cosmos is indeed one. That is a universe. Because of the unity of its cause, the laws of the universe must show a clear universality, and physical properties of material entities must show a strong identity. Being the Logos an embodied word, lex incarnationis, we expect the primacy of a cognitive realism and induction over idealistic perspective. And this could turn out quite useful in quantum mechanics. Do not forget the realistic approach if you want to develop a theology of nature in a Christological perspective. Nature, if it is created in the Word made flesh, nature should have a clear dialogical dimension because the Word made flesh. Information is expected to be an original component of a cosmos created in the Word Logos. Understood in the light of the Word made flesh, the entire cosmic history and the evolution of life should express a unified single design, no matter how long it lasts. Part of this design is overcome fragility, pain, death, whose meaning is definitively unfolded by the mystery of Christ's death and resurrection. To think in terms of a physical history of salvation. The notion of history of salvation is very crucial in theology. But we need also, in my opinion, a physical history of salvation. It is a history that includes not only the history of human beings upon our planet, but the history of the whole universe. A pivotal task for a theology of nature is to begin to think in terms of what we might call a physical history of salvation. Unlike the biblical history of salvation, a physical history of salvation should study, understand, and explain the history of salvation in the context of our physical universe, its space-time scales, its ongoing transformations and future scenarios. The biblical history of salvation, which focused on liberation from a moral evil, sin, and slavery, safeguarding a people, the Hebrew people, so that it can freely profess their worship on the one and true God, asks to be read and understood within a cosmic context. It must also include, on some level, liberation, not only from sin, but from physical evil, from ignorance, from finiteness, from weakness, from lowliness, from final corruption and death of the whole universe. A physical history of salvation should reveal the role of the human being in the whole cosmos. It should restore the image of a universe no longer seen as impersonal, subject to corruption, or even tragic. A physical history of salvation, finally, should reveal how the Paschal mystery of the risen Christ can be read within a cosmic global breath. The history of salvation, which is the history of God's and human freedom, is a clear priority over any evolutionary history of life and cosmos, which proceeds without the contribution of free human will. However, the former intersects with the latter. Supernatural salvation takes place in the context of a physical and biological history. The realism of the Christian incarnation, according to which the Son, when taking up human nature, also took upon himself all the relations that nature has with the created world, suggests that this intersection, with all its consequences, should be taken seriously. Theology and quantum mechanics, new philosophical paradigms, and the need for a renewed metaphysical stance. In this presentation, I am unable to provide a status questionis of the complex relationship between quantum mechanics, philosophy, and theology. There are excellent review papers on this subject. Among them, I recommend the entry Quantum Mechanics, Philosophical and Theological Implication, written by Javier Sanchez Cañizares for the Interdisciplinary Encyclopedia of Religion and Science. I will highlight just a few ideas, hoping they turn out useful. Interdisciplinary work at the intersection of theology, philosophy, and quantum mechanics put in light two problems. The first one is the need for dual expertise. In this field of physics, we need both expertise. While in other terrain of physics, we can have a more or less a general idea of how nature functions. In quantum mechanics, we cannot have a general idea. To do a rigorous interdisciplinary work, we need a double expertise. This is the first problem to solve. And the second is the current lack of a common language that scholars in these fields can use unambiguously the same language. Unlike other branches of the natural sciences, a mere popular understanding of quantum mechanics is not sufficient for serious interdisciplinary work. Philosophers and theologians interested in this time of work must undergo more in-depth training in quantum mechanics, as a dual expertise is here crucial. Currently, we lack a meta-language capable of unambiguously incorporating philosophical theological categories such as ontology, causality, transcendence, and typical quantum mechanics categories, such as indeterminism, superposition of states, non-locality. Perhaps recent efforts of a formal ontology to establish a common language between mathematics, logic, and philosophy of being, because formal ontology was an attempt to have this general language, could be revisited and developed in the context of quantum mechanics. I don't know. It's just a proposal. Perhaps we could have a formal ontology for quantum mechanics. No, we have the formality of language is very high. Two areas remain strategic for interdisciplinary studies in quantum mechanics. First, the quantum mechanics compels us to expand our understanding of causality that needs now to include the top-down, bottom-up, and the whole two-parts causality. Second, quantum mechanics prompts us to explore parallels between psychic and quantum phenomena, including the search for a possible synthesis. This is not naive. We are obliged to reflect in terms of the psychical world and quantum mechanics world, because the subject, the observer, is highly involved. In terms of relationship with the theology, I think it is crucial to convey a coherent image of God based on solid biblical ground and a realist metaphysics. This will allow us to more accurately evaluate what quantum mechanics can truly say about the problem of divine action in nature and the truthfulness of human freedom. Personally, I believe that quantum theories should not discourage the search for an ultimate ontological ground beyond the relationship and phenomena. Moreover, quantum mechanics do not prevent us from thinking that there exist steady formal causalities on which the lawful behavior of physical entities depends. I'm also convinced that as mechanistic reductionism compromised the science and theology dialogue in the 19th century, mechanistic reductionism, so a quantum reductionism is still possible and could obstacle a serious interdisciplinary work in the 21st century. Both reductionisms, mechanistic reduction and quantum mechanical reductionism, operate at the ontological and the gnoseological levels. While mechanistic reductionism reduced knowledge to computability, quantum reductionism could constrain knowledge into abstract and idealistic categories. I go to the end of my presentation because time is over. I skip suggestion about a dialogue on ethics, and I move to conclusions. The formation of scholars trained in both the natural and human sciences, including theology, is essential for fostering fruitful dialogue between Christian theology and contemporary science. Such dialogue should include epistemological and anthropological dimensions and remain open to an integrated, personalistic, non-reductionistic understanding of scientific activity. A fruitful encounter with the sciences can offer theology two major benefits, many benefits, but at least two major benefits. First, contemporary knowledge of the cosmos, nature, and life can inspire a genuine theology of nature. Just as theology engaged with the knowledge of the time in medieval universities, a deeper dialogue with the natural sciences today can enrich our understanding of revelation and foster evangelization in a culture shaped by scientific reason. Second, dialogue with science may contribute to a gradual and homogeneous development of the Church's doctrinal teaching. Dogma develops, remaining itself, but develops in language and in understanding and in deepness. This would not change the content of faith, but deepen the understanding of divine revelation. Such development is a task for theology under the prudent guidance of the Church's magisterium. In both cases, the aim moves from simple dialogue to integration. We think to Jan Barber's categories. We could move from dialogue to integration in Jan Barber's sense. Natural sciences can become a valuable research for theology. There is a special issue of the Journal of Religions entitled Natural Science as a Theological Locus, a place for reflection of theology. Natural sciences can become a valuable resource for theology. Once contaminated by scientific result, theology should improve catechesis, pastoral activity, and the Church's wider apostolate. The dialogue between science and theology is reciprocal, though asymmetrical. Science offers to theology an objective knowledge of the natural world, objective knowledge, while theology offers scientists, not science. Theology offers scientists a broader vision of reality and human existence. In this sense, it is asymmetric, because science offers data to theology. Theology does not offer data to science, but philosophical perspective to the subject making science. Theology provides no measurable data to scientific method, but it can enrich the intellectual horizon in which scientists carry out their research. Science enables theology to understand more deeply what it means to be a creature within a created world. At the same time, the theological vision of creation supports the intelligibility and meaningfulness of nature, the human capacity for truth and freedom, and the responsible stewardship of creation through scientific and technological progress. Both paths remain crucial for the future. Theologians are challenged to integrate scientific discoveries into their reflection, while scientists may rediscover the relevance of philosophical and theological wisdom for the deep questions raised by their research. I thank you very much for your attention.
So we have time for a question. Yes.
You elaborate briefly on what you meant by quantum reductionism and the dangers you see of that?
Yes, I cannot develop in depth, but the idea is that we are tempted to reduce reality to knowledge. So it is an idealistic temptation. We cannot lose realism. The role of the knowing subject is so relevant in quantum mechanics that we first think to mental categories of the subject. And all reality is interpreted in terms of personal knowing categories. If this is put at the extreme level, it may end in a reductionism. This is a form of idealism.
Thank you.
So you link together the contemporary scientific idea of information and the classical idea of formal causality. And I definitely see connections there. Could you just say more about the connections you see and how you see information as allowing a renewed appreciation of formal causality?
My feeling is that the contemporary attention to information is a contemporary way to realize that there is a formal causality in nature. If you speak to a scientist of a final causality, he says, I don't need final causalities, no? But if you speak to a scientist of a formal causality, to explain that formal causality means that things are something. They are and behave and operate according to a specific nature. This is nothing more, nothing less than a formal causality. And they call this information. Okay? And information is not something external to the entity. This is in the entity, but is an original component as matter and energy. In classical Aristotelian composition, matter and form is not external to matter. They are so tight that the very entity consists both in matter and form, but they can distinguish them. And there is a priority of form over matter, because forma dat esse. Things are because of the form.
Thank you.
And this is, in my opinion, intelligible by scientists.
Just one question. Yes, one more question.
So excellent talk. But I give talks to a lot of high school, college students. And the approach I take with them is that, and I think the problem we have in today's world with AI and all that, is people think that our thoughts come from the material world. People think that life comes from the material world. And I
From the
think,
material world.
yeah, in other words, from, atoms, electrons spinning around protons and neutrons. And I think, and I think when I tell them that, they actually get it because that restores human dignity. Because again, we're still fighting this mechanistic, where, computers can replace us because they're just like us. Well, they're not. They don't have intelligence. It's a misnomer. They don't have, it's not part of the material world. And so I think when people understand that, then God created both the material and the immaterial world. And I think that's really what the problem in our society is right now, is
I
that
agree with
we
you.
have to have both.
I agree with you. I agree. It also depends on the image of God people have.
Right. Yeah.
Very frequently, people have a incorrect image of God.
Yeah.
Very good. I think we need to close because
I will stay here 3 days.
We will. I think we would love to have double of the time of this conference. I think with all the conversation, but let's thank.
Jensen?
Yes.
It might help if people ask questions, they say who they are, so we can learn each other's identity.
Thank you so much, Steve. That's a great. Did you hear the good suggestion? When we ask question, we can say who we are, so we start to get acquainted with each, because that's the whole purpose. Thank you, Steve.
This autumn is. And then this one.
I'm logic.
You're making that say, unsure of your slides. Can you?
Who manage?
So I joined the meeting.
Yes, go ahead.
See, that's why.
Your slides. Yeah.
That's what.
There is now I'm not very used to it. Now I open my wait. So I have
All right, so let me just introduce our next speaker, Professor Fernando Sols Lucina. Yes, I pronounced correctly.
yeah. Yes, exactly.
Yes. So he is a professor of physics at Complutense University of Madrid. So he had his bachelor at the University of Barcelona and the PhD at the Autonomous University of Madrid. And he has been working across. Just mute. So he's been working at for 5 years at Oak Ridge National Laboratory. We work with Anthony Leggett, as you know, Physics Nobel Prize in 2003, and Carles. And now he became first associate professor in Madrid. Now you're a full professor there. And he has been working across different areas: physics, theoretical condensed matter physics, ultra-cold atoms, and has a lot of interest in quantum foundation and also in the interface between science and faith. And he's the father of 5 children, and grandfather of 10, and also a passionate music lover. So this is a good witness of science and family life.
Yes, but the secretary asked us to say something
Yes,
interesting about
that's about what Steve.
Maybe interesting.
So we got to know each other more.
Anyway.
So Poincaré, Heisenberg, Gödel, Bell, discovering science fundamental limits. Scene is yours.
Okay, so thank you very much, the organizers, in particular Andrew and Vincenzo for inviting me to participate in this very interesting workshop. I think it's very nice to talk about all these subjects. The topic will be even in the title. And then, okay, so our heroes of today, the first three ones are Poincaré, who essentially founded nonlinear dynamics, chaos theory. Bernard Heisenberg, who is considered one of the main, or not the main founder of modern quantum mechanics. In particular, he formulated the well-known uncertainty principle. Gödel, who discovered incompleteness theorems. And then we will talk also about John Bell, who discovered classical inequalities and its violation by quantum mechanics. So, okay, so with the success of Newtonian physics, the worldview that prevailed for at least a couple of centuries or more is that of a deterministic universe in which, can you see the mouse? Okay, let me help. Okay, okay, so the picture that emerges is that of a deterministic universe in which the future of a system characterized by for instance, the positions and the momenta or the velocities are determined by the initial conditions, which are written here, okay? And this was very successful in understanding, for instance, the celestial mechanics of planets and so on. Then towards the end of the 19th century, Henri Poincaré questioned this picture. He realized that the planetary systems, which have been described so successfully by Newtonian mechanics, was just a two-body problem, and it was more an exception than the rule. He realized that most dynamical systems are chaotic, which means that their long-term evolution is very sensitive to initial conditions, or in a phase space, that the trajectories are very strongly intertwined. So that means in particular that the greater the precision with which we wish to know the future, or the farther the future we wish to predict, then the greater the accuracy with which we need to know the initial conditions. Okay, so the prediction of the future requires knowledge of the present with infinite accuracy. It gets to a point in which we need an uncertainty both in the momenta and in the position, which has to tend to zero. But with the discovery of quantum mechanics, in particular with the formulation of the Heisenberg uncertainty principle, what was realized is that position and momentum cannot be arbitrarily well defined simultaneously. And in particular, there will be this well-known uncertainty relation. Okay, so the product has to be greater than this fundamental constant of nature, which is h bar is h over 4 pi, or 2 pi, so that's h over 2 pi. Now, so that means that the precise prediction of the future is forbidden by quantum mechanics. And in particular, as we will comment in more detail later, that the possible existence of local hidden variables that would rescue the deterministic picture have been rejected by experiments, at least in an extremely broad class of situations. Actually, the Nobel Prize in 2022 was given to these people, Aspect, Clauser, and Scheilinger, for observing experimentally the entanglement of photons, and in particular the violation of the classical inequalities that were formulated by John Bell, who died too young. I will talk more about this at the end of the lecture. Okay, so with Poincaré, we have practical indeterminacy. If we put it together with Heisenberg, now it means intrinsic indeterminacy. That means the future is not determined, which means there is room, although it does not prove, but there is room for the existence of free will, so we are allowed to think that our free will is real, okay, because the future is not completely determined. We can call it also human design if we use it in a constructive way. Providence, there will be also room for providence, understood as the intervention of God without spectacular miracles, just in ordinary life. Quantum measurement, the concept of quantum measurement involves the idea of wave function, or the wave packet collapse, or wave function collapse. Let's assume that we have a system which has, which is in a coherent superposition of three eigenstates of an observable with different values. X, Y, Z represent different states of the system, which have different values of some interesting physical quantity. And A is the macroscopic apparatus. We couple it to them, and this is the most standard textbook picture of projective measurement. So after a while, due to interaction, this apparatus it evolves in different ways depending on the state of the systems. And since in principle the linear superposition principle applies, then that's what we have. Now let's say the capital X, Y, and Z are macroscopically distinct states. So in practice, only one of what happens in practice that we only see one of those possibilities. We never see a macroscopic thing in a coherent superposition of several possibilities. And that is what phenomenologically is called the collapse that was introduced from von Neumann. So quantum mechanics only predicts, and very well, by the way, the statistics of results in identically prepared experiments, but cannot predict the result of an individual experiment. That's very important because in real life, many things are run only once. For instance, we can produce phosphor once, not twice, okay? But anyway, so the collapse or reduction of the wave function is essential to convert what uncertainty about the present, which may evolve deterministically with Schrödinger equation, if we combine it with the wave function collapse, when that uncertainty is coupled to macroscopic operators that evolve into macroscopically different configurations, then that turns out evolves into unpredictability of the future, okay? Well, another way of viewing at this is to invoke the famous Schrödinger's cat paradox, in which here the two states would be that of the state, the atom decay in an excited state or the atom having decay, and then the cat would be the ultimate thing that would be coupled to it because it would be killed in one of the two states. So there would be this type of entanglement. So this would be a particular case of quantum measurement, and Schrödinger put this paradox to say that in practice we would never observe. What happens is that, as you know, Schrödinger mechanics has to be complemented with the postulate of the collapse of the wave function in order to make sense of what we observe. Now, in principle, quantum mechanical behavior is everywhere. Usually it is killed by the coherence, which happens faster in massive systems. But if a variable is sufficiently isolated and if wait for long enough, it can exhibit quantum mechanical properties. So here we have a satellite of Saturn, Hyperion, which is oblong. It's pretty big. It's like a 1/3 of California or something like that. And so it's reasonably macroscopic, but has very little dissipation. And in case the rotation is chaotic, the translation around Saturn is pretty regular, but because it's so long, due to the gradients of the gravitational forces, is chaotic. And that means that, the different in classical phase space, the trajectories diverge very, very fast, exponentially fast. And then you can predict what it will do in a few hours or a few days. But if you want to predict what it will do after some years, you face practical difficulties. But then the theory tells us that if you try to predict for things for over 20 years or longer, then you are fundamentally limited by quantum mechanics. And this estimate was made by Zurich. So some younger people here, 50 years from now, will be alive, and Hyperion will be doing something, and nobody will call it a miracle, right? But the fact is that what Hyperion will be doing in 50 years from now is nowhere. That information is nowhere. It's an information that will emerge. Okay. So we have Poincaré contributions give rise to the concept of practical indeterminacy. Well, I already commented on this slide. I don't have to repeat it again. So then what we are led to is to the elementary questions of what very simple but difficult question of what or who determines the future. So there are several possibilities. One is initial conditions, which determines the picture. That has been essentially ruled out by modern physics, except for marginal proposals I will not get into. Then human design, which is not controversial. Human design means that the nature does and polishes the room and lowers the entropy of the room. That's a daily life, so that's not controversial. External intelligent design for evolution is very controversial. I will get into. I will mention some things at some moment. Well, there is always the possibility of saying, well, it's chance randomness, okay? But let's talk about that. First, we remember what are Gödel's incompleteness theorems. Were proposed by Hilbert and early in the in the 20th century that it should be possible to prove all the theorems from a limited number of axioms. Gödel proved that was not correct. In particular, a logical system with a finite number of axioms and rules, which is sufficiently complex to include arithmetics and which is consistent, which means leads to no contradiction, then it's necessarily incomplete. So it contains theorems which are not true, which are not provable by the finite number of hypotheses. We cannot know which ones are those theorems. Given an unproved and unrefuted conjecture, we cannot know whether it's true or false. In any of the two cases, we don't know whether the proof exists, but we don't find it, or whether the proof does not exist. That's the situation. There are several Gödel's theorems. One of them refers to undecidable statements. There are classes of statements that may be decided in one particular case, but not in general. And the best known example is that of the halting problem by Turing. Okay, if you have a program to be run by a computer, well, typically you know if it stops or it does not. Typically, you design a program to stop at some moment, right? But if you're given an arbitrary program and you are asked whether that will stop or not, sometimes it may not be trivial. And what Turing proved is that there is no general algorithm to know if a program will lead to the computer to a halt. Okay, so it means it does not exist an algorithm that does the following thing: apply to an arbitrary program, okay, creates a program that stops and is 1 or 0 depending on whether the algorithm to which it was applied stops or not. So that's what is called an undecidable problem. Since then, a few classes of problems have been identified as undecidable, in particular the proof of randomness. Essentially, what they do is they map it to the halting problem of Turing. Okay, what is randomness? Okay. Algorithmic definition by Chaitin. A number of sequences is random if it cannot be compressed. That means if no program exists which being shorter than the sequence, that's completely determine the sequence. So if I give you the first 1,000, more or less first 1,000 number digits of pi, it seems random, but it's not, because there are many programs which are very short that can generate that sequence, and in particular, the first one was developed by Leibniz. So this was proposed by Chaitin, okay, and he proved that but what happens in the arbitrary case? Well, another example of a random thing, if I give you 1 billion numbers of 5, you say it's not random. It's not random because you can compress it, because you can write a small program and say, write the number of 5 1 million times, okay? In any case, what in general? Something looks random, but can you be sure if it's random? Well, what Chaitin proved is that there is no general algorithm to decide if a sequence is random. The random characters of a sequence is undecidable in the Gödel and Turing sense. So randomness cannot be proved. Well, we go back to the question of what or who determines the future, and there was a possibility that was chance of randomness. That's what some people could claim, but we find that that's improbable. So that means that the absence of design cannot be proved. Randomness, understood as indeterminacy without design, can be a reasonable, useful hypothesis, essentially to make progress on some occasions, statistical physics, quantum physics, convolution theory, but not provable in stricter sense. The concept of randomness cannot be ascribed with certainty to any process. Randomness is what in physics we would call a phenomenological concept. Okay, it's useful and we need it and so on, but we cannot give it an ontological value. That's the point. Okay. Well, you know, in the concept of chance, randomness is very important in biology, but that is okay. No problem if it is used as a method, okay? But when you put it onto a philosophical, you put it at a philosophical level, then you may be inconsistent. So there is in particular this famous book by Monod, in which, you can find many quotations, but essentially he gives arguments that are totally circular. I mean, he never defines chance, doesn't define it, talks about chance. And he says that chance is fundamental, and because it's fundamental, then therefore it's fundamental. Anyway, that's fine, but it's a bit lacks a bit of consistency. Okay, so it could be understood, you know, that of course the work of Chaitin was not known at that time, but at least he could have realized that those statements were not falsifiable in the sense of Popper. So at least, and it's okay to make those statements if you send them as your philosophical interpretation of scientific knowledge. But to give them a metaphysical status, I think it's not correct. Popper formulated the Parzialic criterion, which is understood as the cornerstone of what is the scientific method. I'm very Popperian in that sense because it settles many issues. Okay. A theory is scientific if it is refutable by a conceivable experiment, which then we say is falsifiable. In a strict sense, a scientific theory is never verified in a definite way, but it can successfully pass many probes, in each of which it could be refuted or falsified. And practical certainty about some theories can be reached. If I say that all the stones fall, if I put them loose, then of course I will have to prove it. I will have to do it with all the stones. But if I make a statement that could be refuted just once, then that's scientific. Okay. Well, since randomness is unprovable, then one concludes that the finality theories, the teleological theories, are unrefutable in principle. This statement was made by record, but I would add to that if something is fundamentally unrefutable, then it's not scientific because it cannot satisfy Popper's falsifiability criterion. Okay. So what we find is that statements about the existence of design may be occasionally very reasonable philosophical statements, but are not scientific in a strict sense. Statements about the absence of design are not scientific either, since randomness cannot be proved. So, this we come to a stalemate, okay? So the finality hypothesis is not scientific stricto sensu because it's irrefutable in the general case, and science hypothesis is not scientific in a strict sense because it's unverifiable in its particular case. Okay. Of course, that does not please very opposite communities. Okay, let's say the intelligent design people and the Talibans of chance. Okay. So we go back to this question, and what we find is science may suggest the existence of design, but cannot prove it, and cannot prove its absence either. In particular, it cannot prove the absence of intelligent design or its presence. I mean, that's the way it is. Okay. Questions about purpose may be of high philosophical interest, but must remain outside the scientific debate. Scientific debate in the sense of the debate with the scientific method. Okay, can be a very reasonable, interesting philosophical debate. Okay, what I'm saying. Well, this takes us to the question of limits of science. Well, there are many possible classifications, but I find this one useful. We have the provisional limits of science, which are those that are displayed daily by any sound research program. Beyond those limits, what we have is realities that are within the domain of science and within the reach of science. Then there are the external limits, which are beyond them. There are realities which are outside the domain of science and therefore outside the reach of science. For instance, the creation from metaphysical nothing, conscious of a subjective experience, that's my personal view at least, ethics, human rights, aesthetics, the concepts of God, soul, and so on. They have in common an element of immateriality. But during the 20th century, science has discovered limits which we call internal, because beyond those limits, there are realities which are within the domain of science, but which are outside the reach of science. And in particular, we have the incompleteness theorems by Gödel, and the indeterminacy combined with all the work of Poincaré, Heisenberg, and Bell, and then this has a number of consequences. One of them is that future is not fully contained in the present. There are non-observable causes. Mathematical truths are not reachable by human reason, not all of them. Finality beyond the reach of science finality is beyond the reach of science, but not of reason. And so the myth of an all-explaining science is unjustified. It's a remnant of the 19th century worldview. So, but still is around. Seems pervasive. It's totally unfounded, according to the picture that modern physics is giving us since 1 century ago. And now we understand that even better. So what I have said so far can be found in these places. There is a version in English, open access, and a version in Spanish in the web page, a bit longer in the web page of the University of Navarre. As I said, now I go to build inequalities again. Okay, as I said, the Nobel Prize was given for people who observe experimentally the violation of this thing, of these inequalities. What are these inequalities? Well, the thing is, when this undeterministic picture of nature emerged with the modern quantum mechanics, probabilistic view, some people did not like it, in particular Schrödinger, Planck, Einstein did not like it. And then some people say, okay, there may be some hidden variables which you don't see, but which in practice, rescue determinism. And for several decades, it was thought that, believe or not, to believe or not in hidden variables was a purely philosophical choice. But then John Bell noticed, was a genius-like piece of work, that there could be experiments in which there can be a difference in the predictions between objective realistic theories with hidden variables and quantum mechanics. By the way, there is one Valerio. He knows about Berlin quite much more than me. He will be a talk on that, and he wrote a particular review, but no locality. Well, essentially, the experiment that was proposed by Bell is that you emit two photons in different directions, but whose polarization is not well defined, but it's entangled. So one has one polarization, the other one has another one, and so on. And okay, and then in that situation, well, I have no time to go into the details, but if the polarization is written in terms of a variable that I can take values plus or minus 1, or you wish in terms of spin could be up or down, we can define a correlation function between what Alice finds and both finds, that assuming that there are hidden variables, sometimes are called lambda, that which the photons carry with them and with instructions of what they will respond to whatever question they are asked, then that correlation function has to be smaller than 1. But quantum mechanics predicts that it has to be smaller than 2 times, S has to be smaller than 2. And quantum mechanics predicts that correlation function must be more than 2 times square root of 2. And so when the correlation function takes values between 2 and 2 square root of 2, we say that quantum mechanics violates the inequalities, which fundamentally refutes the existence of hidden variables, of local hidden variables, which are the natural ones. Since then, the violation of inequalities has been observed in systems as different as photon systems, electron spins in nitrogen vacancy centers, cold atoms, superconducting circuits, in which the macroscopic electric current is the quantum variable. The observation of quantum mechanical effects with a macroscopic current in superconducting circuits was rewarded with the recent Nobel Prize in 2025. So there is no trace of local objective hidden variables in nature. One could even generalize the Bell inequalities to include non-local hidden variables. And actually, Tony Leggett, who sadly passed away a few months ago, he got the Nobel Prize in 2003, was my mentor in the United States, and I have been in close touch with him for many years. So, particularly, he proposed this piece of work in which he generalized Bell inequalities for non-local hidden variables, not the universal ones, but for a very reasonable world class. And its violation was experimentally observed by Zeilinger group and published in Nature of 2007. Zeilinger is one of the Nobel Prize winners of 2022. Okay, so we are. Anyway, so now Anthony Leggett, who died last March, in his second to last paper, is a sort of little summary of a talk that he was given. Is published in this journal of the Institute of Physics, and he makes a very strong statement. He says that my claim is that the greatest physics discovery of the 20th century is the realization that experimental predictions of quantum mechanics are under certain conditions inconsistent with those of any theory of the so-called objective local class and the subsequent experimental falsifications of all such theories. He says that's the most important discovery of the 20th century. Of course, he doesn't say it's about quantum mechanics because it's within quantum mechanics, but he puts it above permitted theory, for instance. Okay. Anyway, I'm not going to say whether that's exaggerated or not. I think it's interesting to notice that Tony Leggett made this point at the end of his life. Anyway, so the conclusions are that if I had to summarize them, I would say that scientific knowledge has fundamental limits. Some are discovered by science itself. We can call them internal. The debate on the existence or absence of purpose cannot be settled through the scientific method. Nature refuses to support hidden variables, and with it the notion of self-determined matter, which is one of the underlying dogmas of materialism, simply not justified by science. So we could say in a colloquial way that material reality has holes. It's not self-sufficient. It's not fully self-contained. In particular, we conclude that the future is fundamentally open, which means in particular that to a large extent we are responsible for it. Okay, so no excuse to say, no, it was not me, it was the Schrödinger question. I was just obeying my Schrödinger question. The outcome we know could be different, okay? And anyway, I probably said, Javier will talk about this, things that are related to this. Anyway, the title of his book 1 year ago is How the Spirit Acts and God and the Soul in the context of contemporary science. Okay, thank you very much for your attention.
Very good. All questions, please. Yes.
Yes, thank you. Peter Beerley. I didn't quite catch why you suggest that local hidden variables is a necessary dogma for materialism. And then furthermore, I was curious as to your thoughts about other ways around, such as the superdeterminism.
Well, let's say, so I would say, I mean, you can define materialism in different ways, but I think essentially it's a philosophical view of the world which says that matter, everything is understood in terms of matter, and that's it. Now, if that is the case, that in natural way leads you to determinism, okay? Because if things are not determined, then who decides the outcome? Yeah, you need something else than matter, because the indeterministic picture of quantum mechanics is that you prepare a system in different occasions. You prepare it exactly in the same quantum state, and the outcome cannot be predicted for one particular experiment. You can predict the statistics. So then that is why this picture of this probabilistic picture of quantum mechanics, finds resistance. And then, so people with that view tend to try to rescue the picture of determinism, and in particular, they tend to defend hidden variables. Now, another story is whether that philosophical picture is attractive, which for me is not attractive at all, because I don't know, to think that here we are, everything that we are doing now was determined in the Big Bang, and we have the illusion that we are talking and thinking. For me, it doesn't make sense from the philosophical point of view. But on top of that, nature does not support it at all. Okay, so when we are talking about the quantum mechanics of a macroscopic variable like electric current in a superconducting ring, involving coherent superpositions of billions of electrons moving in opposite directions, where are the hidden variables there? I mean, when we talk about photons that have zero mass and move, where can you put the hidden variables? I mean, people who defend hidden variables don't have the slightest proposal. Now, regarding superdeterminism, well, that's not scientific, it's irrefutable. I mean, if you say everything was determined in the Big Bang, that's unrefutable. Yeah, so how can you refute that? But then it gets to a point in which we have the science facts and we make what are the most reasonable assumptions. You combine it with your philosophical view, then I think at present this materialistic picture is completely unfounded.
Thanks, Polis. The thing that you've left out in your discussion is that determinism applies only to measurement, right?
Yeah.
And so the universe, until the advent of intelligent creatures who could do quantum measurements, is completely determined according to quantum mechanics. So evolution and everything leading up to our or some other intelligent creature's advent is a completely determined outcome as far as quantum mechanics is concerned.
Well, yes, we don't have a complete theory of quantum gravity, but we know,
No, I
some
understand that.
things, and there are some people who propose that at the cosmological level, things are intrinsically classical. In any case, all that we know for sure is that we never, with our brain, see a coherent superposition of things. If a system has been in a coherent superposition of several possibilities, just until a few seconds before we watch it at it, we can never deny that completely. So what we know is that, of course, when I say measurement is the standard setup, but an dissipative environment which is creating friction on the quantum variable is in practice doing the same thing. And certainly there is friction all over the place, okay? Even if you have a free object in free space, then due to the cosmic background radiation, that defines the position of the system, because different positions give rise to different evolutions of the electromagnetic field.
That makes it unpredictable, but it doesn't make it indeterminate.
That makes them unpredictable, yes, but in particular means that you cannot determine what will happen in one particular outcome.
Yeah, we can't determine it, but it doesn't mean that intrinsically it's not
Maybe we
determined.
can continue the discussion in the coffee break.
Well, intrinsically, I think it's intrinsically undetermined according to our present view of quantum mechanics, which has been, which is strongly supported by
Maybe
experimental knowledge.
Just the last question, okay, Paul, yeah.
Yeah, my name is Paul O'Hara. I taught probability for many, many years. I would distinguish between, take one billiard ball on a billiard table, pretty deterministic. If you know the initial impact, you assume context. First of all, let's back up. Everything has a context. So you have to define your context. So as a mathematician, otherwise you don't know what you're talking about, right? So once you define your context, perfect reflections, I could determine everything with one billiard ball on a single table. The moment I put in n billiard balls or quite a number, become deterministic, or what you use on Lagrangian phrase, non-systematically. You lose total control because the amount of initial conditions accumulates exponentially every time you want to do a calculation. You can't do it. That's very different to the type of randomness associated with entanglement, which is an emergent correlation, which is not deterministic. So I think we also need to refine our language epistemologically. I like Lonig, and I think he's clarified a lot of stuff in terms of language, of how you approach certain problems. But I'm not disagreeing with you. So I just think we can clarify some of the language.
Well, in quantum mechanics, we have an indeterminacy, okay?
Well, hold on. Mathematically, if the terms, because you're using an L2 function, it's a Hilbert space L2 functions. If I take a limit and push it into the boundary, I can actually get a delta function, which is actually
yes.
So it's again context. All I'm saying, everything is context.
Since you mentioned the concept of entanglement, the entanglement is essentially using that indeterminacy, okay, but in such a way that it's correlated. So I don't know whether I have two electrons with spin up and spin down. I don't know what I will measure, but I know that if one is up, the other one will be down.
Well,
okay. So they are correlated, but together they are indeterminate. Okay.
Sure. Well,
and that's what entanglement has. And
let's continue the conversation. We need to wrap up, and we can continue the conversation in the coffee break. So let's thank. It's interesting. 15 minutes, so we'll wrap up here 11:15.
yes. They're correlated.
Nice talk, nice talk.
No, that's fine. You did great. Don't worry.
You were fine.
Anyway, it's fine. I mean, we are getting the Italian, some Italian spontaneity. All right, everyone, please have a seat. Let's start. We are a little bit tight in the schedule.
Is this free?
It's good that Yes. Right. So the first talk of this session will be from Professor Paolo Facchi. He's a professor of theoretical physics at the University of Bari and a member of the NFN, National Institute of Nuclear Physics. He studied in Bari, where he also received the PhD in theoretical physics. And his research lies at the intersection of mathematical physics, quantum information, and the foundation of quantum mechanics, with emphasis on symmetry, quantum dynamics, open system. He's pleased to participate to the conference. He's a good friend and good collaborator of mine. So I'm very pleased that you accept to come, Paolo. And you're really excited too. You were sharing about how important it is to bring together physicists, philosophers, and theologians to discuss these questions, not in isolation. So he is outside academia. He enjoys classical music, especially Bach. I guess I didn't know Bach about what Bach's learning more, and firmly believes that cats should have well-defined states. So very good. I like that. So quantum mechanics and the structure of reality, scientific insight for a theological dialogue. Professor Paolo Bach.
Look at the shade so we can see the.
Yeah, I'll do that. So thank you very much for the presentation and for the invitation, which I'm really very honored and very happy to be here. And I'm looking forward to interact and to exchange ideas, contribute to build this interdisciplinary community. Now, the title of my talk is Quantum Mechanics and the Structure of Reality and Scientific Insights for a Theological Dialogue. So let me say immediately that this will be primarily a talk on quantum mechanics, mathematical physics. So I will not try, with all these distinguished people, to derive a philosophical conclusion from physical theory. I will talk about the physical theory. So my aim is more modest. I will try to present some structural features of quantum mechanics that genuinely change our scientific description of physical reality. Okay, so let me start with a methodological premise. First of all, as I said, this is a talk in quantum mechanics and mathematical physics. And I will try to be as precise as possible about what quantum theory says and what does not say about the physical world. Second, I will distinguish essentially three levels in my talk. One is the mathematical formalism. The second level is the empirical content. And the third level is the interpretation. So the mathematical formalism I will talk about will be what is called the standard description of quantum mechanics in Hilbert spaces with operators and states and probability loop, we will see. The empirical content consists of the phenomena of statistical regularities that can be tested in experiments, such as, for example, the spectra, the interference experiment, correlations, Bell inequalities. Okay. And the interpretation, which is the last levels, the third level, begins when we ask what these formal structures and experimental results tell us about the physical world. Okay, so this distinction between these three levels is especially important because quantum mechanics is often overlooked, is often invoked also in popular discussion I mean, in many contexts. And okay, so very easily one can turn a mathematical feature into a metaphysical conclusion. So this is something that because I don't see my screen. Okay, that's all right. Okay, so the sentence in the box just gives the boundary of my talk. So I will talk about quantum theory does and does not say about reality. Okay, so this is the map of my talk. I will begin with a classical template, so with classical mechanics, because I think that the conceptual novelty of quantum mechanics is best seen against that background, the classical background. And then I will recall the quantum formalism, as I already said. I will talk about the description of quantum mechanics in Hilbert spaces, and then I will talk about structural features, in particular 3 structural features, which are incompatibility, indeterminacy, and entanglement. These are just the features I will talk about. And after that, I will discuss a little bit about the measurement problem and the distinction between the formalism, the 3 layers I talked about before, the formalism, empirical content, and interpretation. And the final part will offer a bridge to philosophy and theology, but this is just, let me say, the beginning of a discussion. Okay, so the classical templates. Let us start from the classical template. In classical mechanics, a physical state is represented by a point in phase space. That means that essentially, if you assign position and momentum of a particle, you essentially, at least in principle, are fixing all possible observables, energy or angular momentum or whatever you want. Because in classical mechanics, the observables are functions of the state of position and momentum. Okay. So this is what we get. And the dynamics is deterministic. We have already so if you know the initial state and you know the laws of motion, then you know that what is in a deterministic way the dynamics. And okay, we have seen in the previous talk that practical prediction may be difficult, in particular if you are in a situation in which you have a classical chaotic dynamic. But because they are extremely sensitive to initial data, so the prediction can be very difficult. But the important thing that I want to stress is that the underlying structure remains deterministic at the level of classical mechanics. A second feature, which is important, is just separability. So what about a composite system in classical mechanics? A composite system is understood, is fully understood in terms of the parts and that possesses independently states and properties. So the state of the whole is assembled from the states of the components. together with the interaction. With this, I mean, if you want to describe not one particle, but two particles to one particle, you just need to know position and momentum of one particle, position and momentum of the second particle, and you know the whole state of the system. Okay, so this is about separability. And the third feature is commutativity. So, as I told you, classical observables are functions of position and momentum, are functions on phase space. So they are ordinary functions. You can pointwise multiply them. And as you know, when you multiply two real numbers, the order doesn't matter. So the result is the same, whichever order you multiply them. So you have commutativity at the mathematical level. At the physical level, this means that you can interpret, this supports, let me say, the idea that different quantities related to your system can be regarded as simultaneously definite, whether or not we actually measure them. So I think that's a very important point. Okay, so you can assume that a classical system possesses all possible properties or possible observables, even if you don't measure it. If you just know its states, possesses all possible energy, angular momentum, whatever you want. Okay, so these features encourage a familiar image of classical reality. So the world can be pictured as made of things, carrying properties, evolving in time, and combining into larger system. Okay, so, and this, I repeat, is related to the fact that you have a commutative algebra of observables. Now, we will see that quantum mechanics does not merely correct this classical template. It replaces several elements of the template itself. So let me move to the quantum formalism. What is the structural break in the quantum mechanics? So as I said, the quantum mechanics is not classical mechanics with a small amount of uncertainty added. It is a completely different, it has a completely different mathematical architecture. First of all, a quantum state. What is a quantum state? Quantum state is represented by a vector in the Hilbert space, or more generally by a density operator. We will not enter this. But so to a quantum state, there is not a point in phase space to which it is attached to all possible observables. It's just a mathematical object that we will use in order to compute probabilities. I will tell about this later. And okay, so observables are no longer functions. These are operators on the Hilbert space. And this is quite a fundamental change, because at variance with functions, operators do not commute. I mean, in general, the order in which you apply the two operators matter. Okay, and so we have what is called a non-commutative algebra, and this algebraic feature will have a very important physical consequences. Now comes how you can combine these two things. You have states, which is a vector in the Hilbert space. You have observables, which are operators. And how do you relate these two things with the layer of experimental results, so what you get in the lab? And here comes what is called Born rule. You compare these two objects, mathematical objects, and you can compute probability. So this is given, okay, by the trace of state and observable. In particular, if you want the expectation of a certain observable, you just use that formula. So this essentially gives you the probability of a certain experimental outcome. So what about the dynamics? The dynamics is given by a unitary dynamics, essentially is a rotation of this vector in Hilbert space. And of course, this is famous Schrödinger equation that gives you the dynamics of the state. Now, a quantum state evolves in time in a deterministic way. If I know the initial state, I solve that equation. I know in a deterministic way what is the state at later times. So there is a deterministic equation that determines what is the evolution of quantum state. However, the connection between the experimental outcome, this is probabilistic. This is given by Born rules. And in fact, is exactly this combination of deterministic evolution of the quantum state and probabilistic outcome that gives you the conceptual tension of quantum theory. Okay, so composition is equally important. We have seen that in classical mechanics, the composition is just given. You take the states of each parts and you know the state of the whole system. In quantum mechanics, composition is described in a product of Hilbert spaces, in a tensor product. And now tensor products, these are vector spaces, and they contain not only states that are separable. I mean, the product of state of system A times system B. They contains a lot of states that are co-entangled that you cannot describe as the product of system A and system B. So the formalism introduces, as I anticipated, a completely new grammar. We have vectors, we have non-commuting operators as observable, we have the Born rule for the probabilities, we have unitary dynamics for the evolution of the state, and we have composition in tensor products. Okay, now the formalism gives a precise framework in order to have a predictive, in fact, let me say better, you have an enormous predictive precision. This is quantum mechanics, quantum theory in general is the most successful theory of, so we have this enormous predictive precision together with open questions about how that precision should be understood in terms of our description of reality. So, and this is why it is exactly this combination that makes quantum mechanics so interesting. And in fact, I think this is also why a wider audience, as popular audience, has such much interest in quantum mechanics. Now, the next 3 slides will focus on 3 structural features, as I told you, which is non-commutativity, indeterminacy, and entanglement. So let me start from non-commutativity. As I said, given 2 observables, 2 operators, A and B, the operators do not commute. If I look at A, the product of A, B, this in general is different from the product of B, A. And this difference is the degree, the fact that this commutator is non-zero, marks a fundamental difference between the quantum algebra, which is non-commutative, and the classical algebra of observable. Now, from the physical point of view, what does it mean that 2 operators do not commute? Essentially, it means that the observables are incompatible. Incompatible in a very precise sense, in the sense that they cannot be assigned simultaneously sharp values. So if you assign a sharp value to one of the two observable, you cannot assign a sharp value to the other one. So this is completely different from the classical situation in which I recall you can assign all possible observable to a state too. And this relation here is a very famous relation in quantum theory. This is the uncertainty relation that gives a lower bound in terms of the commutator of the product of the dispersion of the two observables. Okay, so that means that the larger the commutator, the more incompatible, let me say, roughly speaking, are the two observables. Okay, so this is the now this is this uncertainty principle is not a limitation in the, I mean, in experimental technology. It's not due to the fact that when you measure a quantity, you disturb another quantities because your apparatus, your measuring apparatus is clumsy or is not perfect. This is in fact a structural point. Let me give you the most important example, which is that of position and momentum. The commutator between position and momentum in quantum mechanics is proportional to Planck constant. That means that in this uncertainty relation, you have Planck constant on the right-hand side. And that means fundamentally, at the very end, that you cannot describe the state of your particle as a point in phase space. So you have to renounce completely to the description that I gave you for a classical system. I repeat, you cannot describe a particle with definite position and momentum in space. Okay? So if position is sharp, the value of position, the value of momentum is not sharp, and vice versa. So this changes the grammar of physical property. This is why I use this expression. No? I'm changing completely the description of my system. Okay, this change you can think is related to non-commutativity, non-commutative algebra. Okay. So, of course, given this mathematical description, there are a lot of philosophical questions that can arise, in particular about objectivity, about what are the precise limits on which you can. So, I mean, of course, it's a very interesting starting point. Maybe the picture, this is just related to measurement of what is called a spin of a particle. So if you have a sharp value for the polarization of the particle in direction Z, you completely lose any information about the incompatible observable, which is polarization along X. Okay, so let me move from incompatibility to indeterminacy. Now, within the formalism, as I told you, a quantum state does not determine the value of the observable, of the outcome of a measurement, but it determines the probability of a subsequent measurement outcomes. In particular, okay, there are particular observable that may be sharp. So you have a deterministic result. But now, if you prepare a system in a state in which a particular observable is sharp, and then you measure an incompatible observable, you will get a probabilistic result, which is given by Bohr rule. It's written there. Now, So the Born rule gives a definite probability distribution. However, the point is that even for a fixed preparation, the individual outcomes are generally predicted only probabilistically. You cannot say if the outcome is the yellow one there. Okay? The theory does not predict whether the outcome will be the yellow one or will be another possible one. The theory predicts in a very precise sense what is the probability of the outcome, but not which particular outcome you will get. Okay, so now I think it's very important an interpretive caution. Depending, this is the formalist. The formalist gives you probabilities by Born rules. But now, what those probabilities mean? That's, I think it's important, particular here, our discussion. They may be interpreted as ignorance, as propensities, as relational information, as rational degrees of belief, or in other ways. Okay, so this depends on the interpretation that you give to these objects. And maybe it's a good point to mention other interpretation of quantum mechanics. One possible, I think somebody will talk about it also in this conference, about Bohmian mechanics. So in Bohmian mechanics, you get deterministic trajectory of the particle, but at the expense, you have to pay some price. There is no free lunch. I mean, at the expense of adding additional variables, additional degrees of freedom, the hidden variables. And the point is that in Bohmian mechanics, these hidden variables are not local. So from the description, the physical description, they're very difficult to describe because the state, I mean, the trajectory of a particle at this point depends on the position particle, the instantaneous position. So you imagine immediately that there will be, and in fact there is a great difficulty to extend such a picture to relativity, to relativistic theory, because simultaneity is just a non-relativistic concept. Okay, this is a possible interpretation. Of course, at the level of non-relativistic quantum mechanics, this is fully equivalent. I mean, it gives exactly equivalent in the sense that it gives you exactly the same prediction that you get Hilbert space description. Another interpretation is that the many worlds interpretation by Everett. And this is something that I never understood. So I don't know how to explain you. So it's just, okay, there is the idea. It seems to me that you're completely forgetting about the Occam razor, no? You just multiply. Okay, that's it. Now, I think the safer scientific conclusion that we can get from this is that the classical ideal of properties of prediction through a complete set of simultaneously definite properties is not built in quantum mechanics. You have to renounce about that. So probability is a part of the formal predictive structure of quantum mechanics. Of course, this does not imply the absence of law. As I told you, on the contrary, quantum probabilities are governed by an exact mathematical structure. Okay? But what changes is that the form taken by physical prediction and the conceptual relation between states probabilities and the outcomes of experiments. Now, let me move to non-separability, entanglement. This is perhaps the clearest challenge to the classical principle of separability. So essentially, if you consider two quantum systems, the composite system is described, as I said, in the tensor product of Hilbert spaces. And some states are product states. That means that you can assign a definite state to both subsystem A and B. But most states, such as, for example, the state I wrote there, but the equation is not important. This is called Bell state. These are entangled states. Okay, these are states that you cannot write as the product of two states, states of the first system times states of the second system. So what does it mean, this fact? It means that the global state of essentially, the global state is in general not determined by the reduced local states of the system. I recall you what I said before about classical mechanics. If you have two particles, two point particles, if you know position and momentum of one particle and position and momentum of the other, you know exactly the state of the global system. This is not the situation, the usual situation in quantum mechanics. So if you know the local state of one particle and the local state of the other, you still are missing something. You don't know the global state of this. And this missing something is what is called entanglement in mathematical. Okay, so essentially different global states can share the same local states. Okay, but they differ in the possible correlations. Let me stress again. This means that the complete physical description of a composed system, of a composite system, is not contained independently in the two parts. Okay, so the whole, if I want to use a slogan, the whole is not simply a collection of parts, each carrying its own complete states. This is the typical situation for an entangled state. So now, this statement, of course, gives rise to several experimental, proved, tested results, in particular to Bell type results to inequality, but I don't want to enter here because Valerio is going to talk about it. So essentially, there are very interesting experimental consequences, and there are also very interesting technological consequences about this. And I guess Vincenzo, knowing him quite well, he will talk about the use of entanglement for example, technological application. Okay, so from the point of view of this talk, the important message is that entanglement places an empirical constraint on the classical intuitions about locality. The fact that you can separate a global system without the single description of each point. Okay. Okay, I think I already said about this. This is just not a metaphor for everything is connected, but it has, I don't know how much time do I have. 8 minutes. Okay. Well. Okay, so let me go on. So the conceptual consequence is that a quantum whole can have properties that are not reducible to independently possessed properties of its subsystem. Now, let me move, since I have just 8 minutes, let me move to the measurement problem. The measurement problem is that essentially you prepare a state, you have an apparatus, and you get some outcomes, for example, outcome A or outcome B. And now let me formulate in a simple way, in a compact way, what is the problem? The problem is that, as I told you, the state evolves in a unitary way, we preserve superposition, and it creates the interaction with the apparatus creates entanglement. Essentially, you have these dynamics, unitary dynamics, and you don't understand why at the very end in the lab we registered either outcome A or outcome B. Okay, so the situation is that how is this definite outcome relates to the superposed and entangled state which is produced by the unitary dynamics of the state. So this is essentially the problem, the measurement problem. And also here there are several interpretations. I don't want to enter into them. There are collapse interpretation. There are again Bornian mechanics that gives you there is a trajectory and so on. Relational approaches. There is an approach which is called cubism, which is just to change it, to try to revise the status of the meaning of a state as a, okay, in terms of probabilities. But now, what I want to talk about very briefly is just the coherence. The coherence plays an important role here. Essentially, it plays a role that essentially it says that the interaction with the environment just makes some interference. It suppresses some interference between alternatives in open system. Okay, so essentially this interaction with the environment, which essentially entanglement with the environment, is what creates decoherence, and in a sense, it is a way to try to understand this dichotomy between unitary dynamics and the result of an experiment. Okay, I think my time is running over, so let me just move to the three layers that should not be confused. One is the mathematical formalism, paper spaces, operator states, tensor products, probability, as I told you. The second layer is the empirical content, so what you get in the lab, spectra, interference, non-classical correlations, statistical prediction, and what is the role of the observed experimental test, and so on. And the third layer, which I think is the most interesting layer here today, is just interpretation. So what's the formalism and the empirical results have to say about physical reality? So what is a state? When can we talk about definite property of an observable? What constitutes an outcome? What is the role of the observer or the experimental context? So I think this is the layer that, and this matters because I think that most misleading claims come exactly from confusing these three layers. Okay? And from moving, I think, too quickly from one layer to the other without, noticing it, without, this is something that we have to be very careful. And so sometimes one takes a mathematical expression and try to interpret it as an ontology. Or it takes an interpretative idea and thinks that this is an experimental result. So the three layers should be one should be very, scientific rigor here is what protects the dialogue from category mistakes, which are very dangerous in this situation. How much time? Okay. I'm moving to the conclusion. So I just repeat what is the difference, what quantum mechanics changes from a classical template to a quantum structure. This is a picture I asked ChatGPT to. It's quite nice. You have this clockwork universe, and you get. I don't know. Okay, so in the classical template, you have deterministic trajectories. You have separable parts. You have simultaneous properties, so you can assign all possible properties. And you have that the measurement reveals pre-existing groups. In the quantum picture, you have instead probabilistic prediction given by Born-Hall. You have entangled holes, you can separate parts. You have incompatible observables. And you have non-classical measurement outcomes. Essentially, measurement in a sense contribute to the value of an outcome of a observable. Okay, and so the scientific takeaway is that quantum mechanics, of course, does not answer every question about reality, but it changes which questions can be asked and not. Okay, final slide, a bridge to philosophy and theology. So physics offers precise constraint, tested structure, experiments, tends to clarify concepts, and it gives you limits. Where dialogue begins. Okay, this is, so I'm moving, this is Dante, this is Ulysses when he's moving in the open ocean after. So I'm moving in a territory that for me is completely, okay, unexplored. Namimisi per l'alto mar aperto. Yeah. So essentially, of course, one is the intelligibility, and the other point is that, of course, order and contingency, and how they are related, how causality can be understood, and what measurement teaches us about objectivity, and what is the relation between systems and experimental context. Okay, so I just repeat something that I already said. The methodological principle is that a fruitful dialogue respects the distinct methods and questions of physics and theology, and philosophy can help understanding and clarifying their point of contact. So this is what I hope in the next day. And so the take-home message is that quantum theory changes the mathematical structure of our description of physical reality. And there are formalism, experiment, interpretation. So, okay. Thank you very much.
Well, questions?
Well, more than I enjoyed your talk immensely. I agree entirely. Would it be worth pointing out that all the Bell states are rotation invariant, and when they decohere, you break the invariance? Are you aware that all the Bell states are rotation invariant? I can prove it quite easily. You just break. So, and also the second thing would be to note that quantum probabilities are not the same as classical probabilities. For example, they wouldn't obey the Chapman-Kolmogorov equation. But I mean, we're getting off. But I agree entirely. It's just, but again, even the probability notion is quite different.
So about the rotation invariant, I didn't want to enter too much about inverse inequality. And in fact, I didn't tell you that, I mean, the fact that if you measure the angular momentum of one particle, the spin of one particle, and you find the spin in some direction, and you have perfect correlation with the other particle in the same direction, it's not so surprising. you have exactly the same result in classical mechanics. If you just use conservation of angular momentum, you start from a state with, okay, maybe a simple way, zero angular momentum, and you have two parts, then the angular momentum is conserved. And so if one particle has a certain angular momentum, the other particle has just the opposite one. Okay. The very surprising thing in quantum mechanics is that this happens whatever the direction you measure. So at a certain point, there is a change of rule that the observer can, during the time of flight of the particle, just change his idea and just decide to measure in another direction. And you have perfect correlation or anti-correlation, whatever the direction you measure. That's, I think, a very important point. So in a sense, no, not in a sense, you have the correlation in quantum mechanics are stronger than in classical mechanics. So they're just not due to rotational invariance, conservation of angular momentum. Of course, it plays a role, but there is more. And the same for quantum probabilities. But maybe we can talk about that.
Just one, yeah, another question.
Yeah, here. So I like a lot how you presented this clarification of dialogue. Still see a link or a bridge that needs to be filled between formalism and experiments, because you need to define the basis in which you are going to make the measure. Because the coherence doesn't give you the preferred basis. So you need this context. I mean, you need to touch base with the formalism, so to produce a model to compare with experiments. Would you agree on that?
Symmetry breaking.
So, I mean,
Symmetry breaking
this is,
You have a selection.
Symmetry breaking.
I mean, you have, of course,
Because you have a context, because you have an environment.
Selection works
yeah,
perfect.
of course.
So you need more information.
You need more information on the environment. On that, I agree. Yeah, I mean, of course, let me say in a different way. If your system is not an isolated system, particularly if you have to take into account the role of environment, of course, your description exactly, we are falling in the same problem that I told you about separability. Okay, so in order to describe your system, you need the description of system, apparatus, and environment, because there is entanglement between environment and.
Yeah, if I may just follow a follow-up. I'm just wanted to say that that separation, system, environment, or the interaction Hamiltonian is something that the theory doesn't give you. So it's a.
I mean, this is the role of theoretician, exactly to understand how you model the experiment.
Yeah, but in a sense, you need interest, you need focus on in a specific physical scale. So there's still a link between formalism and the experiment.
Well, this I understand, but I think I read this as a general link which happens in physics between theory and experiment. Of course, there is a continuous interaction between theory and experiment.
We need to continue the discussion. Maybe you can come further up to set up. Maybe we'll get just another last question.
So I just want to comment on the role you play, you give to the uncertainty principle, right? But in a way, uncertainty principles can be easily linked to Fourier pairs, right? This is the and then of course you have Fourier pairs in classical optics, in classical physics, okay? Near field, far field, and bandwidth time. So what is the quantumness precisely in those approaches?
That's a very good question. I mean, you are saying that maybe you get uncertainty principle, for example, in music.
Yeah.
Okay. So if you decide what is the frequency, the note of, and the length, I mean, how much time you can. So, for example, if you have an instrument which plays very low pitch, you cannot play fast music. I mean, so this is
So,
the uncertainty principle is referring to. This is related to Fourier transform. Actually, essentially,
Ascol
if a signal
Perelomov is writing a book.
Yeah.
Its title is Quantum Mechanics, Fourier Transform, and a bit more. What
Yeah.
is the bit more?
Yeah, of course, everything is not Fourier transform. No, so talk about position and momentum. I can fully agree. Sorry.
So the next speaker is Father Robert Veriel. So Father Robert, let's continue the discussion in the coffee break. Sorry. So Father Robert did his studies at Cambridge University in UK and PhD Mathematics Blackfriars Studium in Oxford, DSPT Berkeley, California, and he has he got an MA in philosophy there, and then also a MA in physics and PhD in philosophy at Baylor University. So another example of interdisciplinary background. And he is interested in making sense of Aquinas' philosophy of nature in the light of contemporary physics. He used to be a system engineer and a software engineer for a solar company before entering religious life. So his talk will be on hylomorphism and the meaning of light.
I guess I need to, am I on? I guess I need to connect to get on Zoom. Just, I guess so. I think now go to Zoom. I'll just join. Just join. Like, is this connecting?
Okay. Okay. Here you go.
So in the first decade of the 20th century, a young Georges Lemaitre expressed some excitement to his science teacher, the Jesuit priest, Father Ernest Barrow, over a particular passage from the book of Genesis. To Lemaitre's imagination, this passage seemed to suggest a foreshadowing of developments in science. Father Barreau, however, suggested Lemaitre should curb his enthusiasm. Saying, if there is a connection, it's a coincidence and of no importance. And if you should prove to me that it exists, I would consider it unfortunate. It will merely encourage more thoughtless people to imagine that the Bible teaches infallible science. As the most we can say is that occasionally one of the prophets made a correct scientific guess. Now, Father Barreau obviously had a huge influence on Georges Lemaitre. Many years later, in 1951, when Father Georges Lemaitre was an internationally recognized and respected physicist, he expressed dismay when Pope Pius XII tried to make a connection between his work on Big Bang cosmology and the fiat lux of Genesis, creation narrative. One can imagine that if St. Thomas Aquinas had been around to see the developments of 20th century cosmology, he too might have been very concerned about drawing a direct connection between the Christian doctrine of creation ex nihilo and the scientific theory that the universe expanded from a primeval atom. For example, in his commentary on the sentences of Peter Lombard, Aquinas argued that it could never be demonstrated by human reason that creation had a beginning in time, or that it did not have a beginning in time. So the belief that it did have a beginning in time could only be accepted in faith. Now, I agree that we should be duly cautious in drawing connections between what we read in Scripture and what we understand of contemporary science. After all, we don't want another Galileo affair. But nevertheless, there is also a danger in making the division between science and faith too rigid. And it is with some of these dangers in mind that I'm about to share with you that has motivated my interest in the role that light plays in Aquinas' hylomorphic ontology. So let's consider a first danger. So as I said, Aquinas thought that it was impossible to establish by human reason and scientific investigation whether or not the universe had a beginning in time, but that we must nevertheless still believe in faith that the universe did have a beginning in time. Now, believing that the universe had a beginning in time is not some superficial tenet of the Catholic faith that could be easily jettisoned. For the denial of a temporal beginning to the universe could easily undermine belief in a universe that has a purpose which God wishes to accomplish through salvation history. If the universe had no temporal beginning, it would be much more plausible to believe in a universe of endless repetitive cycles. Therefore, if a physicist were to boldly claim that the universe had no beginning, this would present a serious challenge to the plausibility of the Catholic faith. Aquinas would have said such a bold claim would be misplaced, but we live in a world where people are far more likely to listen to a physicist than to a medieval theologian. But as it turns out, this medieval theologian was right, and physicists who claimed that the universe was eternal had overstated their case. This was one of the points Pope Pius XII made in his 1951 address to the Pontifical Academy of Sciences, and it is a point that doesn't strike me as at all problematic. As another example of why we should avoid a too radical division between science and faith, consider what Catholics believe about the soul. Hylomorphism claims that there are real ontological principles, matter and form. And according to the 14th century Council of Vienne, the rational or intellectual soul is the form of a human body. But this still leaves open the question of what do we actually mean by form? For suppose we had been told in high school that the whole of reality is made out of tiny particles that interact with each other like billiard balls, then we might suppose that the form of a human body, the soul, was some kind of immaterial principle that introduced some indeterminacy in the behavior of the particles that constituted the human body, making them swerve a slightly different way from how they would behave in the absence of a human soul. If a physicist were to tell us there were absolutely no scientific evidence for such swervings, then this might make us doubt whether the soul was really real. It should therefore be of great interest to those of us wishing to defend the Church's teaching on the human soul that what Nobel Prize winning physicists like Steven Weinberg mean by a particle is nothing like a tiny billiard ball. And so the whole question of whether these particles swerve or don't swerve is completely wrong-headed. Thus, there are benefits to be gained when theologians keep up to date with contemporary science and are able to critically evaluate it. And there are also serious dangers when theologians assume anything a scientist says is of no relevance to theology. And as a final example that I think is of particular relevance to the relationship between hylomorphism and light, suppose our high school physics teacher had told us that light consisted of super fast massless particles that bounce off things like billiard balls. And that when we say we see things, what is really happening is that these tiny particles of light are hitting the atoms in our eye, and depending on the location and the energy with which these interactions occur, we have particular experiences from which we can infer there is something out there that led to a change of events resulting in this experience. But if this is how we think about light, it seems to place a huge chasm between our experience and the thing we believe we are experiencing. So, for instance, when the priest holds up the Blessed Sacrament at Mass and says, "Behold the Lamb of God, behold him who takes away the sins of the world." What's to stop someone saying, well, you're not really beholding the Lamb of God, it's just that light is bouncing off the Blessed Sacrament and then tickling your eyeballs, resulting in you thinking that you see the Blessed Sacrament. What you are directly experiencing is the particles of light, which is entirely different from the Blessed Sacrament. Now, what these three examples demonstrate is that there is great danger where we find ourselves in as Catholics if we insist on a radical separation between science and faith. But if we do, we will find ourselves completely ill-equipped to respond to scientific claims that seem to challenge the faith. Now, Aquinas was greatly interested in the natural science of his day. Whilst he acknowledged there was a division between science and theology, this division wasn't so radical that they couldn't inform each other. What I find particularly interesting about Aquinas' understanding of the natural sciences is that the apparent challenges to the faith that some people worry about today weren't at all challenges for him. This suggests we might adopt a threefold strategy in trying to help provide people who have help to address the worries that people have today. So firstly, we can try to gain a thorough and non-anachronistic understanding of how Aquinas saw the natural world. And secondly, we can try to explain why the apparent scientific challenges to the faith weren't challenges to Aquinas. And thirdly, and maybe this is the hard bit, we can try to show that despite Aquinas' arguments sometimes resting on false scientific claims, these arguments can be appropriately updated in the light of contemporary science so that the conclusions he draws still hold. So in my talk, I want to consider the role that light plays in Aquinas' hylomorphic ontology and how he avoids there being any epistemological chasm between our experiences and the things we judge ourselves to be experiencing. I won't have time to explain how we might update Aquinas's understanding so that to make it more plausible in our modern world. So I apologize for that. But all I want to suggest is that Thomists who wish to engage with contemporary science shouldn't be entirely silent about what Aquinas says about light. So what does Aquinas say about light? Well, in the Prima Pars of the Summa Theologiae, Aquinas devotes a whole question to light. In question 67, there are 4 articles in which Aquinas asks, is the word light used in its proper sense in speaking of spiritual things? Is light in corporeal things itself corporeal? Is light a quality? And was light fittingly made on the first day? In the first article, Aquinas argues that in its primary meaning, light signifies that which makes manifest to the sense of sight, but that this meaning is extended to that which makes manifest to cognition of any kind, from which he concludes that when the word light is taken in its strict and primary meaning, it is to be understood only metaphorically when applied to spiritual things. So here, Aquinas is adopting a different position from St. Augustine, who thought that our primary meaning of light applied to spiritual things and then only secondarily to physical things. So the word light is, of course, used in many different ways. We speak of natural light, we speak of the light of reason, we speak of the light of faith, the light of glory, and we speak of God as being light. But Aquinas thinks that when we read about light in the first book of Genesis, we should understand it primarily to mean the natural light by which we see things. So this means that when theologians speak about light and when physicists speak about light, they are sometimes speaking about exactly the same thing, although they might disagree to some extent. So unsurprisingly, some of the things Aquinas says about light are wrong. For instance, in the second article of this question, Aquinas argues that light is not a body because, unlike a body, light can travel from place to place instantaneously. Nevertheless, just because, now we know that light doesn't travel instantaneously, of course. But nevertheless, just because a conclusion is drawn from false premises, it doesn't follow that the conclusion is false. And the fact that we can think of light as being as a electromagnetic wave and oppose that unlike quantum field suggests that Aquinas' conclusions were probably true here. And then Aquinas goes on in the third article to argue that light is a quality, and it's here that we begin to see the important role that light plays in his understanding of hylomorphism. In arguing why we shouldn't think of light as a substantial or spiritual form, Aquinas says that as heat acts towards perfecting the form of fire as an instrumental cause by virtue of the substantial form, so does light act instrumentally by virtue of the heavenly bodies towards producing substantial forms. And then in the fourth article, where he argues for the fittingness of assigning production of light to the first day, he says that the formlessness of darkness should be removed, first of all, by the production of light, because light is a quality of the first body, and thus by means of light it was fitting that the world should first receive its form. By first body here, Aquinas is here referring to the heavenly bodies as a whole. Now you might be thinking that this all sounds very medieval, and that we should just follow St. Augustine and say that this light of Genesis is a purely spiritual light. But my concern with immediately discarding these aspects of Aquinas' medieval physics is that by doing so, we never really get to understand how he might have addressed questions such as why there isn't an epistemological chasm between our experiences and the things we think we are experiencing. Only once we have a full and non-anachronistic understanding of the role that light from heavenly bodies plays in Aquinas' ontology can we begin to evaluate whether this role for light is entirely redundant, or whether we need to posit, or the role of the heavenly bodies, whether they're redundant, or whether we need to posit some other principles that can do the work which Aquinas attributed to this light coming from the heavenly bodies. Also, further reason for why we should be cautious of going down this entirely spiritual route in Genesis is that it might be the case that by discarding something about the natural world, we actually that Genesis is telling us, we might actually be discarding something that God wanted to reveal to us. So we need to just be discerning about this question about what kind of light is actually being talked about in Genesis. So to explore the role that light plays in Aquinas' hylomorphic ontology, I need to say a little bit more about hylomorphism itself. And as I've already mentioned, hylomorphism claims that there are these real ontological principles, matter and form. I still need to say more about what Aquinas means by matter and form. So a hylomorphism begins with the observation that the things in the world around us change. And some of these changes, the things remain the same kind of thing with only some of their properties changing. These are so-called accidental changes. But there are also changes where things change into different kinds of things. These are so-called substantial changes. But in either kind of the change in question, there is a principle through which it can be other than it is in some respect, either a different thing entirely or just having different properties. And this principle is the thing's matter, also referred to as its principle of passive potency. And there is also a principle that determines its current state of actuality, and this is its form. Now, in numerous equations, Aquinas speaks of form as a kind of ontological boundary. For example, in his commentary on the De Sensu et Sensato, he says, what is unbounded is related to what is bounded as potentiality to actuality, or form is a boundary of matter. Similarly, in his commentary on the physics, he says the contained body is related to the container as is matter to form. In his commentary on the De Cielo, he also says the contained and the terminated pertain to the notion of matter, but to be a container and that which terminates to the notion of form. And also in the Contra Gentiles, he says in things composed of matter and form, the form has the character of a term, and that which is terminated by the matter or something material. And it also says that a substantial form is a kind of limit. So there are all these examples where Aquinas is speaking of form as a kind of ontological boundary and container. And the reason I prefer to think of form in this way as an ontological boundary rather than, say, just an organizing principle, as you'll often hear it described, is that there can be entirely immaterial ontological boundaries, whereas the notion of an immaterial organizing principle strikes me as somewhat unintelligible. So the idea that form is a kind of ontological boundary also suggests that it is through a being's form that beings meet each other. So when understood in this way, it's not at all surprising to hear Aquinas telling us on many occasions that a thing acts through its form. So also, when we think of form as a kind of ontological boundary and container, it invites us to think of how beings exist in themselves and how they exist in other beings. A created being that exists in itself is a natural being, and the substantial form is the ontological boundary of a natural being. But a being can also exist in another being, and there are two important modes in which this kind of existence can happen. A being can exist in another being by its power, that is, it can exist virtually in another being. So this is this is virtually how Aquinas understands virtually more than how we understand it today. So this is presence by power. And a being can exist in another being intentionally so that it can be known. As an example of a being that exists in another by its power, consider this quote from question 8 of the Prima Pars, in which Aquinas talks about God's omnipresence and power, and says, spiritual things contain those things in which they are, as the soul contains the body. So Aquinas is saying that the soul both contains the body and is in the body. Now, this might sound first rather paradoxical, but the context of this question suggests that the soul is present in the body, not according to the soul's natural subsistent being, but according to its power, that is, its virtual being. And this suggests that the soul, present by power in the body, is the act that permeates the whole body and serves as its ontological boundary, differentiating the living body from inanimate bodies. This understanding of form as the ontological boundary of matter is consistent with Aquinas' statement that form is the act of matter. As for being that exists in another intentionally, consider anything outside yourself that you're currently experiencing. Being exists in itself naturally, but according to Aquinas, in order for you to directly sense it, it has to have a mode of existence in your senses. So the very same being that exists naturally in itself also exists intentionally in your sense of sight, for instance. This mode of being too has an ontological boundary, namely its sensible species. And so it's through the sensible species that the thing sensed meets the one who senses. And likewise, as you understand this thing, it is all exists intentionally in your intellect. And this mode of being also has an ontological boundary, namely its intelligible species. It is from this understanding of intentional being that we get sayings in Aquinas like the thing known is in the knower according to the mode of the knower, and the intellect in act is the intelligible in act. Since Aquinas denies that there can be action at a distance, this has implications for the medium which separates us from the natural beings that we sense and understand. For in order to avoid there being any epistemological chasm between the knower and the known object must also exist intentionally in the medium between the knower and the known. Now, it is in regard to this regard that light plays a crucial role in allowing us to directly see colored objects. To explain this role, we need to make the distinction between two kinds of light, lumen and lux. For Aquinas, light, as translated from the Latin word lumen, is the act of the transparent insofar as it is transparent. In terms of the transparent, that color is defined, or color is the boundary of the transparent in a determinate body. But only when the transparent is in act, insofar as it is in act, can the colored object exist intentionally in the transparent. As for the second kind of light, light as it exists in its source, is what Aquinas calls lux. And since it is an active quality of its source, it is an accidental form. So it's a property of the heavenly body. So lux doesn't exist as a natural being in the transparent medium, but rather it exists there by power. And so this suggests we can think of lumen as the ontological boundary of lux as it exists virtually in the transparent medium. But this ontological boundary will be the act of the transparent that permeates the whole transparent medium. But for Aquinas, lux doesn't only actualize the transparent so that it can receive colored objects intentionally. Lux, as it exists by power in the sublunar realm, also plays a role in adducing substantial forms from the potency of matter. A reason lux is needed for this is that the elements of earth, air, fire, and water are rather limited in their natural powers. And so in order for bodies composed of mixtures of the elements to have powers beyond their powers of these four elements, there must be some principles present to composite bodies that actualize these higher powers. So this is what I take Aquinas to mean when he says in question 67 of the Prima Pars that light acts instrumentally by virtue of the heavenly bodies producing substantial forms. So this means that lumen, which is the act of the transparent insofar as it is transparent, does much more than just allowing colored objects to exist in it intentionally. Now, for those of you who have read my abstract for this talk, you will have noticed that I've said next to nothing about what I promised to do. So when I initially envisaged this talk, I had hoped to say more about how we might update Aquinas's understanding of hylomorphism and light for a modern scientific audience. So all I'm going to have time to do is just to note that physicists are always talking about systems, and we've heard several examples of this morning already, and light plays a central role in the transference of information from one system to another. Now, the fact that there is information in a system suggests that we might consider thinking of systems as kind of containers, thus echoing the notion of form found in Aquinas. Also, the etymology of the word information, coming as it does from the Latin word informare, meaning to shape, to give form to, or to delineate, suggests that there might still be an important role for light to play in an updated hylomorphic ontology. So in this talk, I've been trying to convey why my theological interests have motivated an interest in quantum physics, because both theologians and physicists speak about light, and sometimes in the same way. Their claims are not entirely independent of one another. And so there is some possibility for conflict. But I'm nevertheless confident that the truths of faith cannot contradict the truths of nature. And so if theologians and physicists are willing to talk to and understand one another, then I think such dialogue could greatly enrich both theology and physics. So thank you very much.
Robert, time for question. Yes, please.
Yeah, in the language of today, what would be the equivalent of the concept of form according to St. Thomas? Because at that time, it was not a well-defined mathematical description of reality and so on. Nowadays,
So, I mean, I am attracted to the idea of kind of understanding form in terms of, so when you have these kind of disentangled states, it seems that you can say something definite about one state independently of the other state. And so it seems like there is a kind of a place for seeing, that there are if you believe in that there's so in quantum physics you have all this kind of sort of entanglement going on, and it seems like in order to have an intelligible understanding of reality, where you actually can say something about part of reality without saying something about the whole of reality, there needs to be some kind of sort of ontological principle by which you can sort of disentangle reality. So it isn't just one huge entangled quantum mess. So that's kind of how I'm trying to envisage how form might play a role in an updated sort of quantum context. That's kind of what I'm thinking about. And I'm I mean, if I had more time, I would have gone into the interpretation of my PhD supervisor, Alexander Pruss, who has his traveling forms interpretation of quantum physics. So it's kind of like, it's a bit like the many worlds interpretation, except it's a one world interpretation, but you have all these kind of myriad of possibilities, and the forms tell you which of these possibilities is actual. And I'm also, there's another interpretation of quantum physics called, it's not very well known, by Adrian Kent, which is where you have it's in terms of the Schwinger sort of view of quantum physics, where you have quantum states over a kind of space-like surface, and then you have it's the variables on some far distant future hypersurface, and you do conditional expectations on at a particular point on the area outside the light cone of these points. And that kind of gives you a kind of one world interpretation of physics, which has all kind of nice properties that many world interpretations like things like Lorentz invariance. But it's a one world interpretation. What Kent says absolutely nothing about is why are the beables on this hypersurface these values rather than those values. And this is where I can kind of sort of see this notion of these principles of actuality, these principles of form, determining why reality is this way rather than that way. So that's kind of how I would try to update the notion of form, these principles of actuality that kind of, so they kind of limit it to sort of being this way rather than that way, rather than just a kind of a completely open realm of possibilities. So.
But these are accidental form you would envision?
Well, I mean, I guess it's kind of, yeah, I mean, I guess you you have to kind of
open question.
Yeah, it's kind of a question. This is we're getting into the details of it and trying to. I mean, but what I kind of how I'm seeing different in these kind of different answers is really trying to just open up the sort of the logical space so I don't want to sort of say that you have to like adopt to the sort of traveling forms interpretation or the Pence interpretation of quantum physics. It's more kind of questions like how do we know things? I mean, how do I believe that I'm actually seeing you now, rather than just sort of having kind of intuit that I'm seeing you and just having these kind of experiences. I want to kind of have a kind of realist sort of epistemology.
Sure. Very good.
A soul or a form. Is soul then for you is constitutive of a thing or a thing in itself?
Well, you can think about the soul as a thing in itself, because there are the soul you do have. After you die, the soul continues to exist.
Okay, so a thing of
forms,
natural forms.
Yes. Sorry.
A natural form, the constituent of the thing or a thing in itself. For Aquinas.
I think in the case thing is that the form it informs is the first act of life of living body. So, but I think when he talks about it, I think he talks about it as having because thing is even talks about it's not just informing a body, because it's got an intellectual operation. So, and that means that if the body ceases to exist, the form continues to exist in itself. And and he also, so I think, I mean, I guess it does sound like, he's saying that the talks about the powers of the soul. So, I mean, that's kind of like, he's talking about the powers that are present in the body, and also the intellectual faculty, which is not in the body. So it sounds like the soul is something that can exist in itself. Otherwise, when the body ceased to exist, the soul would cease to exist. So
let's just continue. So we give another chance for another question. Then we continue the discussion. The coffee break. Sorry, just yes. Yes. Sorry, we can do it later. Yeah, please go ahead.
Quick question. You want forms to explain the values of the hypersurface. Couldn't you do that with one cosmic form, a cosmic element?
Well, maybe. I mean, I guess. Yeah. I mean, you could. But I guess it's kind of like, can you talk about? You might be able to have one cosmic form, but I think you're trying to say something about part of reality without saying something about the whole of reality. And I think you want to. I mean, I think if you just said they're just one cosmic form, then that would kind of be sort of saying. It seems kind of absurd to say that. I think it's absurd to say that you can't know part of reality without that you have to know the whole of reality to know part of reality. And I think saying that there's just one cosmic form might sort of indicate that you didn't have to know the whole of reality to say something about part of reality.
All right, very good. This is great discussion. Thanks for the Robert. Everybody want some lunch, right? So we should we have like an hour? What do you think?
We go until 2, so we have plenty.
True. Yeah. So back at 2 p.m. Plenty of time. So more than an hour. Yeah, 2 hours. 2 p.m. All right. And there is lunch outside, right? So the lunch outside.
No.
I think. This cosmic, is it accidental?
Yeah.
Substantial.
Yeah.
Should deny the single identity.
Yeah.
It's more than the part, but it's not yet defining as, it's not substantial. That's what I would say.
Yeah. So I mean, but when you're saying that there's something definite there, that you can place upon definitely there, independent of the rest of the whole of reality. Then it means that thing has definitely and I'm saying that yeah. So you're coming.
I think there is a substantial form, although it doesn't define everything. Anyway, then you.
I agree.
Slide 7.
It's also, here have that,
When you speak.
so the soul is really two things. Yeah, it does on the body, so. That explains.
There is focus pantheism.
Gave us the talents. And also.
It has to be a form, like still keep it.
Like the soul, it's a life antidote to the past.
His identity.
Thank you so much. Yes. And so yeah, very, very interesting, and I can see quite a few parallels in some of the work that you're applying this concept of forms, boundaries, very broad topic. I worry that it's a little bit unconstrained.
Yeah. Well, I mean, this is why I guess you have to start going into
non-local interaction, but it's a single
actually kind of exploring. It's kind of what I mean, my kind of views is that in order for the way to work when you talk about there's some kind of limit which reality or doing the kind of like case of quantum physics. I think
describe them together, but visualize
and so in order to have a
in your
so when you can have like a thing that you can have definite description
so there is a dimension that depends on the
so that's why I think so it is what I'm trying to do is and I get this kind of when you talk about just like it's just like it's very hard to understand how
it's finished.
And so I want to extend it we are actually saying something
sure. So your particular focus is on this idea of I'll have to look more into this.
Yeah, well, I don't. The thing is, again. It's kind of opposite, but I guess kind of and I guess it is kind of like it kind
know how to
no, but it's always because it could give you the impression that and matter ways go together, whereas there's lots of examples where you have things without matter. And so, and this is still kind of part of the philosophy of yes. So you're, so I guess there was a kind of danger of thinking about as just
myself too.
Sure.
I need to be just into the bottom.
But it's kind of like it's a kind of language that we're stuck with.
So if you don't mind, so as an example of where my mind was going with this, so at the moment, one of my main projects I'm working on is you have some sort of you know, you have some sort of Feynman diagrams
say
of
you have
course,
Yeah,
and I'm taking a Green's function approach where, you know, you have external boundaries.
Yeah,
And
yeah,
that touches on like using a
yeah,
Green's
yeah,
function
yeah,
approach,
yeah,
and then
yeah,
and that
yeah,
you know
yeah.
that of course touches on some of
So what you measure
the
yeah,
topics
yeah,
that you were
not
talking
what
about.
was
But
before,
I don't know if that's really like really the type of
but
mapping
as a result of
this
the
idea of forms that you're really looking
Yeah,
for.
yeah,
That's an
yeah,
example.
no, I think that's kind of, I mean, I think like in quantum physics, you are kind of, you are talking about,
observing,
when you kind
are
of
coming
change
from
the
the
terms
observing
like
system.
cramps, it's sort of where you go from what you
Because
go, these are
otherwise
kind
you
of
can't
like
conserve
forms, which kind of, you know, when you have a form, you're kind of, you
And so then
start
once
off with
you
a
see
particular state,
that,
that's a kind of a
then you
limitation of
start
what it is, and then you kind of
focusing on the
work
observing
out,
system.
what are
you
the
do
kind of
that,
the realm of
You have to
possibilities,
treat that mechanically.
that
and
evolvement
look
state,
at
but then
Bell's
there's a actually
assumptions
happens,
in
and
his
so there's a kind of a
He assumes that the
until something actually
two
happens, you don't know what, you know, there's no kind of
which
measurement
means you
in
can
the
factorize
you
them.
end with a kind
But
of
you can't factorize them.
so I think just
And so therefore,
so I'm
the two detectors are
inclined to sort of think that in order to have a kind of
And if you consider
way
the
to avoid kind
all
of
possible
um,
quantum states that can
view
give
of
you the
reality, just having,
macroscopic
you know,
state,
you
it's gotta
have
have
a
the orientation
a
of
form
this
at the beginning and
and
a
the orientation
state
of
where you
this
start from, then a
as
form
part
at the
of
end.
the
And physics doesn't
specification
tell you
of
what the
the,
form at the end is going to be, but it kind of say what
which
it
is contrary
and so
to.
you say
Yeah, okay, no, I see.
so you're kind of, but you're kind of committing yourself. I mean, I guess you are committing yourself that
And that means it's all falls apart.
that measurements do actually happen.
Yeah, and you mean in a temporal sense.
Yeah, but also I'm I mean, also by finding
theorem,
not
the.
I mean,
I'm just
I'm
getting.
questioning
attracted to actually just trying to get more kind of representation of time, and this is kind of like, so when I talk about Kant's interpretation, you could actually kind of get a kind of a sort of partial being on
You're
this
presenting,
then something else.
I'm not presenting it all. Oh, you're not?
Okay.
I just.
Which could be kind of more kind of
You were having the
so
conference.
kind of into a kind of more representation of time as the time as the measure.
But I am trying to, I am just dipping my toes.
Kind of
Very interesting. I'll have to look into some of your writings.
I was doing
Yeah,
that.
I haven't been paying attention. I've got a doctor.
Oh, really?
Okay. Thank you.
My name is Ray Dawson. I'm a graduate student from
Yeah,
the
so-
Center for Statistics.
Okay.
I just want to say.
Thank you.
Right, so.
Sorry,
the thing that was
If I can ask, I was wondering what is said about the
detection,
how to update Aquinas'
measurement
theory of
as a
light.
quantum
in modern
process.
Yeah. I mean, that was kind of what I'm playing around.
Once you
whether
do
Alexander
that,
Press,
Right.
Which you have to do because of my
I
argument
know,
about
we come across Alexander
the
Press.
fact that,
I
you know,
I met him at the Institute.
from the measuring system.
And also he,
You've got to also do the measuring system and measurement.
what this physicist Adrian said.
There's a principle in medicine is
about
how you observe somebody.
interpretation, which has.
What you're observing, if they know you're observing this, if they don't know you're observing. Observing them, yes. So it does change.
But it's the same thing with any kind of sensation. I mean, sensation is a result of not only what we're sensing,
I was worrying
but also our
about
felt.
That's right.
how you work with like the
Do you have any
initial
other-
existence of light.
Yeah, so I have, so I have,
Sometimes.
but I think it's kind of like maybe how
That's
thinking
the
about
third one.
information and
Uh-oh.
system kind
Has
of.
one left.
I guess I haven't fleshed out, but it's kind of in the way that,
I haven't.
I mean, it's a way.
Okay, then
That,
don't worry about it.
that in a way.
It's like information carried.
Yeah.
I think you intentional existence.
Yeah. That I think it's sort of trying to have some kind of. That how something can be in another way, which is not that's the same as physics. And in a way, sometimes there's also a danger, you know, when you get physicists saying, you know, everything's information and everything's right. Go towards the other.
I was finding
I think it's
more
quite
thinking part of it.
Yeah.
Okay.
Quite a kind of middle.
Do you live?
But I guess that's
I live in Fontana, you know,
it's
where
sort of
that
like this,
I don't.
it's about 40 miles.
And really, I was thinking.
40 miles. Okay, so that's close.
Save light.
I live
that really does relate to the non-material. In other words,
Okay, you're right. Yeah,
oh, I understand this. It's not a
Just
physical
took
process.
me about an hour and
It's
15
that
to get
light of reason,
Yeah,
and
yeah,
the reason God says is that I'm the light, because He's the light. He's
Yeah,
both,
yeah,
you know, He
yeah,
created.
yeah,
Just
Thank you.
there's the material part of light,
Yeah, yeah,
and then
yeah,
there's the non-material part of light, which is thought. Yeah,
Yeah.
yeah. Yeah. So yeah,
Okay.
yeah.
So there's a lot of ambiguity about form. I think there's
Yeah,
at
yeah,
least
yeah, I don't, yeah.
3 different versions
Yeah,
of
yeah, yeah.
allomorphism.
Yeah, and I know, I mean, and I guess I there's some kind of version of hylomorphism that I think is pay lip service to a quite extent.
Yeah.
So I mean, I guess I kind of yeah, I mean, I guess the kind of definition that I gave, I think it's quite a very broad definition of thinking of form as a kind of ontological boundary.
I tend to go with Aristotle, what I think is Aristotle's
Yeah.
hylomorphism as opposed to Aquinas. I think Aquinas is Neoplatonic.
Oh, okay, yeah.
And Aristotle, I think, makes a division between natural and artificial processes. And hylomorphism in regard to artificial processes, it requires a artisan to impose form on matter. So, you know, making a vase or something. But the physis, which is a nature, Aristotle defines as movement from internal principles. And so both matter and form are physis. And so that means that matter, ule, is an internal principle which brings about change. Okay, so it's not a completely passive potency like prima materia.
Yeah. But I mean, it's good that, yeah, maybe it makes a difference between fine matter and.
And so the way I understand Aristotle is that we have an object here, say an acorn. I'm talking about natural objects now. Okay, so an acorn is an acorn and it has the form of an acorn and it has all of the first actuality of an acorn, that it can do acorn-like things. But it can also do something which will stop it from being an acorn and will make it into an oak tree. And that's its hule. So the hule is those natural tendencies within a thing that will make it something else. And so, but it's dynamic as opposed to purely passive as in Aquinas. And so I think that when we're talking about form, that we need to, be more specific about what it is that we're talking about, because and then the third interpretation is from Plato and Theaetetus, where he's got the abstract ideas that are being imposed in space as Cora, and they're basically like a signet ring impressing in wax. And so there's 3 different versions of allomorphism, at least.
Yeah. I mean, because I think Aristotle also talks about the wax as well, doesn't he?
I don't think I found him talking about
the wax. I think he talks about it sort of. It's more like when he talks about the senses and the form making it's like the medium and the.
Maybe in terms of sensation.
Yeah, but I think he does talk about
but not directly in terms of in this discussion of hule per se.
But I think, but anyway, but I think it's still I mean, I guess it's still I mean, maybe because I also think about maybe talking about the philosophy of nature just as hylomorphism kind of limits kind of what you say about the philosophy of nature, because there's the immaterial forms as well, and that doesn't really kind of capture so hylomorphism. I guess hylomorphism, because it's a 19th century word, which kind of narrows our kind of perception of Aquinas's.
Well, I mean, there's more to Aquinas than how.
Yeah. So, but somehow I think but also there's more to forms don't just inform matter, and
So I'll tell you about the basic
okay.
problem I had as a physicist
Okay.
studying scholastic philosophy at Loyola many
Yeah,
years ago in the
yeah,
'60s.
yeah.
And that was that hylomorphic philosophy of nature wants to put all of the intelligibility, well, all natural intelligibility into forms, individual specific forms that may be the same across species, but they're basically not universal. Whereas modern physics, starting from at least Newton and maybe before, wants to have universal laws of nature, which apply to all reality. And so one of my intellectual problems was kind of trying to reconcile those two ways of conceptualizing nature. So I think they are reconcilable, but I think that they involve different conceptual spaces.
Yeah. And I think maybe my interest is trying to make ontological space that you can talk about, because it seems like again, when I talk about billiard balls, I mean that's kind of when you have that kind of notion of these billiard balls following these sort of these deterministic laws, and it doesn't seem to have any kind of ontological space for talking about like substantial change, because things is just they're just changes of configurations.
Well, but
whereas
you have to think about levels of abstraction. Okay? In physics, we're concerned with inter alia. We're concerned with electrons and protons and neutrons. And it doesn't matter to a physicist whether they're sitting out in the middle of cosmic space or in the middle of some high-level organism. So therefore, biology, not therefore, but a biologist is focusing on the context, the physics is abstracted away. And so physics doesn't contain the information required to do biology because it's abstracted away by saying, I don't care about context. Okay, and so I don't think you can carry out the project of reductionism because all physics is going to tell you at most, which you're never going to find explicitly, is that this organism is possible. But it's not going to tell you that it's actual, and it's not going to tell you how it relates to other actual organisms.
I get you some food.
Okay, maybe.
I'd like to get you a plate of food.
Okay, that'd be good. That'd be great.
You want to continue the discussion?
Okay.
Have you had anything to eat?
No.
Okay.
I'll go on a little bit. So.
Okay.
But anyway, so I think paying attention to abstraction and what is abstracted away is very important in interfacing different disciplines, because different disciplines use different conceptual spaces, which are not necessarily contradictory, but they're not necessarily overlapping either.
Yes.
You better get some.
Where else the food?
Okay.
It's just outside, so.
Okay, thank you.
Yes. Just had a bit of a trouble getting here, so
You really should eat something. We can talk later.
Yes. And are you speaking? Is it tomorrow then?
I'm speaking this afternoon, actually.
And yes, I guess the Topoi book of essays, is that all going, the specialist, is that all going ahead now then, is it or?
Yes, have you been told that yours is?
Yeah, I mean, I saw a kind of a version which kind of still, I mean, it was kind of satisfactory. I mean, it had a kind of few kind of formatting errors, but it was.
I had that problem in mind. I found that no matter how many times I told them, I never got it where I wanted.
Yeah. So I mean, I guess I just signed the thing, and I guess I guess it's just mainly is the content, I guess.
So it should come down to some point, they're a bit unpredictable.
Yeah,
Annoying,
frankly.
frankly.
Very well. Yes. Right.
Good. So that's and quite a nice collection, I think.
Yeah. My first thing that I've had published in quite a long time. So yeah, yes.
Are you going to try and get something out on Adrian Kent's?
At some point, yeah, and I guess it's sort of trying to yes, get sort of balance all the other.
I thought it was going to be where we saw the.
Yeah. So anyway, I was kind of, yeah. Anyway, I guess one of my kind of reluctance to, I guess a bit kind of wary of just sort of spinning my, investing too much kind of sort of myself in a kind of when there's so many kind of different interpretations of the thing is I do like and I guess it's kind of like how because I guess I appreciate sometimes Ken's interpretation can sound a little bit this idea of vehicles on our distant hypersurface can sound extremely speculative and I wouldn't want people to sort of say
any world sounds extremely speculative.
Yeah. So I don't want people to sort of think that that high-levelism is even more speculative than it really isn't. But it's kind of, but maybe it's kind of more kind of just having these kind of toy examples where you can sort of explore the kind of questions about these kind of questions. But I got interested.
I'm being very bold today. Now, there's not time to give a presentation, but I am putting some.
Is this going to be like some of the work that you show me then?
This is going to be presented as a general schema, so not attached just to bowling mechanics, but generalizing PRW and CSO. So if you're sticking with optimistic mechanics, this is a way of being a halomorphist, and it doesn't conflict with what you're doing with a relativistic interpretation of mechanics. It's not confrontation. You can get some enough.
Well, we have to be careful what I say again. We'll say good things. We have been, for a few years now in sharing again in the same decide that is behind this and also collaborating. And so we are about to write some papers also. And Mark is a professor of philosophy at the University of St. Thomas in St. Paul, Minnesota. Here his PhD in philosophy at the State University of New York at Buffalo, and his BA and MA at the Franciscan University of Steubenville. So Mark was interested in this conference that you said because of the topics intersection with the overall project of synthesizing the best of contemporary thought with classical Catholic metaphysics, anthropology, and theology, and which has led him in the past to the question of how to metaphysically interpret quantum mechanics. So you did some work already in this direction, which actually was how I started to read one of your work, and there was. So he's excited to learn from others here about how to better affect this synthesis, and then outside academia he enjoyed hiking, camping with his wife, 5 children, so it's beautiful, and engaging in writing project with his wife, who is a theologian, editor, and a teacher. So you very good. So analogy, aesthetic method, and theories of quantum mechanics, freedom and providence. Mark, the floor is yours.
Thank you. Yes, it's great to be here. And I work on a lot of different things, and I feel like I'm kind of an outsider here. Philosophy of physics is just kind of a side thing I'm kind of interested in. So I'm happy to be corrected in anything I say here. I'm taking up a problem here. And it's a problem that came up in the morning's talks. It seems like currently available scientific evidence, currently available mathematical formalism is not sufficient to determine the correct epistemological or ontological interpretation of quantum mechanics. And so we have these different theories: Copenhagen interpretation, pilot wave, many worlds, hylomorphic theories, a range of theories. Some of these can overlap, some of them probably can't. But it seems like the currently available scientific evidence is just not enough to determine which of these is true. And what I want to do is propose, solution is too strong a word. I want to propose a method that maybe might be helpful here. A method drawing on recent philosophical and theological work, which might help push us in the direction of a correct interpretation of quantum mechanics. If you're interested in my work on this, I work out this method in much greater detail in my book, The Irreducibility of the Human Person, which came out from Catholic University of America Press 3 or 4 years ago. The method is what I call the analogical aesthetic method. And what we're going to try to do on this method is consider analogies among and perceivable wholes formed by first, interpretations of quantum mechanics, theories of free will, and theories of divine providence. So we're going to look at analogies among those theories, and then analogies among the experiences behind those theories and the realities to which those theories and experiences seem to point. And by looking at analogies between interpretations of quantum mechanics and theories of free will and divine providence, and then looking at experiential evidence regarding theories of free will and excluding certain theories that don't fit with the experiential evidence well, we might be able to reason by analogy to at least excluding certain interpretations of quantum mechanics. This talk's going to proceed in 2 steps. So first, I want to lay out this method, at least in sort of its bare bones. And then I want to apply that method to 3 sets of theories. The first 2 sets of theories I think don't work, and then the last one, a hylomorphic set of theories, I think has a better chance of working. And all that said, I'm much more confident about the method than about its application. So if anyone wants to tell me I'm totally wrong in how I applied the method, that's just fine. But I think the method has a lot to recommend. Okay, let's turn to that method. So I want to explain this method in 4 steps, looking at 4 thinkers who have developed pieces of this method of reasoning. And our first thinker is the Thomistic philosopher, early modern Thomistic philosopher Thomas Cajetan, who gives us, building on Thomas Aquinas, the idea of the analogy of proportionality. So Cajetan says that some concepts have analogical meanings. That is, we grasp their meanings not through a single, univocal, single meaning idea, but through interconnections among multiple terms. For example, if I want to know what the word sees or seeing means, I need to recognize that the concept seeing captures both the eye's act of visual awareness, as in I see you all right now, and also the mind's act of insight, right? As when I see that some theorem or some definition is true. So if I want to know what sees mean, I need to grasp that 4-term interconnection, right? As the eye is to its act of eyesight, direct visual awareness, so the mind is to its act of insight or direct intellectual awareness. And each of those acts, eyesight, mental sight, is only understood by its relation to the other. I'm not going to fully understand what's going on when I see you with my eyes, unless I also understand what's going on when I see something with my mind, and vice versa. The two pairs are mutually illuminating. And this idea of analogy is based, I think, in the experience that when relations among one set of ideas are structurally or formally similar to another set of ideas, those 2 sets of ideas are mutually illuminating. So we can find theories, for example, that are structurally or formally similar to one another. Each might be able to tell us something about the other. And then furthermore, we can check claims about one analogate, one side of this 4-term relation, by examining the other. For example, if we have good reason to accept a realist account of eyesight, that is an account on which by eyesight, as we heard in the last talk, we're aware of real objects, not just photons or retinal images or neural representations, that might be good reason to also accept a realist account of mental insight, as opposed to a purely idealist account on which, with my mind, I'm grasping realities. Second step, 20th century Thomistically influenced philosopher Eric Chavara. Chavara focuses on the idea that we find analogy not just in concepts, but in reality. So building on Cajetan's analogy, Chavara, among others, saw that the structure of reality shows up as analogical. Things are simultaneously similar to and different from one another. They have, in his technical terminology, an in and beyond structure. By grasping those conceptual analogies that we were talking about on the last slide, our minds are directed towards analogies that exist in reality. Formal similarities and differences at the level of concepts or theories point us to similarities in difference in reality. Take just one example with which Chavara starts off his book, Analogia Entes. Human consciousness, my consciousness, exists in itself. I'm directly aware in a first-person way of my identity and my awareness. But consciousness also exists beyond itself. It is intrinsically open to, intending of, and participating in extramental being, reality out there beyond my consciousness. Extramental being out there in reality, likewise exists in itself, but it also exists beyond itself in its intrinsic disposition to be taken up by consciousness. Each of these things, extramental being, consciousness, exists in itself, but also exists beyond itself in its intrinsic relation to the other pole there. This real analogical unity between being and consciousness grounds the conceptual experience that Cajetan was talking about. Each analogate, so eyesight, mental sight, or being, consciousness, extramental being, consciousness, each side of that analogy can, because of its real in and beyond structure, its real pointing towards the other, serve as a lens or an icon through which I am better aware of the other pole of the analogy. So by examining eyesight, I become better aware of how mental sight works. By examining mental insight, I become better aware of how eyesight works. By examining extramental being, I can grasp more about consciousness and vice versa. And now when analogates are analogically unified in this way, this kind of unity doesn't reduce the analogates to being mere parts of a larger whole. Analogical unity preserves the irreducible wholeness of each analogate. And Chavara's proposal is that all of reality is structured in this way. Third step. The Swiss theologian Hans-Urs von Balthasar takes up this analogical method, building upon Chavara and Cajetan, and he contends that we best see analogies by seeing them as forming a single gestalt, a single perceivable unity, which is not reducible to its parts, but only has its identity and meaning as a whole, and which does not reduce its parts to being mere aspects of that whole, but allows each part to have identity and meaning in its own right. So consider, for example, how we look at an artwork, say the famous icon of Christ. We perceive that artwork as a whole, and then we move to looking at the particular parts of it. The particular parts illumine something about the whole. We move back and forth between them. The parts of the icon only have their identity in relation to the whole, but each part also has its own identity in its own right. So by moving back and forth, we better grasp that whole analogical structure, the way that the parts and the whole exist in analogy to one another, and we better grasp each part in itself. And furthermore, it's only by perceiving things as having a place in whole perceivable gestalt, in these perceivable wholes, that we experience them as fully intelligible, meaningful, and understandable. A number of disjointed facts or things lacking such unity are not fully intelligible. It's only when we see things in their place in a larger whole, analogically related to that whole, that we fully grasp them as intelligible. Last thinker I want to mention, contemporary philosopher of science, Nicolas Thé, who teaches at the University of Notre Dame. He's proposed that something like this method helps us make sense of scientific models and theories. And he explains this in his book on the philosophy of symmetry by proposing that there's an analogy between scientific and artistic representations. When I look at a painting, I grasp the similarities and the differences between it and the subject which is being portrayed, like in this painting by Cézanne of a mountain in France. And I fully grasp the subject through the representation only insofar as I understand the process by which the artist translated the original into this medium. We grasp the subject in the depiction and in retracing the act of creating the portrait, but also beyond the picture, in reality. And ideally, we perceive this whole set of interrelations in a single complex act of sensory and intellectual perception. Now, similarly, Tabb proposes, a scientist builds up a model or representation of a physical system, like the formal mathematical representations involved in quantum mechanics, and we perceive that model as a meaningful whole, a meaningful gestalt, and through it, we perceive the reality that it portrays, and we do this especially when we grasp the process that the scientist engaged in to build up the model. A model exists in itself and beyond itself in relation to the reality it models. Furthermore, Tabb proposes the activity of painting is analogous to the activity of theoretical model building. The formal similarities between those two processes allow us to perceive how these two human activities exist in and beyond one another and how each illumines the other. I can better understand what scientists are doing by considering the similarities and differences between their activity and artists' activity and vice versa. Now, I think that this method of seeing theories as analogous to one another, seeing theories as analogous to the realities that they portray, and seeing all of these things as aspects of a single complex perceivable whole, allows us to think through interpretations of quantum mechanics in a distinctive way. So first, potential analogy. I want to draw an analogy between a version of the Copenhagen interpretation of quantum mechanics, certain theories of free will, and the theory of divine providence known as non-interventionist objective divine action. So on one version of the Copenhagen interpretation, the deterministic development of a quantum system represented by the wave function is treated as the best way to understand a system's development over time and to probabilistically predict its future states, as we heard about this morning. When a system is measured and seems to collapse indeterministically to one definite state, this is really just the acquisition through measurement of more information about the current state of the system. The scientist must distinguish aspects of reality describable in terms of classical physics, like aspects of measuring devices, and aspects of reality describable only by quantum mechanics, like the system when it's not being measured. Guided by the scientific activity of theorizing, we come to see reality as having indeterministic features and as being bifurcated into classical and quantum aspects. On this view, we cannot perceive or metaphysically know the real relation between those aspects, though we can probabilistically predict what will happen in experiments and observations. So we've got a deterministic development, we've got this indeterministic collapse, and the two are aspects of reality, but we don't exactly know or necessarily need to know the relation between them. Now, analogous to this interpretation, there's a family of views of free will, including some versions of views known as intellectualism and some versions of views known as event causal libertarianism, on which events of free choice are indeterministically related to prior reasons or events. So on these views, when I make a choice, my choice among alternatives is partly explained by the reasons I had in mind leading up to the choice. So I had reasons about like what to select at lunch. So there were those reasons. There were other events influencing me prior to the choice. Those reasons and events provide a range of possibilities for what I will choose, with some weightings as to the likelihood for choosing each particular possibility. And the production of my choice involves some indeterministic relation in this series of reasons or events. Those reasons or events are genuine but not sufficiently deterministic causes and explanations of my free choice. So there's a series of reasons and events, and then a choice happens. Structurally, formally very similar to the progression of the wave function, opening up a range of possibilities and then a collapse to a single possibility when the system is measured. So there's an analogy of proportionality, like what we saw in Cajetan, I think, between versions, the version of the Copenhagen interpretation that I described, and these views of free will. This conceptual analogy, in turn, points to an analogy in reality. Free choices and quantum state collapses are given in experience as analogous to these progressions of reasons and events and acts of free will. There's also a similar analogy to a view of divine providence, again known as non-interventionist objective divine action. Just as human free choice puts some physical systems into definite states, so on this proposal, God can intervene to put physical systems into definite states, and so providentially guide the world as he determines. So God allows events to progress, and then at various points, for example, in events of quantum state collapse, God intervenes to put the world into a definite state. So again, we have three views here on which we have progressions of events and then interventions or events which put the world into a definite state. I think there are significant problems with these views, which I'll turn to in a minute, but first I want to consider a second analogy. So a second analogy is an analogy between the pilot wave, the Bohmian mechanical view interpretation of quantum mechanics, and the theory of free will and divine providence known as the physical pre-motion view or Bayesianism. On at least one version of the pilot wave interpretation, although aspects of the development of a physical system over time are captured well by the wave function and the Schrödinger equation, there's another equation describing a hidden guiding or piloting wave moving through configuration space that determines the observable state of properties of the system at all times. There's no genuine randomness in the transition from the wave function to the apparently collapsed state, but just an observation of the always definite state of the system, though the behavior of the quantum system might appear random at times to an experimenter. The guiding equation determines the state of each property in the context not just of measurements or observations, but in the context of the whole universe. Indeed, on this view, the only real quantum system which develops over time in a fully determinate way is the whole universe. Analogous to this, I think, is the view of free will and divine providence known as the physical pre-motion view, or Bayesianism, after the early modern Thomist Domingo Banez. On this view, human persons have a power of free will, which is a power to act in a way grasped by, or power to act in a way guided by intellectually grasped reasons, so I understand reasons, and to act in a way that's not fully determined by any contingent cause, any cause in the physical world, or any actuality distinct from my power of free will. So this is a power that's open to alternative possibilities in its act. But every time I make a choice, God introduces into my will a property, a physical pre-motion, whereby he directs my will to act in some definite way. It causes me, actualizes me to perform, to move myself then to perform the free act that God in his providence wants me to make. Since God, as the being that is being itself, transcends and is the ultimate source of every kind of created being, power, or act, God can cause a human agent to perform some definite act of the will without threat to human freedom, according to the view. God can give free being and free acts. This is thus a theory of both human free will and divine providence. By the physical pre-motion, God can providentially direct all free acts exactly as he wills, and by those same pre-motions, human beings act as they will to act. So God moves me to move myself to act as I want to act. Now, again, I think that there is a clear analogy between these views. So as the wave function is to the guiding equation or the pilot wave, which ensures that the quantum system is in a definite state at all times, so the human power of will is to God's providential pre-motion. And I think we could even put these views together into a single view. It's a sort of Leibnizian parallelist view. God sets up the universe to develop according to the guiding function over time, and God moves human souls, human wills to act at certain definite times such that the two parallel one another exactly. And so we can get a single sort of gestalt, a single perceivable account of the world in which God is guiding all things that occur, guiding the world, the physical world through the pilot wave, guiding human free acts through physical pre-motions. Okay, so we've got two sets of analogies, right? One set of analogies between Copenhagen, these event causal theories of free will, and a non-interventionist account of divine providence. And on the other hand, an analogy between a version of the pilot wave view and physical pre-motion. And on the analogical method, when we've got these analogies set up, if we can critique one analogate within the overall analogy, that provides us with a lens by which we might be able to critique the other analogates. So if there's something wrong with a theory of free will, there might also be something wrong with the corresponding theory of quantum mechanics. So what I want to do here is briefly examine an account of the experience of free will. So this is a sort of phenomenological description, what's directly given in my experience when I make a free choice. So when I make a free choice, here are some things that seem to be given there. My acts of free choice, I experience them as influenced, but not determined by various external events or by the reasons I have in mind. So certainly those play some role in explaining why I choose what I choose, but they don't fully determine it. Second, when I make a free choice, and especially when I make a decisive free choice, like the choice to marry my wife, or the choice to assent to the creed, I experience those acts of free choice as mine alone. They are self-determined. I experience myself as responsible for them. When I make an act of free choice, I experience myself as possessing myself so that I can give myself. Right? I am in my own power such that I can bestow myself upon another person, a community, some cause or movement, an ideal. And I experience my acts of free choice not as random, not as indeterministic, but as fully intelligible and meaningful, even though they're not determined by the reasons I have in mind when I make the choice. My choices are experienced as meaningful, but with a meaning that I can only grasp from the first person point of view. Only I know, only I have direct access to why my act is fully meaningful. I can't convey that in words. Okay, so that's, and again, we can critique if you think that's wrong. If that doesn't match your experience of free choice, we can talk about that. So that's an account, a proposal of what the act of free choice is like. And so any theory of free will is going to need to accommodate that experience. Second experience that I think is relevant here is that experience that I've already described when I was describing the analogical method. Reality is given as a whole, intelligible gestalt, a unified, meaningful whole, with parts that are themselves whole, intelligible, meaningful gestalt. Now, if this account of our experience is right, certainly it's open to critique, but if this account of our experience is right, then neither of the accounts of free choice considered so far can be fully correct. Even though, through both analogies, we directly perceive acts of free choice to be analogous to quantum events. In the first analogy, free choices appear random and indeterministic, not fully intelligible in themselves. I have a bunch of reasons and events, and then suddenly a choice happens. But that's not how free choices directly give themselves an experience, as I've described here. Given that the account of free will in the first analogy is incorrect, or at least not fully correct, then if the analogical method I've proposed is a good method, then the version of the Copenhagen interpretation that was included in the first analogy can't be fully correct either. The apparent collapse event, the free choice, can't be a purely random event, but must be an intelligible event in itself, even if it's not deterministically related to or fully explained by the previous progression of the wave function. And I think also the first analogy also includes a serious unresolved tension. It presents the world both on the one hand as a unified, meaningful whole, and as having serious splits in it, like the split between the classical and quantum aspects of the world, or the split between the aspects of the world describable by the wave function and the collapse. So we've got both a unified view and a not unified view of the world, which violates this last experience. In the second analogy, the experience of my choices being entirely mine, entirely self-determined, are not fully recognized, not fully taken into account, since my choices are really determined by something other than me, whether that be the pilot wave or divine physical premotions or both. Again, I think this account is inconsistent with our basic experience of free will. And insofar as then that account of free will doesn't match our experience, by analogy, we have reason to reject the pilot wave interpretation of quantum mechanics. What we need, I think, and now turning to the final analogy, closing this paper, what's needed is a view of quantum mechanics, free will, and providence that fits with all our basic experiences of reality, our scientific experiences, our experiences of free choice, our experiences of reality as providentially guided, our experiences of reality as a perceivable and intelligible whole, and an account that leaves each part of reality as an irreducible whole that it appears to be. And we find that view, I think, in certain versions of hylomorphism and in certain views of God's primary causality, where God is the subsisting being that is the universal cause of created being. The hylomorphic interpretation of quantum mechanics that I want to propose, and here I'm developing the works of lots of other people, including people in this room, builds upon facts like that whole quantum systems have properties that are not reducible to or mere sums of the properties of their parts, or that entangled parts of quantum systems, even if spatially distant, act as a unity. So here's my proposal. We should think of, so on the hylomorphic view, things are unities of form and matter. Matter is impotential to being many ways. Form makes things actually some way. So I propose we should think of matter as quantitatively describable. For example, by the Schrödinger equation or other features of that mathematical formalism. The matter of a quantum system is impotential to a whole that includes it, but is greater than it. Physical substances are most fully explained not by their matter, but by their form, which gives meaning and actuality to the whole system. Substances are made out of matter that already has definite mathematical properties, but that matter is taken up into a substance and given a nature, actuality, and meaning by form. In virtue of form and its powers, substances sometimes develop over time in a deterministic manner, describable by the wave function. And at other times, they take on definite states of properties, again, in virtue of the form. In other words, substances sometimes determine themselves to let their matter develop on its own, and sometimes they determine themselves to be in definite states. At the level of our current best modeling of matter, the relation between these events looks indeterministic, but at the level of form, all is explainable in terms of the powers of the whole substance through their form, whereby they determine their own states. Form does not just interact with matter at the moment of wave function collapse, rather form and matter are always unified as act and potency in a single substance, which presents itself as a gestalt, an intelligible whole. And at all times, form explains what the matter is actually doing and what it actually is, even if sometimes form does this by letting matter develop in its own right. briefly now turning to the idea of free will. Free will is a power of human substances who intellectually, knowingly, and consciously determine, give themselves. And it's an aspect of my form. Why do I have free will? Because I have an intellectual form. An aspect of my self-determination that I carry out when I freely choose involves my form putting my matter into definite states to implement my choice. If I choose to extend my arm, my form puts my matter into definite position such that my arm is extended. On the view that I propose, by analogy, we can see all forms as doing something similar. Form puts the matter of their substances into definite states. We human persons carry out this self-determination and determination of matter in an intellectual, free way. Non-free, non-intellectual substances do not freely determine the states of their own matter. Nevertheless, I propose that they do something analogous to a free act, selecting among the probabilistically weighted states given by the matter and bestowing definite states upon them. And by the same analogy, we can think of a view of divine providence, on which God is the good primary cause of everything that exists and of every act, but does not determine what creatures, including free human persons, actually do. On this view, God, like form, bestows actuality, intelligibility, and meaning on all substances without determining what they do. Rather, God does this by letting them be and letting them act according to their nature. God thereby causes all of being and gives all things a place in the universal meaning of the cosmos. God is the primary cause of human free acts and all acts of self-determination, including apparent quantum collapse events, not by determining what they do or when they occur, but by bestowing being, actuality, and meaning upon them in an analogous way to how form bestows these properties on the matter of substances. And with this analogy, this hylomorphic analogy, understanding quantum collapse events through the lens of a particular view of free will, understanding divine providence through the lens of that account of free will, I think we have here an interpretation of quantum mechanics that better takes into account all the various aspects of experience, scientific experience, experience of freedom, religious experience, experience of the world as intelligible wholes, in a way that's better than the Copenhagen interpretation or the pilot wave view taken on their own. And I'll stop there.
You, Mark. Yes, please.
So Mark, thank you for this. A quick question for you about just a dual question. First of all, like you rightly said at the beginning, that Cajetan's notion of analogy is that you can't really understand what it means to have the concept like seeing, you know, mind and the way it interacts with its content, eye, how it interacts with its content. In looking at all these analogies, it doesn't, I'm wondering what the single concept is. So like when you're talking about like how we're making an analogy between like quantum mechanics and like form and matter, like is the single concept that we're looking to understand like non-caused free actions, and like I'm confused as to what the concept that's being analogized. And then the second, there's just to follow up on that also is, does that mean that we can't understand, nobody can understand quantum mechanics without this analogy?
Yeah, good. So I'm confident, I think, about an answer to the first question, and I'm not confident about an answer to the second question. So the first one, the Cajetanian thing about concepts is just like the first piece of developing this method. So Cajetan develops this idea of analogy in order to understand concepts like seeing or really like being. But then I think we can take that method of thinking about things analogically and apply it in lots of other contexts, such that we can see there are analogous, that is formally similar theories, which I don't think we could name a single concept that encompasses all of them.
There has to be something that's unifying the analogy.
Oh, sure. And that's where I think that the Gestalt piece comes in, right? So I perceive this unified whole. Do I have a word for that? I don't want to hazard a word right now. But I perceive that there is something structurally similar between how free will operates, how quantum systems operate, how God operates. I mean, ultimately, the concept here is being. The claim, though, is not that no one can understand quantum mechanics or free will or divine providence without the others. But the claim is, I think, that no one can fully understand these without the others. That is, we can't understand any one aspect of being except in its, ultimately and fully except in its relation to all other aspects of being. Actually, I am confident about that.
I guess this analogy help to understand, but the full understanding is still unreachable, I would say, no?
Oh, of course, yeah.
Anyway, so-
That's a sort of promissory note that I can't fully cash out, yeah. That no one can.
Yeah, so thanks a lot because it was, amazing. I think I fully agree with the problem with the second analogy, because if I understand it well, so we are dealing with superdeterminism. So we have no local hidden variables. The function itself is a problem with Bohmian mechanics. And that fits very well with a view about free will, which is compatibilism. So compatibilism says that everything is determined, but we are free. I don't buy that.
I don't
think
either.
It's inconsistent.
Yeah.
And I think that's fully incarnated by your second analogy. But I'm not so sure about your first analogy, because I think there's a more charitable view of the Copenhagen interpretation. In other words, I think you're asking too much about the Copenhagen interpretation. And randomness in science is fully compatible with free will. So Copenhagen interpretation is not saying that ontologically nature determines itself randomly. It's saying that, so randomness in science means independence between variables. So it's contextual, and it's epistemic. So maybe a more charitable view of Copenhagen interpretation is compatible with your theory of free will that I think I agree with.
Yeah, no, I mean, I think that's right. I think this is probably not fair. This is one very specific view of the Copenhagen interpretation that probably nobody actually holds.
I think we discussed this.
I think I mean, I want my view to include the best of these other views. Like, I think there's definitely a lot that's right about the Copenhagen interpretation. And I think there's probably a lot that's right about there's things that are captured on the Bohmian view that are probably right as well. That is, I'd like some sort of account of like the whole cosmos as a unity to be included in the best view. Yeah.
Van der Spitz was first, and then Steve, and then yes, Van der Spitz.
Just a quick methodological clarification. Thanks for the good presentation. But using analogy, I was just wondering, how would you get around this objection? Just because the notion of freedom is inadequate or incomplete or fails, it's not necessarily the case, like logically, if A, then B, not A.
Yeah.
But analogies don't work that way, because somebody could object, well, gee, that's maybe because the analogy was poorly done, maybe because analogy come out of my head, or that's because the analogy has all these dissimilarities, and the dissimilarities are the reason that there's not a good parallel between these things. So even if the freedom thing fails, why does the other, namely the quantum interpretation, why does that have to go down with it? Because maybe it's the disanalogous features that are causing, making it not parallel, not capable of having implicative power.
That's right. Yeah. No, I agree with that entirely. So this is why I say I think I'm confident in the method, and my application of it to these three analogies is very quick and hand wavy. We'd need to develop each of these analogies in much greater detail. Right. What we have here is sort of a program, sort of project, right? We need to draw out the exact analogies, find those versions, those theories of free will that are directly analogous to interpretations of quantum mechanics. And only when we get that precise analogy and it's spelled out in detail would we be able to engage in this reasoning. And even then, I agree, this is not a claim about logical entailment.
Yeah.
Right. This is a sort of argument by fittingness. Right. It's an aesthetic method. Right. I perceive in something like the way I perceive an artwork, or perceive a whole unity in nature. Right. I perceive the interrelation between these. So this gives me reasons to prefer some interpretation of quantum mechanics But not to say it's absolutely logical.
Very good. So one last quick question, Steve, but then I'm sorry, I cannot.
This is very quick. So it seems to me the more safe way to go about things generally is to use something that's better understood. To shed light on something that's less well understood and
Yes.
more mysterious.
Yes.
Now, it seems to me that the human mind has a better chance of understanding physical stuff than it does of understanding, say, the spiritual soul. And better chance of understanding the spiritual soul than it has of understanding the divine nature and divine development. So I think in trying to use a theory of divine providence, which is and of human free will, which are very mysterious things, to understand something as mundane, though itself mysterious to some extent as the physical world, is getting things backwards. I mean, you're using theories about what is more mysterious and sort of less proportionate to the human mind to shed light on something that is one would expect to be less mysterious and more proportionate to the human mind. Do you see what I'm saying?
Yeah. No, that's good. Yeah, so I mean, I think this is in some ways like the basic problem behind my project here, right? Is it relies upon a particular account of human experience, right? So I would just deny that I have better access to the material world than I do to the contents of my own mind. That is, I think I directly know what it's like to engage in free acts, and I only have indirect access, or I have less direct access to the sensory world out there. So I think, I mean, one big problem with my whole project here is it's a debate about the basic structure of human experience and what we know better. And yeah, if your account of what we know better is right, then yeah, this is the wrong way to go about doing things. If my account is the right way of what we know better is right, then this might be the right way about going about things. Thank you, though.
Speaker is Father Ambrose Lito. No, we are doing the second talk, so we are all full of energy. There's no ready to go. No, there is we after this talk. So we do 2 and 2. Yeah.
So first of all, which internet?
So you're going to join this was Daniel, I think a good point. Chapman. See, that's what we need to work together on this. There was one talk, they copied and then 3 talks.
Where is the Zoom?
So it was better.
Is that get sent to?
You're just gonna
right there.
Zoom.
Maybe so maybe you take another question while we set up.
Okay, another question. You have a question. Okay. Oh, sorry. Who was first? I can't remember. You have it.
Oh, great.
Okay.
On my
That's how I led the.
I agree with what Mark said.
Mark,
Gonna have to break behind.
I cannot, there's a question for more question.
Yeah.
I agree with much of what you said, but it seems to me that the reason that Cajetan's analogy of proportionality works with essence and existence is that you have the same dynamic in each instance.
Yes.
And so the motivation for me, at least, to accept a method like this is that the dynamic on the right is a reflection of the dynamic on the left.
Yes.
But that's not what is being shown. What's being shown is that the blocks are analogous. And so it seems to me, method leaves open the possibility for you projecting your own interpretation into the conclusion, because you're saying, okay, this is going to be the same as that, but you haven't really shown that the dynamics of this is the same as the dynamics of that.
Yeah, so it's like Father Spitzer was saying, there might be significant disanalogies. And this is really just the sort of outline for a research project. You would need to really show the formal similarities and the dynamic similarities between the different analogies. I think that's right.
Yeah. Okay.
On that same vein of finding the similarities and
Yeah.
dissimilarities, it occurred to me that on your analogy 1, you had
Lena will take care of
something about the deterministic development of wave function, and then the wave function overlap. And on your 3rd block, you had something about previous events prior to divine action, and then divine action.
Some is used, or God is punctually
Now,
intervening.
have you considered, and maybe you already addressed this in your book or plan too, that in the one case, the wave function, while it does not determine the outcome of the collapse, it does somewhat constrain through like the probabilistically, but
Okay,
that analogy would say.
So we are ready to go. Conversation topics.
Yeah, no,
let's So I'm very pleased to have here also Father Ambrose Little. We've been known for the past several years and interact quite a bit. So Father Ambrose is at the Dominican House of Studies, and I think the last year you're the director from the Domestic Institute. So you have a bachelor licentiate at the Catholic University of America. The doctorate is at the University of Virginia in philosophy. And he's very interested in bringing together Aristotelian, Thomistic, natural philosophy to develop better scientific models. So that's the perfect place to be. And looking forward for your talk, act, potency, and quantum indeterminacy. Looking forward to it. Thank you, John.
All right, so first, just to begin by thanking all the organizers for this. This is an interesting event, and I've been looking for a place to kind of to present this particular development that a couple of us have been working on. And I say a couple of us because this is not just my work, but this is very much work that is dependent upon kind of a group discussion, especially with one of our student brothers, Brother Cashin Iozzo, who has a PhD in physics from Cornell and is a budding philosopher. He and I worked very closely on the theory that I'm about to present to you. And we also relied a lot on the help of Jonathan Lunin, the scientist for the Jet Propulsion Laboratory. So the three of us kind of work together on this. I depend on them for most of the actual science. So I can explain some of the science, our views on the science, but there might come a point where I'm going to run up against a wall. So I apologize about that ahead of time. And I'm only able to give you a very, very brief glimpse of what we're doing here. But for the purposes of today, I'm going to be outlining the principles and commitments of the proposal and give an example for how this Thomistic proposal can solve, or at least hint at a way we can solve a number of open questions related to quantum indeterminacy. And now I'm proposing this also as a new quantum, a new Thomistic proposal, not as if it's completely new out of the box, but I'm developing it as a new interpretation, but that's relied upon other people like Robert Koons, Ryan Miller, or Ed Fazer, or William Simpson. So our proposal builds on that existing framework, but offers a new way to incorporate quantum indeterminacy into natural philosophy. And we can identify the specific novelty of our proposal after we've laid down some groundwork. So to begin, what makes this a Thomistic proposal in particular? It is a Thomistic proposal because we are applying a robust understanding of the real distinction between act and potency, as well as a Thomistic notion of change to the concept of quantum indeterminacy. Now, what is the real distinction between act and potency, you say? To put it simply, Thomists, following Aristotle, think that the verb to be, to exist, to be, to have being, has multiple irreducible meanings. In other words, there are many ways to be. And so one of the ways in which Aristotle and Thomists will say that there are many ways to be are the 10 categories. You can be as a substance, you can be a quantity, you can be a quality, you can have a relation, etc. There are 10 of these. All of these are distinct ways of being. They're related ways of being as well, but they are distinct ways that something exists. Now, along with these 10 categories, we said that each category of being, something can exist in that category being also in two really distinct ways. That is, something can exist actually as such, and as potentially as such. And that these actual ways of existing and potential ways of existing are really distinct ways of existing and can be true properties of the things that we're talking about. So take, for example, take, for example, a log of like a piece of wood, right? You have a log, and I want to describe it. I'm going to describe all the properties of the piece of wood. Now I can describe certain actual properties of it. I can say that this piece of wood is 3 pounds in weight. It's a certain type of shade of brown. It's cylindrical, right? It lies lengthwise on the ground, etc. But then I can talk about different other properties of the log. I can say that the log is combustible. The log is choppable. The log is something that I can stand upright. So these are all real properties of the log, but some of them we'd say are actual properties and others are potential properties. Now, probably the easiest way to understand the actual properties of the log, that it is 3 pounds, that it has these certain shades of color, that it is cylindrical, these describe the way that a thing exists in its simple present sense, in its most simple sense. But then the potential properties are real ways in which this log can undergo change. So we can say the log can combust, but is not combusting at the moment. It's not on fire at the moment. But here's something that the log is not in potency to be. The log is not in potency to be turned immediately into a liquid, right? You have to basically change it a couple different ways before you can then turn it into a liquid state, right? So it has the potency to be put on fire, but it doesn't have the potency to become a pool of water. So these are the potential properties are real ways that this particular object, namely the log, exists and describes ways it can undergo change. And these are different ways of existing than the actual ways of existing, that it is 3 pounds, that it is lying on the ground in a particular way, et cetera, et cetera. Now, there's a lot more to go through here. I teach an entire class, several class sections on this, but I would say we have some good videos on this on our Aquinas 101 videos. So if you are interested, we'll look up Aquinas 101 and our video on act and potency. Okay, now we can ask, well, wait a minute. Why do we really need these different ways of existing? Why did Aristotle and St. Thomas use this complicated philosophical framework to talk about reality? Well, the answer is they need it to answer the question of what does it mean to change? So Aristotle has this very long discussion about how to even begin to understand the concept of change. And it turns out you need these different modes of existing in order to understand why one thing can become another, or why one thing can go out of existence, or why one thing can come into existence. So when I say that this log is something that can be on fire, and then when I light it on fire, it's now on fire, I can talk about how this one thing, the log, was not on fire and is now on fire. And in order to discuss that, we need to be able to talk about potency and act, and we need to also be able to talk about the different types of the 10 categories of change. And now when we look at change for Aristotle, right, we want to say that change always is a movement from not being something to being something, or from being something to not being something. And this requires potency to undergo the change, and an actuality that is either gained or lost. Again, there's more to talk about here, but these are all the types. These are some basic concepts that are required or helpful for understanding the concept of change in general. Now, in Aristotle, all physical change involves an interaction between two things, right? So in traditional understandings of Aristotle as it's received into the historiography of science, people will say that for Aristotle, everything requires a push or a pull, right? But really the way that I think the easier way of describing it is for any change on the natural level, there have to be two things where one thing loses a form and gains a form, and another thing loses a form and gains a form. And that one change involves two different exchanges or an interaction between things. All right. Now, in saying that, I'm excluding certain types of natural change. So I'm excluding certain types of natural change that are appropriate to living things like plants or our ability to perceive. I think that's necessary. I think that's actually irrelevant to what we're going to be describing in quantum indeterminacy and the observer paradox. So here, I'm just going to be focusing on the most basic characteristics of change in Aristotle, which is a physical change that requires an interaction between at least two things, but not simply two things, where there is a loss of an actuality and a gain of an actuality in all of the things that are undergoing the change or involved in the change. All right, so now among the categories of being, there is substance, there's quantity, there's quality, and then there's a category of being that we call relation. Some properties of a thing are relative to other things, and that these properties come into existence only in relation to those other things. So for instance, the velocity of an object is defined in relation to something else. This concept should be recognizable from Einstein's theory of relativity. Now, since all being can be distinguished into act and potency, all relations are also either actual or potential. So the properties based on these relations are either actual relations or potential relations. When a relation is actual, it has an actual existence. It has an actual existence that is necessarily dependent upon two or more things. So take, for example, individuals A and B, as I have here up on the slide, and the relation R that is between them. So this can be formalized, as you see there on the screen, R, parentheses, A, comma, B, and close parentheses. So R really describes an actual way that A and B exist. And R does not actually exist except in the way that A relates to B. Now, potential relations are slightly different, but they describe properties of individuals that permit that individual to enter into a relation with other individuals. So take an individual A and a variable X, which ranges over the possible individuals to which A can relate. And the relation R describes those potential relations. So then again, this is formalized as the relation R, open parentheses, A, comma, variable X, close parentheses. So here, R is principally a property of A and nothing else, because X is simply a variable. So as a facile example here, let's say that R is the relation of electrostatic attraction. Then A can be a positive charge and B can be a negative charge. Now, RAB would be the relation between two actually existing charges that attract each other. If we only had one charge, then RAX would describe the potency for a positive charge to attract a negative charge if one were actually to appear. Although the positive charge A is not actually attracting any other charge at the moment, it still has the real potency to do so. Okay, so now there are two kinds of real relations that are of interest to our study, each of which can exist in act or in potency. So now we'll look at two of these real relations. One are physical relations, the other are quantitative relations. So a thing is the subject of a physical relation if it acts on something else or is acted upon by something else. So if it acts on something else, we call it an agent. If it is acted upon by something else, it is called a patient. In a mutual interaction, one and the same thing can be both an agent insofar as it has an effect on something else, and a patient insofar as it is affected by something else. So in physical relations, right, there is truly an act upon and something that acts upon another and something that receives the act of another. Right. A quantitative relation exists when there is any kind of real proportion between two things. So for example, if we establish a certain length as a basis for measurement, then there is a real relationship between the physical thing that sets the basis for the measurement, say an iron bar in the city of Paris, and the thing that is measured according to that basis. There is a quantitative relation between a meter stick and a boat's length measured at 10 meters. The fact that quantitative relations are real relations is what then allows for, say, gauge fixing and predictability in mathematical models. Now, properties of a thing can also be intrinsic and extrinsic. And actually, we see St. Thomas do this with the 10 categories of being. St. Thomas will interpret the 10 Aristotelian categories of being as saying that some of those categories are intrinsic properties and others are extrinsic properties. So an intrinsic property is something that is inherent to the thing itself. So a thing has an intrinsic property simply because of the kind of thing that it is. These flow from their essences or properties that subsist in the subject themselves. So for example, iron has the property that it can be permanently magnetized, but copper has the property that it can never be permanently magnetized. So these are intrinsic properties to these different metals. Then you have extrinsic properties. Extrinsic properties depend on a thing's relations. So a thing has an extrinsic property because of the actual relations that it has with something else. So for example, the linear momentum of a bowling ball depends on its relation to other things. A bowling ball does not have an intrinsic linear momentum. Now consider the potential physical relations that belong to anything. These are based on the potencies of that thing for acting upon something else in a certain way. That is, its potency for action. Or it also has a potency based on being acted upon by something else in a certain way. This would be its potency for a passion. So the potential physical relations are dependent upon, but distinct from, the potencies for action and passion. When the action or passion is actualized, the physical relation is also necessarily actualized. The set of potential physical relations of a thing are real properties of that thing, only because they are grounded in the potential ways that that thing can be acted upon or can act upon others. So because the potential properties only really describe the individual and nothing outside of it, we can call these intrinsic potential properties. That is, these are potential properties that are inherent to the thing itself because of the kind of thing that it is. Now, for example, whether an electron is spin up or spin down is not defined until it interacts with a Stern-Gerlach magnet. So the property of spin directionality, either up or down, is something that we might think of as an extrinsic property of an electron. However, because we know that an electron will always interact as spin equals 1/2 particle, there's an intrinsic way in which we know it will go in one direction or another, right? So the very concept of spin in quantum mechanics is based on the interaction with other particles. Yet the fact remains that an electron always has an intrinsic spin by which we understand how it could potentially interact with other things. So the intrinsic spin in an electron is an intrinsic potential property, and the spin directionality as measured by an experimental apparatus is an extrinsic property of the electron. We now proceed to apply some of these key concepts to build up a atomistic understanding of quantum indeterminacy and measurement or observation. So a note about our use of the term observation. Of course, in standard English, observation implies an intelligent agent as an observer. It also implies that the observer is not influencing the observation. But in quantum theory, due to quantum indeterminacy, the observer does influence and change the thing or bring about the event by an observation. So whenever you observe, you change something in it. This is because an observation requires an interaction with the system in some way. Therefore, one of our key kind of commitments is that every observation causes a change. So in our proposal, the observer is anything or event that interacts with a quantum phenomenon, whether it is an intelligent being or not. The act of observation does not require a conscious or self-aware subject. And in fact, we can prescind from observation as an intellectual act for now and just consider all observations in terms of interactions. Okay, so now we're in a position to discuss the novelty of this proposal. The previous Thomistic interpretations of quantum mechanics located quantum indeterminacy in the properties of the particles themselves. Our proposal is to make a distinction between intrinsic and extrinsic properties of particles so that we can locate quantum indeterminacy only in the extrinsic properties of the particle themselves. So the relations between the particles. The intrinsic properties are not subject to quantum indeterminacy. So let's see how this works and what the consequences are. As we will see, this proposal will share features of both the Copenhagen interpretation and an interpretation called relational quantum mechanics, without falling into either camp. Now remember that whenever a change occurs, some potency is changed into act. For this to happen, there must be a physical relation or an interaction between the two things. In an interaction between two things, there are some potencies that then become actualized. And so with that, we can then apply this act potency framework at the quantum scale. It becomes especially apparent at the quantum scale that every measurement or observation is an interaction and therefore involves a physical relation. Every measurement of a thing actualizes some potency of that thing, and extrinsic properties are then derived from the kind of actual being that results in this physical relation. Since potency is a real mode of being, we can see that the intrinsic potential properties of a thing are real and determinative without them having to be actualized prior to an interaction. So for example, an electron before any measurement has the intrinsic potential property of intrinsic spin, which is the set of potential relations that it could have as a particle that could potentially spin in one direction or another. When the electron spin is then measured, there is an interaction that establishes an actual physical relation. In most cases with a magnet. The extrinsic property of the electron's spin directionality is then an actual property of that electron. From a physical relation, we are then able to abstract a quantitative relation. Thus, we have to distinguish between measurement as the action of measuring, that is the interaction that takes place, and measurement as the process of abstraction by which we obtain quantitative understanding of the interaction. All right. Quantum indeterminacy. So for everything we normally encounter, a single potency is determined to a single act. In other words, we can expect identical causes to have identical effects. However, not all potencies have to be determined to a single actualization. Bell's theorem suggests that when the scale of an interaction is comparable to the de Broglie wavelength of the interacting objects, there are potencies that are determined to different acts according to a probability distribution. This coincides with our Thomistic framework in this way. An electron need not have an actual spin direction prior to measurement, yet it still has the real intrinsic potential property that is determinative only to the extent that the electron should interact with the spin in some direction. The potency is not determined to be specifically spin up or spin down before the interaction. That actualization only occurs when the physical relation is established by the measuring interaction. With this understanding, we can then make sense of the collapse of the wave function in the Copenhagen interpretation. A mathematical model, of course, is a quantitative abstraction of a physical phenomenon. The wave function is a quantitative description of the different potencies that could be actualized. So the collapse of the wave function describes the actualization of those potencies to one actual extrinsic property. And so just to reiterate, because the potential being of a thing is a real mode of being, the wave function is describing something real about a quantum system even before an interaction. It is just not describing an actual property, but only a potential real property of that system. Okay, so then what follows is a central consequence of the novelty of our proposal. Some actual properties are mutually exclusive. One electron cannot be measured in two locations at the same time. However, a thing can have multiple potential properties simultaneously. But since only one is actualized at a given time, we do not run into logical contradictions. So superposition describes the different intrinsic potential properties prior to actualization. As we said earlier, actualization occurs by an interaction which is a real physical relation. However, a physical relation is only actual between the things actually participating in that relation. The potency is really actualized between two things in a physical relation, but both of those things remain in potency to some third thing that has not yet established a real relation. So if superposition is a description of an intrinsic potential property, then that intrinsic potential property is only actualized as an extrinsic property between the two things that are in relation. The superposition remains for some third thing that has not yet been involved in the interaction at all. With this understanding, then, superposition is relative, not absolute and universal. And so this is where our proposal diverges from previous Thomistic interpretations. Whether or not the wave function has collapsed is relative to different observers, depending on whether or not they have interacted with the system in question. So to flesh this idea out, consider three isolated systems, A, B, and C. Let A have some intrinsic potential property, for example, spin directionality, that is in superposition with respect to B and C. If B interacts with A, then there is a physical relation established between them, and A now has an extrinsic property, for example, spin up with respect to B. However, A and its intrinsic potential property still remains in superposition with respect to C. If C does not maintain a real relation with B after B's interaction with A, then not only is A in superposition with respect to C, but the entire AB system is now in superposition with respect to C. For example, C may know that the AB system is spin aligned, but it doesn't know whether it's spin up or spin down. Thus, we never actualize an extrinsic property absolutely and universally, but only relatively. From a quantitative perspective, we never collapse the wave function universally and absolutely for every observer. Just as there is no absolute and universal frame in relativity, so too there is no absolute and universal laboratory with respect to a thing's extrinsic properties when they're being actualized. And a big advantage to this idea is that we can explain an entanglement phenomenon without having to appeal to unmediated distance action at a distance. With this framework, quantum entanglement and entanglement swapping are not unexpected and surprising phenomena. On the contrary, these phenomena become more fundamental and expansive. Each measurement is the result of an interaction, that is, a real relation that itself actualizes extrinsic properties. This means the measurer and the measured become entangled with respect to another isolated system. Not only does an observer influence everything they are trying to measure, but the fact that there is no absolute laboratory means that we can never step outside the universe and consider it from the so-called God's eye perspective. Regardless of how wide the entanglement network grows, within which an extrinsic property is actualized, we can always consider yet another observer outside the network, for whom the network would be in superposition. So to take an image from Thomas Hertog and Stephen Hawking, rather than seeing our understanding of the universe as if we were standing outside it, we have the perspective of a worm inside the apple and part of the apple that it is trying to study. And its own exploration of the apple changes the apple. Okay. So the fear might arise that the order of the universe would lose its unity and integrity as networks of superposition seem to isolate from each other. Indeed, this is what pure relational quantum mechanics would seem to suggest. However, our proposal avoids this in two ways. First, in the real world, the sheer complexity of interactions, just to think of the number of photons flying around in this room, means that it would take a careful experimental setup to isolate a small system that remains in superposition with respect to everything else. As we know from experiment, carrying out entanglement experiments is hard because it is hard to prevent particles from interacting. Second, even though we might have a macro scale system in superposition relative to another observer, we would normally not expect to see interference phenomena due to the due to the relatively vanishing de Broglie wavelength. However, we can revisit the classic Schrodinger's cat thought experiment for an example of how a macro system could be set up to exhibit a significant difference between two possible actualizations. Within the box, the cat itself is either dead or alive. Its property as living or non-living is actual as soon as it interacts with the chemical, which interacts with the tripwire, which interacts with the radiation detector, which interacts with the radioactive particle in superposition. However, outside the box, we would affirm that the cat is in superposition of being dead and alive. Superposition is a description of an extrinsic property. So the superposition is not whether the cat is dead or alive in itself, but how the entire box system interacts with an outside observer. And this is key. What is in superposition is not so much the reality inside the box, but rather all the ways the box system can interact with the world. Thus, the cat as alive with respect to the outside observer or dead with respect to the outside observer is what is in superposition. We can compare this simple example we can compare this to a simple example in special relativity, where whether a ladder has the property of fitting into the barn depends on the ladder's length in itself, the barn's length in itself, and their physical relation with each other based on their relative velocity. The question is not whether the ladder's length in itself changes or whether the barn's length in itself changes. The question is about all the ways they could interact. So just as relative velocity, an extrinsic property, relates to how the ladder's intrinsic properties interact with the barn's intrinsic properties, so in quantum mechanics, the state of superposition is about the extrinsic properties of systems that describe how the intrinsic properties relate. So to conclude, there's obviously more to say here to develop, but for those already familiar with the previous atomistic interpretations, the key distinction that we submit for your consideration is whether quantum indeterminacy only applies to extrinsic properties, our proposal, or whether it applies both to intrinsic and extrinsic properties. If it only applies to extrinsic properties, we get a relativity of superposition. If it applies also to intrinsic properties, then we run back into the difficulty of trying to explain the whole suite of entanglement phenomena. But we think that if this proposal is correct, we can apply this interpretation not just to the micro scale, but to the macro scale. Such a model could form the basis of a relativistic quantum mechanics that could provide a framework for interpreting a solution for quantum gravity. So, thank you for your time.
One or two questions. So just first Paul and then Spitzer.
Well, thanks for your talk. I published a paper in 2019 entitled The Einstein-Podolsky-Rosen Paradox and SU2 Relativity. And it's very close to, I give a mathematical structure, I hope, to what you're saying. And in that sense, you need to also be very clear that entanglement, in that sense, it's an emerging property. So that you could call it intrinsic, but it's the only way I think you can handle is Trulonic and higher viewpoints. Otherwise, I don't see how you cannot fall back into hidden parameters. That's all I'm saying. But I do tackle the whole point and called SU2 relativity, which is a group structure which has a relative effect. It's analogous to the SO1 group of special relativity, but it works specifically for entanglement.
Very nice comment that we can discuss in the break. Father Spitzer,
Yeah, just very quickly, thank you for an ingenious proposal. Just two quick questions. The first thing is, if entanglement doesn't have unmediated action at a distance, doesn't imply it, then there must be some mediated action at a distance. And I'm trying to figure out, what are you saying the mediation is?
The mediation is the interaction of the observer with the system itself. So for instance, there are going to be objects that are far away in the system, say that you wouldn't necessarily interact with. So say you have like a system as large as like the galaxy, right? Like, and there's a way in which we're interacting with something at the other end of the galaxy. There's no way I would individually interact with that object. But if I have a way, I might have a way to calculate about that object if I interact with something that is also already within that system, even though there's a mediation of the interaction with the whole system itself.
And just a second clarification, just on relativity. It sounds like when you say in itself, that it doesn't, that the ladder has a length in itself. It's almost like length contraction, duration dilation are not real. It's like it still maintains this in itself length. How can you give a measurement and in itself, as it were.
Well, remember, for measurement is always when you take one object and measure and apply it to another, right? So like when the measured number, as St. Thomas refers to it, is this kind of relative quantified nature of things. So, but then there is this intrinsic property of it, namely that it has length or that it has diameter, that then we apply this unit of measurement to it. So then according to time dilation, right, the objects will be smaller in relationship to others based on the difference of velocity.
But not in itself.
But not because the velocity changes the relative positions towards it. I think that it's based in the properties it has in itself, or changed by the velocity.
I want to take a look at that in itself notion. Might not correspond to observable evidence, but I'm not sure.
Okay.
I understand.
Okay, so let's conclude this section. Stop at 3:45, right? Yeah. 15 minutes. 3:45.
University space, so it's a
Satisfying the relation on one.
But it's like. Fidelity is supposed to have maybe like a formality.
very.
They're analogous to each other.
No, that's
Perceive the reality of
No thought and anything.
And maybe like a little question that analogy.
That, yeah, so like I.
being, yeah.
Metaphor.
Yeah.
Now, it is. And that conflict observer has anything.
Yeah, we need it.
I just think it's because they should know.
Ingenious proposal.
Yeah, I was. I had similar.
But my question is.
I was thinking about someone.
Yeah.
Well.
Big fan.
Well, so like, so for instance, when the Copenhagen, when certain versions of the Copenhagen interpretation just insist like the cat is down at the same time before we observe, right? So that's basically interpreting that the property of it being dead or alive based on the quantum state is talking about actual property of the cat. So because they can't make a distinction between act and potency, they just make all free distinctions of this state just is in both of these different versions of the same.
Yeah, but that's like. There's a question about like what's the analysis? Right. Oh, well, yeah. I think I kind of agree. I think I know.
Yeah, I agree with you about that.
But I think that's the same.
Yeah.
In some views, like the argument is about the most aware of the world, at least aware.
Yes.
It's quantifying over the potential state, but then we might say though, like there is this system of the cat in the box itself. All have actual realities, right? So like the observer outside the box hasn't interacted with him, so there's no the observer outside the box cannot calculate or figure out the liveness or deadness. It's not, and in some ways it's not just an epistemological thing. Until you enter into a relationship with it, you can't actually make a determination about it.
Well, that's epistemological.
Well,
you can't make a determination. True enough.
But it's there's also a metaphysical reality because the only way you can have access to the physical reality is by being first to have that physical action. Like there is the epistemology, I can't know it, and it's also based in the physical reality that I have not yet interacted with.
It only mean actual. when you say that the common interpretation.
Yeah.
Only
action properties.
I don't.
No, I think it only applies, I don't think the interpretation has to be applied. So that's one of the things that we're adding to that.
But I mean, I love it, but I think it's like. It's so much.
So yeah, so that's where we're at right now.
Weird stuff, and even bad. Like.
Okay, so that's okay.
Yes.
Yeah, half an hour. Get that accreditation, some expansion.
Yeah, I agree.
Yeah.
No. I mean, I have a lot of what I've done written down, but I mean, I'm just giving presentations on this at the moment because I don't have anything to do.
Say electrical property.
Half an hour and they show off quantity.
Yeah.
Early, you'll be celebrating.
According to Aristotle and Delta, quantity is a potential property because it says quantity is three different numeral and if it is measurable. Both of those is requiring an operation to actualize. Okay, and so your properties over here, which are these. They're not actually, they're potential properties.
Well, they're potential properties until you have the interaction.
Until you measure them.
So when Aristotle talks about discrete and continuous modes of being, right? So the discrete is numerable, the continuous is divisible. Like what measure. It's like those are like but I think about the real that it is say where it is discrete.
It doesn't have a number yet.
Yes, because then you have then to get the measured numbers, you actually apply the measurement and then that
the measurement is interaction. And the interaction is going to change the result.
Yes.
And so the numbers you get and be not described before applied process. Because it's not a maximum property, it's a potential property.
Oh, no, but it is actualized once it's measured.
Actualized once it's measured,
Yeah.
it's still.
So I just clarify that, that's what we were intending.
So it is one.
I like it.
Oh, it was years ago.
Well, so I do think that the act of measuring does change the things to be interactive.
Yeah.
So, and that's part of it. So like, what is it that makes the electrical spin up, spin down? Once it interacts with the magnet, it goes up, right? Or it goes down, right? So like, there is a way in which to interact, or like, if you think about the famous double slit experiment, right? It's only when you have slits, like those, then you have this, and then when it interacts with the photo at the end, that's when it determines where the colors come in here. So every time it's measured, there's also a change.
Assessing the already existing. Probably, right? Where it sounds like measurement in the quantum realm really is.
Biggest thing we were trying to do right now.
Assessment of interaction.
Well, this is what the basic, like, the Heisenberg is the initial description of and the initial description of setting up. That's right. Because you mentioned in its velocity, you want application, because then you change its velocity. Personally, I think the electronics is that the interaction. So personally, I think that what we're dealing with these things are quantities that then through the interaction. So that's a further development of the theory that I need more time. Right. Unfortunately, most of my time is spent fundraising these days.
Are you at the role?
So that makes things.
Very good.
We put together these ideas 10 months ago.
Yeah, but not-
I haven't thought about it much since then, so I need to, hopefully someday I'll get a sabbatical.
Yeah, so I was gonna say.
Yeah, it's going to do
That's exactly what I did yesterday. And in fact, I should have mentioned these slides are all, I gave them to Claude and then modified them. Well, and they, but if you look at it, like there were definitely some things that were not, like I corrected a lot of things. And it looks like Claude was using some Notre Dame professor's slides. The colors are all like Notre Dame colors. And like all the insignia, I was like, my executive assistant looked at it, she's like, this looks like Notre Dame slide.
You need a Dominican star or something.
Exactly. Change it to black and white or go back into Claude and say, change it to black and white, right, please. Yes. None of this gold blue stuff. All right, I need to grab some.
Anyway, I asked about that now, actually.
I'm only there for a couple days. I get back on the 26th and I leave probably on the 29th.
Thanks for doing.
I think I might run your host over for. I live in the chapel there.
Oh, very good.
Yeah.
All right, thank you.
Well, I'll wait till the talk starts.
All right.
Okay. You have enough water?
I got enough water. Thank you. Stop. That's my son. That's almost over. I took biotics.
He's gonna bring it.
Actually, that's a bad one.
That's true.
This is where I get
calculations.
But you're gonna bring, he's gonna go earlier to celebrate with the Yeah, I was gonna go, we go together, whatever. Yeah, you can go together. The monstrance is already in the second. It's already. With decoration or? The candles? Yeah, candles, yeah, we do. You can do. Yeah, I'll come over. Sorry, Father, I'm gonna go help Father Matthew set up. He needs it.
Oh.
I'm no intellect's no use here at the Q&A session, so. Let's go stuff.
Yeah.
This is awesome. I love hearing these talks. I'll be back.
All right.
20 minutes.
You still see you.
This particle interacting here does, but the final state particles of that interaction are not.
We don't get this is not a.
Is this chair in use?
I'm sorry?
Is this chair in use?
I don't think so.
Okay, I put this on here.
Sure.
Thank you.
Absolutely.
So you're talking about this particle, so like whatever particles interact.
Yeah.
Describing that interacts are intrinsically non-linear.
because the current is not.
By the way, it's.
Nice to meet you. Great. As they say, blindness, I'm gonna put your voice down. Very nice to meet you.
That's anything to do with the fact that if you think about, and I think very like a great experiment, but recently,
Yes, that's a problem simply, but I think it's running smoothly enough.
uncertain in most measurements is what we call like cross sections.
Yeah, I know.
But what we say is just like cross sections with the nucleus, but there's some component.
Oh, is that right?
But that's talking about cross sections is basically burying a lot of physics in a single number.
Yeah, so using that question.
But so if you want to describe this, no, you'll find the underlying equations. This has got the Schrodinger equation of the Dirac equation.
People typically is, the nucleus is complicated.
Right.
But you're saying that that's part of the complication.
The problem is treating this as a classical system when it's not. And because of that, this fact that this is nonlinear is ignored. And the nonlinearity here is exactly what collapses the wave function, because once you have nonlinearity, you cannot have superposition. And so the equations here are so complicated that this is extremely chaos. So it appears to be random.
Random-ish, but yeah. And then we loop and then we pump it all in. So this is so complicated.
But what's going on here is, I mean, if you just apply elementary physics.
We take a lot of shortcuts
First
to
of all,
get
first year graduate level physics. It's clear that describing this as a linear system and trying to force this into Hilbert space.
Yeah.
Is a mistake.
Yeah. So the problem in general is very strong. And let me ask you this, so what we do, for example, in like software is, all right, so whatever's happening here is a complicated piece that we don't want to deal with, right? So what we do is, let's say in that case, like shoot, then you have, the vector over there, but if you make them functionally identical, as in you fill them with the same stuff and blah, 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 then the claim is that the systematics associated with this part are going to cancel between the measurement that you're making here and the measurement that you're making here. But it really is just in terms of like just interactions, it really is just how flavor on like what flavor flavors from measure here.
Right.
So in that sense, some experiments don't do that. But in that sense, I think that this does in fact, yes, that's all.
Right, but what we're talking about, or why wave function collapses, why you can't have like make that superposition, like the whole matter. Okay, so brains and so stats or that's yeah.
Come with me and
So it's underneath the computer. So just one at the same time. Save it. Just go. Yeah, just join the meeting. If everyone will have a seat, we're about ready to start the next. All right, I'm happy to introduce our next speaker. Our speaker is William Simpson. He's a tenured associate professor at Ohio State University. He's also a research fellow at Blackfriars Hall, Oxford. Honorary Fellow at the Department of Philosophy at Durham University, holds a doctorate in philosophy from Cambridge, and a doctorate in physics from St. Andrews. His current research is focused on the mind-body problem, emergence, and the metaphysics of quantum mechanics. More generally, he's seeking to combine classical thought and contemporary science to provide a general account of the natural world and how humans and animals fit into it, with a focus on the integration of mind and matter. His work advances our understanding of the place of life and agency within the world described by physics. And the title of the talk is Quantum Heliomorphism. So I turn the time over to you.
It's a pleasure to be here at this on quantum science and Catholic theology. Can you hear me at the back if I speak at this level? I need to amplify a bit. Okay, I'll try and do that. So wave if I get a little bit quiet. So the title is Quantum Heliomorphism Beyond the Copenhagen Interpretation. And the Copenhagen interpretation, or at least a certain way of talking about quantum mechanics that bears this title, actually it seems to mean a lot of different things in different contexts, has long been attractive in science and religion circles, because I think it seems to offer a vision of reality in which is more accommodating than the closed world of classical mechanics. First, there's the quantum superposition, in which a system is represented as a combination of alternatives that would be mutually exclusive in classical physics. Second, there's the act of measurement, often treated as a basic postulate in which the wave function of the system collapses to a single determinate outcome. Third, there's the role of the observer, who appears to be involved in this mysterious transition from indeterminacy to definiteness. It's not hard to see why this interpretation has been attractive to certain kinds of thinkers. If classical mechanics was taken to describe a closed world governed by deterministic laws that had no room, no causal role for mind, agency, or divine action, then Copenhagen appeared to reopen the door. In other words, this kind of Copenhagen interpretation has tended to attract dualists who have speculated that mind or spirit enters the story just where the physical world becomes indefinite or the physical story contains gaps. But the attraction of Copenhagen was also a liability. It leaves unclear what kind of thing an observer is, what precisely counts as a measurement, and whether collapse is a physical process, merely an update in our knowledge, or a sign that the theory itself is incomplete. For these reasons, many philosophers have not regarded Copenhagen as a satisfactory interpretation of quantum mechanics. They've preferred realist alternatives that give a clearer account of what exists and how it evolves, such as GRW-type theories, in which the wave function undergoes spontaneous physical collapses, Bohmian mechanics mentioned earlier, in which particles have definite positions and are guided by the wave function, or many worlds theory, in which the wave function never collapses, but all the branches of the quantum state are taken as physically real. These quantum theories are remarkably different, but they share the ambition of describing what the quantum world is like independently of our acts of observation. My concern here is not to adjudicate between different versions of quantum mechanics, but I do want to ask why Catholics in particular might have reason to go beyond the Copenhagen style approach to consider ontological interpretations of GRW-like theories and Bohmian-type theories. To explain that, I need to begin with a basic question. What is the world made of, and how do human beings fit into it? It's a question a young child might raise, but also one of the oldest in philosophy, and it is, I think, one of the most important questions for any serious dialogue between physics and Catholic theology, because Catholic theology is not dualist in the sense inherited from modern philosophy. It does not think of the human being as a ghost inhabiting a machine, or as a disembodied consciousness tacked onto the edge of the physical world. It does not conceive of the body as a disposable instrument of the self, but as something that belongs intrinsically to the person and is destined for resurrection. According to the Catechism, the soul is the form of the body and the human person is an embodied unity. Even the sacramental life of the Church presupposes that macroscopic things such as water, bread, and wine are real and can bear spiritual signification. If divine grace is supposed to perfect nature, as some Catholic thinkers have claimed, then it matters whether there are any things in the world that have natures to be perfected. That is why I want to sketch today a hylomorphic approach to non-relativistic quantum mechanics. My ambitions are much more modest. An approach that takes the physics seriously but does not treat the familiar world of macroscopic bodies as such as organisms and human beings and sacraments as mere convention. So the talk will proceed in 4 steps. First, I want to sketch 3 perennial pictures of nature that adopt different attitudes towards the macroscopic scale, the macroscopic reality. I'll call those the atomistic picture, the cosmic holist picture, and the hylomorphic picture. Second, I shall consider 2 realist alternatives to Copenhagen-style dualism, wave function realism, and what's called the primitive ontology approach to quantum mechanics, and the difficulty each faces in accounting for ordinary macroscopic objects. Third, I shall sketch my own proposal, still work in progress, the hylomorphic primitive ontology approach, in which matter is complemented by a context field that functions as an analog of Aristotelian form. Finally, I shall suggest why this picture is, I think, more congenial to Catholic theology than Copenhagen-style dualism, especially regarding the existence of embodied souls and material sacraments. So I've suggested that Catholic theology takes matter and the body seriously. It's a tradition in which divine grace is mediated through material things that exist on the human scale. By the human scale, I don't mean just things we happen to care about. I mean the macroscopic world in which we live and act, the world of chemical compounds and animal organisms, as well as sacraments, but the world that incidentally is also the domain in which science is practiced. Quantum theory is not confirmed by disembodied minds gazing on wave function, but by stable records produced in laboratories by macroscopic measuring devices, detectors that click, pointer readings, traces on screens, note inscriptions in notebooks, that sort of thing. But there is a recurring temptation in philosophy, physics, and in some forms of theology to think that the human scale is less real than other scales and to treat the objects of ordinary experience as epiphenomenal or subjective constructions. Setting dualism to one side, I think one can distinguish 2 perennial visions of nature in the history of philosophy that require us to locate what is really real at some other scale. The first is what I'm going to call local atomism, the atomistic picture of nature, whose origin lies in the work of Democritus, for whom reality was nothing but atoms and the void. In its modern form, atomism is the claim that fundamental reality is to be found at the microphysical level, at the level of classical particles or fields, for instance, where one distribution of matter determines the next. Human beings, artifacts, and sacraments may be practically important, but when all is said and done, they are merely arrangements, aggregates, or useful patterns in a more basic microphysical stuff. The story of how nature unfolds is a story about the micro-doings of the micro world. The second is the cosmic holist picture. Its ancient formulation can be traced back to Parmenides, for whom reality was ultimately one. In this picture, the cosmic whole is more fundamental than its lesser parts. In a modern setting, cosmic holism is sometimes cashed out in terms of the cosmos being a quantum entangled whole from which local objects may emerge only approximately or perspectively.
This picture resists atomism, but it flips the reduction of macroscopic reality in the opposite direction. The world of local agents, embodied persons, and ordinary objects are just shadow play cast by the cosmic whole. I am the cosmos doing something over here, you are the cosmos doing something over there. There is, however, a third picture, which Father Robert discussed earlier today and has been mentioned several times during the course of the day, a hylomorphic picture, which I want to pursue a bit in this talk. This conception of nature is associated with Aristotle's hylomorphic theory of substances, which he proposed in response to the atomism of Democritus and the cosmic holism of Parmenides. And the theory was developed by Aquinas and has played a significant role in the Catholic tradition. In this picture, reality is not exhausted either by an inventory of the smallest elements, nor by the cosmos considered an abstraction from its lesser parts. The world contains substances with their own natures, causal powers and natural ends, and these substances can come in different shapes and sizes. A living organism is not merely a heap of particles. A human being is not a ghost haunting some part of the physical field. Matter is always matter under some form, and form is the principle by which matter is organized into a substance of a given kind. This hylomorphic picture is congenial to Catholic theology, I suggest, because it permits us to take the reality of macroscopic things seriously, giving them a role to play in how nature unfolds, rather than treating events at the human scale as merely epiphenomenal or perspectival. And my aim today is to suggest one way quantum theory can be brought into conversation with that third picture. Once one moves beyond Copenhagen towards something more like GRW theory or Bohmian mechanics, it becomes important to provide an account of the kind of world that quantum theory describes, independently of any human act of observation or measurement. Is the wave function or quantum state of a system merely a calculational device, or is it physically real in some sense? Is matter located in ordinary space and time or somewhere else? And how do the familiar objects of our world, measuring devices, organisms, human bodies, fit into quantum theory's description of the physical world? Among realist approaches to quantum mechanics, two broad strategies are especially important for my purposes. The first, wave function realism, gives ontological priority to the wave function. The second prioritizes what philosophers of physics have called a primitive ontology of matter. Both have been applied to GRW theory and Bohmian mechanics. Wave function realism, associated with philosophers like David Albert and Alice Ney, treats the quantum state as real and fundamental. On its strongest versions, the wave function psi is conceived as a field with local structure on configuration space, whose distribution at one moment determines or fixes the possibilities for its distribution at the next. The total physical state of the world is then exhausted by psi of t. But this comes with an immediate cost. The wave function of a many-particle system is not defined on ordinary three-dimensional space, but on a high-dimensional configuration space. The fundamental arena of physical reality of this view is therefore not the ordinary space in which tables, chairs, and human beings seem to live. Ordinary local objects, if they exist at all, must in some way be grounded in the wave function field as a whole. And that gives rise to what we might call the macro object problem. If the high-dimensional wave function is the fundamental physical object, how do we recover ordinary macroscopic things as stable three-dimensional objects with causal powers of their own? It's not enough to say that if we look at the wave function in just the right way, we can find something corresponding to ordinary objects, when if we were to look at it in another way, we might see
fairies and unicorns instead. A realist must explain why that way.
Can you speak louder? Can you speak louder, please?
I can try. A realist must explain why that way of carving the state into ordinary objects is physically privileged. If the ordinary world is the world in which experiments are performed and records are produced, then it cannot be merely a matter of perspective or useful fiction, but must contain robustly real objects and records. The primitive ontology approach program associated with philosophers like Vale Allery and Michael Esfeld seeks to avoid this problem by refusing to shift the primary theater of reality to the high-dimensional space of the wave function. It begins instead with matter in ordinary space, or what the physicist John Bell called local beables. The thought is simple. If physics is supposed to describe the world in which experiments are performed, records are written, and bodies move, then the theory should tell us what matter is doing in ordinary three-dimensional space. The wave function of this view is treated either as part of the law governing matter or as representing matter's dispositions or potentialities to evolve in various ways. The matter in any case is real and exists in ordinary space. In the primitive ontology approach to Bohmian mechanics, the matter consists of particles whose trajectories are choreographed by the wave function. In GRW theories, matter is conceived either as a mass density field that spreads and contracts as the wave function spreads and localizes, or as instantaneous flashes corresponding to spontaneous collapse events. The physical state of the world in either case can be represented as psi q, where psi is the wave function or density operator, and q is the spatio-temporal distribution of matter. This approach has an obvious advantage over wave function realism in that it gives us something real in ordinary space, not just an abstract quantum state, but a material ontology. It keeps matter in the world we inhabit. If Catholic theology needs a world of concrete bodies, material signs, and embodied agents, this may be a step in the right direction. Yet the primitive ontology approach to quantum mechanics does not straightforwardly provide us with a world of macro objects with their own natures. In Bohmian mechanics, the motion of each particle is guided by the wave function of the whole system, the whole cosmos, and depends in general on the configuration of all the other particles in the cosmos. Likewise, in GRW theory, the evolution of the matter field is determined in a non-local way by the total quantum state. So the matter is an ordinary space, but its dynamics is evidently holistic. This is one of the reasons why critics worry that the matter posited in the standard primitive ontology approach is merely a decoration of the wave function. One seems to face then an uncomfortable choice. On the one hand, wave function realism risks turning ordinary objects into shadows cast by a locally evolving field in a high-dimensional space. On the other hand, the primitive ontology approach risks treating ordinary objects as impotent patterns in a three-dimensional distribution of matter whose behavior is choreographed by a cosmic state. In both cases, a kind of cosmic holism looms large. The problem is not simply how to locate macro objects, but how to account for their stability, unity, and causal powers. That is the macro object problem, and it is here I suggest that a hylomorphic extension of the primitive ontology approach may become interesting, even attractive. The hylomorphic view holds that positing matter in ordinary space is insufficient to explain the causal powers of macro objects if the matter is conceived as bare matter. On a hylomorphic view, matter in this world is always matter under some form. And that, I think, is the lesson to draw from the difficulty I've just described. The primitive ontology approach is right to resist wave function realism by insisting that the material furniture of the world is real and belongs in ordinary space. But if that material furniture is conceived merely as particles or mass density or flashes, a bare distribution of matter whose effective organization is left entirely to the wave function, then it remains too thin to explain the stable objects of ordinary experience and scientific inquiry. A measuring device is not merely a distribution of bare matter, it's matter organized so as to measure. A living body is not merely matter arranged body-wise, it's matter organized as a living body. Abstract away from the form which delimits the matter and you lose the object. This point, I think, is not foreign to physics. Physicists constantly distinguish different physical regimes, phases of matter, symmetry-broken domains, boundary conditions, and so on. The philosopher of physics, Laura Ritchie, has emphasized in her work on quantum field theory that realistic physics often requires us to attend to such regime relative structure in order to explain the physical phenomena of interest. She criticizes what she calls a pristine approach to scientific realism, which presumes that the formalism and laws of a quantum theory will yield a single context-independent inventory of reality that explains all the phenomena. Ritchie argues this ideal comes under pressure because the phenomena invoked in support of realism are often explained using regime-specific and sometimes unitarily inequivalent representations. The context matters. Consider a familiar example of symmetry breaking. Above a critical temperature, a ferromagnet is in a disordered phase. Below that temperature, it can enter a symmetry-broken phase with a magnetization pointing in one direction and another. Once symmetry breaking occurs, we introduce a new order parameter and we move to a new sector or representation. The same lesson appears in a simpler setting. An atom does not emit radiation in exactly the same way in free space as it does inside a resonant cavity. The boundary conditions, the available electromagnetic modes, and the material structure of the cavity change the atom's behavior. So the microscopic dynamics are not indifferent to the physical context. The pristine ideal is that all of this should ultimately be derivable from one universal quantum state evolving in one fixed representational framework under one universal Hamiltonian. But that is not itself an empirical discovery. It is a substantive metaphysical assumption about how the different regimes in physics must fit together. My proposal is to relax that assumption, taking a leaf from Nancy Cartwright's philosophy of the dappled world. Instead of requiring every regime to be contained within one persisting microscopic description of the cosmos, we might allow the physical context to select the relevant dynamical package under which the quantum state and the primitive ontology evolve. Furthermore, I propose to make that regime structure explicit within the ontology, and in so doing, to give the matter enough structure to account for the stable, causally powerful things of the familiar world. In a recent paper in Foundations of Physics cited on the slide, I suggested thinking of this regime structure as a context field which is defined in ordinary space and time. Very schematically, we can write the state of this dappled world as a triplet of psi, q, and lambda. Here, psi is the quantum state, which carries the information about dispositions or propensities of the material configuration. Q is the material primitive ontology, Bohmian theory, that's particles, and GRW theory, a mass density field. And lambda is the new ingredient, the context field, if you like, a local regime selection variable. Its values encode physically real mesoscopic structure in ordinary space, phases of matter, symmetry broken domains, boundary conditions, amplification regimes, and so forth. Given the full context profile lambda, the theory selects the relevant dynamical package, transition rates, update channels, sector structures, and so forth, depending on which quantum theory we plug into this schema. The relevant dynamical package is a functional of the context profile as a whole, assembled from local lambda-dependent terms. So lambda here is not an arbitrary label, nor is it extra little force pushing matter around. It's a way of representing within the ontology the regime structure that is already used in realistic applications of quantum physics. Lambda encodes the sorts of local mesoscopic structure that physicists already rely upon when they model real quantum systems, but which philosophers tend to overlook, I think, out of a habituated desire to compress reality down to a single scale. Context field plays two central roles that are relevant to a hylomorphic picture of the physical world, as I've recently argued in another paper cited on the slide. First, it supports the individuation of macro objects. It supplies resources for identifying physically privileged macroscopic regions and regimes. Lambda, a detector, for example, is not merely any pattern of matter that we decide to call a detector. It occupies a stable amplification-ready record-producing regime. Second, lambda modulates the dynamics. Matter on this view does not simply evolve according to microphysical laws applying uniformly everywhere, irrespective of context and regardless of boundary conditions. Which dynamics are relevant depends on the local regime, whether this region is a crystal, a cavity, a measuring device, a living cell, etc. The context field records those regime differences and allows them to enter the dynamics of the primitive ontology in a controlled way. In my recent work, I have explored how this schema can be implemented consistently in both GRW and Bohmian type theories by performing what I call a contextual extension of their dynamics. Obviously, I can't go into the technical details here, but you can check out the two papers cited on the bottom of the screen and see how lambda gets to play a modulating role in both of those theories. The Bohmian ones are a bit more developed. I'm still thinking about spontaneous collapse theories. In my current work, the local context, I'm thinking of it as fields modulating the stochastic confidence dynamics, thereby affecting how the interdensity evolves. So the implementations differ, but the governing idea remains the same. Local mesoscopic structure makes a causal difference to the dynamics of matter. This hylomorphic primitive ontology approach to quantum mechanics steers a via media between atomism and cosmic holism by giving us a way to understand the relation between the quantum state and ordinary objects. The wave function on this view need not be reified as a material field, high-dimensional space from which the familiar world must somehow be recovered. And the material ontology neither determines how nature unfolds, nor is it merely an impotent shadow choreographed by the wave function. Rather, the quantum state, the material ontology, and the context field together specify how matter is organized and how it evolves. This is why I describe lambda as a physical analog of Aristotelian form. It's not a ghostly stuff hovering over the primitive ontology and pushing it around. Rather, it's the organizing structure by which matter belongs to stable physical regimes and exhibits determinate causal powers. One might put the point like this. The primitive ontology approach to quantum mechanics says to the wave function realist, let's put matter back into ordinary space and let the quantum state govern its evolution. Then the hylomorphist says, very good, but let matter in ordinary space be always matter under a local form, and let its dynamics be context dependent. That's the basic proposal, and I've included a couple of quotes on the slide concerning its reception by Valia Allery, who champions the primitive ontology approach to quantum mechanics, and Nancy Cartwright, who wrote The Baffled World, which I won't read out now. Let me conclude by returning to the theological motivation with which I began. I've not argued that quantum mechanics proves hylomorphism, nor have I argued that any Catholic doctrines can be derived from the formalism of quantum mechanics. My claim is more modest. If one is looking for a realist interpretation of quantum theory that is congenial to Catholic theology, which can treat macro objects as having natures, then a hylomorphic primitive ontology might be one promising place to start. With regards to the soul, it avoids two familiar mistakes. First, it avoids reducing the familiar world to a mere arrangement of microphysical stuff, whether in ordinary space or in some high-dimensional space. Bodies, organisms, measuring devices, artifacts, sacraments are not treated as mere conventions or as matters of perspective. They are real, stable structures. Second, it avoids treating mind or soul as something to be tacked onto the world at some point where physics allegedly runs out of road. That was the danger I suggested of some Copenhagen-style approaches. They tempt us to think of the soul as something that operates in the gaps, giving the matter of your body a little push whenever it can get away with it, or perhaps even constituting reality in a world that wouldn't be there unless you looked. A hylomorphic approach is something different. Matter is capable of form. It can be organized into scientific instruments, chemical compounds, in a way independent of anyone's personal preferences, perspectives, or observations. And a living body, a measuring device, compound, can make a real causal difference to how nature unfolds. Not by violating the laws of physics, but by helping to determine the physical regime under which those laws operate locally. Of course, the rational soul is not identical to some value of the context field, but the hylomorphic approach makes it easier, I think, to conceive of a world in which the soul as a type of form is not something alien to matter and is able to make a causal difference. This also gives us a helpful starting point, I suggest, for thinking about sacramental action. Though here, one must be very careful. I'm not saying that grace is reducible to a quantum mechanical effect or contained within physical things. Even so, if sacraments are to be instruments of divine grace and not merely symbols or conventions, then they must have some positive reality of their own that can be instrumentalized, some causal powers that make them apt to serve as sacraments. Whilst the hylomorphic primitive ontology approach to quantum mechanics does not account for sacramental grace, I think it does help to resist those pictures of reality in which macroscopic things like water, oil, bread, and wine are simply too thin to bear form, signification, and instrumental causal roles. It gives us, at the level of the philosophy of nature, a picture of matter as already ordered and formable, already capable of entering into higher unities and causal roles. So finally, the lesson I want to draw is not that quantum mechanics gives theology a special loophole for inserting a ghost into the physical machine. It is rather that quantum theory, interpreted hylomorphically, can help us to recover the familiar world as a world of formed matter, where macro objects are real. And that, I suggest, is why quantum hylomorphism is a more promising partner for Catholic theology than Copenhagen-style dualism. It doesn't try to find spirit at the edge of matter. It invites us to see matter itself as already ordered, intelligible, and capable of participation in higher forms of life, meaning, and ultimately grace. Thank you.
Open for questions. Yes.
So, thank you, William. So, I have a question. I find the approach fascinating. I look forward to reading this paper more closely. I'm curious about, like, given the two versions you've been working on, where does non-locality still fit into this, right? So you still have. I
haven't disrupted it.
So in this context, then you would have individuals with a certain context, but there would still be at least the potential for some sort of quantum non-local engagement, whether through the Bohmian version or something else.
Yeah.
Okay.
Basically. If you like, there's still a cosmic form in this picture, which accounts for that non-locality, but there are also those local mesoscopic, macroscopic forms which are modulating the trajectories of the particles if it's Bohmian mechanics, or the way the mass density field is spreading and contracting if it's a GRW or CSL type theory. Yeah, I haven't disrupted non-locality. I haven't got rid of it.
Questions? I had a question about your lambda parameter. Do you view this as a physical field? Can you measure it? Is it part of the formalism? Is it more of a philosophical metaphysics?
It's part of the formalism. I put it in. If you look at the paper on Bohmian mechanics, it's there in the equations of motion. But think of this hylomorphic primitive ontology approach as a schema, which then has different models. So you could have quite a pragmatic coarse-grained model, if you like, in which the context field just contained labels like this measuring device is in an amplification state or a ready state, or quite high-level description, and then you could have a much more detailed context field specifying perhaps even a continuous regime selection variables. So it's the field of classical values or labels, if you like. And I hope that goes some way towards answering.
Okay. Yeah.
I guess
it's the metaphysical then.
Oh, that's it.
Yeah, Javier, go ahead.
No. So I should pursue that question. I think it captures something. So basically, it is part of the physical formalism. So I'm treating these physical regime structures as real. I'm treating symmetry breaking as a real change in the world. And lambda's encoding that, and lambda's modulating the dynamics. Now, there's a metaphysical interpretation. The full-blown metaphysics, the hylomorphic metaphysics, I want to say that lambda is a kind of analog of form. I don't think I want to just identify form with context field. If you take the case of a human person, for instance, the soul, or that a soul endows you with various physical capacities, but that's not all the soul does. In traditional Thomism, we have powers of intellection, powers to conceive, which involve material powers, and the context field doesn't capture any of that. So it's really concerned with modeling physical powers of macro objects and to capture everything that is true about Aristotelian form.
Okay, I think you still have a question, or the answer?
Yeah,
Go
very
ahead.
quickly. So would you aspire to have also a dynamical description for lambda? Because if I understand that you have a Bohmian mechanics expanded with lambda, so Q and psi have a dynamical description, but lambda is put by hand. is it possible to have a dynamic of a lambda dot in the equations?
So I do suggest a dynamics, if you like, for lambda that needs to be filled in. It is specified in the axioms of the contextual program quantum field theory paper, because it has to be a two-way. If a microphysical change in my body could cause my body to die and lose its substantial form, that would be a change in the context field, and that change would then, in turn, act on how that is distributed. So yes, it's two-way, and yes, I do suggest a way in which we can think of the context field as changing. Simple answer, yes, for development.
Maybe one time for one more question. Yes?
This is Ryan Nadolsky. This is just a clarifying question. I know you mentioned earlier that the homomorphic addition is the lambda, the addition of the context field, in addition to the, correct me if I'm wrong, the quantum state and the material ontology.
Yeah, it's an extension of that primitive ontology approach.
But I guess my question is, conceptually, why distinguish between the material ontology and the context field? Because I would think that the material ontology, and maybe this is just a semantic point, would include ontology being like the theory regarding the forms of the objects that are involved in whatever you're measuring or assessing. So why? But it
Well, I'd
sounds
have thought the stronger counter-argument would be that the wave function implicitly encodes those forms. The matter on the primitive ontology approach is really just this bare distribution of primitive physical stuff. The GRW can calculate it directly from the wave function, kind of. From Bohmian mechanics, it's a little bit more complicated. You've got a separate dynamics for the particle configuration as well as to the wave function. But the particles, at least in, say, Detlef Deer's version of Bohmian mechanics, have no intrinsic properties. They get their properties from science position. They get their properties from the wave function.
So when you say
there's not a lot to them. They're very naked.
So when you say material ontology and then you're just saying material ontology and then as in the bare matter, and we're including now
We
the
need
form.
something more than that. There's something missing from those theories, and it's the physical regime spectra.
Okay. Thank you. I appreciate it.
All right, let's thank Dr. Simpson again. All right, the last talk of the session is from our organizer, Vincenzo Tama. I'll give a brief introduction to Vincenzo. Everything is okay? You don't need a cable. You have the share your slides. So Professor Tama is the founding director of the Quantum Science and Technology Hub at the University of Portsmouth in the UK. He did his degree in Bari in Italy, the master's and the PhD, and also at the University of Maryland. So Vincenzo is an expert in quantum optics, quantum physics, foundations, quantum metrology, and obviously passionate about his Catholic faith and how it integrates with all of that. He's most well known for a very surprising effect, which I think he'll talk about today, which is a two-particle quantum effect, that if you have particles arriving at different times with non-overlapping wave packets, you would say, traditionally, you would think that because there's distinguishability, you cannot have interference because there's a distinguishability of those two photons. But the trick is, if you don't measure time, you measure the complementary observable frequency, you can get interference, two-particle interference, which is a critical and interesting effect, which is also useful in quantum technology. So with that, we're happy to have you, Vincenzo. Take it away.
Thank you, Andrew. I think you gave already a better talk than mine, so I guess I just have to add some prayer now. All right, so good. I'm glad to show you a little bit of the work that we do, mostly from us as Paolo. I will focus a lot on quantum physics, and then I will give a little bit of possible insight, open questions that we can work out together from the philosophical theological side.
So this talk is based on the work that we do in our quantum science and technology hub, some direction of research that are based on looking at the interference now between particles, and I will tell you what it's all about, and how we can use that from technology and see what are the opening to philosophical and theological dialogue. So let's just first start with a simple experiment that maybe most of you have known of. Is what we call the Young double slit experiment. So you have light, we are speaking now waves, electromagnetic waves, that goes to a double slit. So there is two fangitures where the light can come across and then to a screen. So this was an experiment done back in 1801 by Thomas Young. And when you have like a spherical electromagnetic wave coming through the double slit, you see now that the subwaves after the two double slit interfere at the screen. And you see in the lab a succession of dark and light spot, right? And the physics of it is quite simple. You think about, you have like a plane wave, and then these two subwaves, now you can do this experiment even in the water and see interference of waves in the water. These waves either constructively or destructively interferes. What do I mean is that either they superpose in phase or out of phase. You know, so basically you have like the case of destructive interfere when they are out of phase. So you see the minimum and the maximum are matching, so really out of phase. When they sum together, they sum and you don't see any signal because they cancel each other, right? And these are the spot that we call black fringes. No light comes there. On the other hand, there are spaces on the screen where the two waves, you see the maximum and minimum are aligned, so they sum coherently, and you see maxima. So that's the simple physics. You can then understand this in classical optics, okay? So if you instead of using waves, you're just using particles, you know, you have from a gun, like, you know, I used to joke about my children, you know, shooting gun to a double slit, just projectile going there. So you don't see anymore this type of interference. You see a concentration of particle here or there, nothing like that. So, and this comes from the fact that is a particle behavior, where the particle either go to one slit or on the other, and you have a concentration associated to the diffraction to the two slits, right? So what does it happen when we have quantum particles, right? So, and this works for any type of quantum particle. It works with photon, electrons, you know, the particle that orbit around the nucleus of atoms, or photons. We learned about light in the talks before. So the photons are what we call quantum light. The most fundamental particle that describe the light. These are without mass. And so what the question is, what happened when we do now, we do an experiment with photons or electrons? So there are two possible ways now to observe. Let's say we have a single photon that goes through a double slit. To observe the two photons, two possible choices. Either we can attain information about which slit the particle comes across. So we have a device that in principle gives us that information. So I'm speaking really about the measurement choice process, right? And measurements in quantum mechanics is really an interaction with the system, okay? So I can interact with my system going through the double slit, either getting information from where the particle goes through, or not getting that information. I have two choices, okay? That depends on me as an observer, rationally to choose between these two. And if I do the measurement, so without getting any information of where the particle goes through, and then what I do is basically I shoot one photon at a time, right? You see these dots. It's one iteration of my experiment every time. And so these photons are hitting a screen, right? And I wait, and I do this over and over and over and over. You can see after a lot of these measurements, now it comes back. The actual interface, you see the concentration now are of the particle. This was done with electrons. So this is, the concentration is here where again you have like a kind of dark and bright fringes again, like we would have with classical part. This is what you would observe in the lab, right? So we have what we say is that like we have interference now of two single photon quantum waves. So the photon behaves as a wave, like we described before the waves, the classical waves in the CPRON. Now, but it's a wave associated to a single particle, a single photon. And these two waves, two quantum waves, superpose and they're associated to two possible indistinguishable single photon path, and we observe the interference, okay? But this is now at the single particle level. So we have a wave behavior now of the photon, okay? Now we have another possible choice, right? So the other possible choice will be, I have a path sensor, let's say here. So I gain the which path information on the system. So this different type of measurement choice that I do. If I do that, then I don't get any more this wave behavior. I come back to a completely particle behavior, no interference. And we have a concentration of photon electron here or there, okay? So that's what we will observe in the lab. So this type of measurement that I choose to do as an observer is a result of rational choice of the observer that decide which type of apparatus to interact with my system. And depending on what I choose, I have completely different behaviors of my single photon system. It's quite remarkable. And this is the same single photons, right? So we have, in the case of no which path sensor, this type of apparatus, I have a wave behavior, I show it to you. If I have a which path sensor, I have a particle behavior. So it seems that the quantum particle state, in essence, is like predisposed to both a particle and a wave behavior. So they are both potentially, we heard a lot about isomorphism, potentiality, actualities. So I think it's interesting to think, I felt it's quite fascinating to think now there is a potential, a predisposition of the physical system now to the actual choice of the observer. So me as a scientist make a choice, a rational choice of what type of measure to do. But the two possible results are a result of a predisposition already inherent within the physical state of the particle before even the measurement choice is made. So this is what we say is the famous emergence of a particle, a wave particle behavior, right? So we have two possible, which I would say, in my opinion, this is not a duality of reality, right? You have a single real objective reality of my single photon, but that reality contains two possible predisposition, two possible behavior that are in a sense waiting to be informed by the rational choice of the observer of which type of apparatus to take about. So this is, of course, I'm just giving hints of possible philosophical insight that it would be lovely, but this is just at the opening. So this is so this phenomenon is a very key phenomenon in quantum mechanics. In the world of Feynman, is a phenomenon which is impossible to explain in any classical ways, and which has in it the quantum, in it the core, actually, of quantum mechanics. Reality contains the only mystery of quantum mechanics. So so this is see how important to understand. So the wave particle duality behavior in quantum mechanics from a philosophical perspective is key to understand quantum mechanics as such. So this is the single. So I guess you understood I'm going to speak about multiple particle. Before I jump to multiple particle, I just tell you, we did just this experiment, showed this experiment with just a particle on a double slit. But of course, you can do the same thing. Now, if you have a photon, again, it can be an electron, anything, but now you can use a beam splitter. A beam splitter is just a device that reflect, let's say it's a balance beam splitter, reflect the photon 50% of the time and transmit it 50% of the time. So after the particle interact with it, you have we have now two possible, in the same way we had before, two possible single photon waves going either to the upper or lower slit, interfere. Now we have two possible single photon wave associated to the photon, either to be reflected or transmitted. Is completely analogous, right? So I can do this with a beam splitter. But so it's a quantum, what we say, a quantum superposition between the two possible situations. But really is the potentiality of having both behavior at the same time. But now, if instead of having just one photon going through a beam splitter, I have two photons, things get even more interesting. So let's think about I have a red photon and a blue photon, right? A red photon that goes in pinch from the top of the beam splitter and the blue from the bottom, right? And what I do now, I'm trying to, I want to observe them at the output, right? And see, you know, the detect them at the output. There are two possibilities for the photon to go to the output, right? Either they are both reflected or they are both transmitted. Both are potentially possible, okay? And really what you have are correlated path, you know? So there is a double reflection and a double transmittal. You see already the correlation and entanglement occurring there. But now again, in analogous to what I was saying before for a single photon, I can also do different measurement choices. Again, as an observer, as a rational observer, in the lab, I can choose two possible ways to look at the system of the two photons after they come out from the beam splitter. And what are the two possible ways? The first one is the observation of the colors of the two single photons. So I look at them at the output and I try to, resolve the color with a single photon spectrometer, with the device. So I have, in that case, two equally probable measurement outcomes, right? You have a red and blue photon, so I have either the red here and the blue here, or the blue here and the red here. And of course, once I do the measurement, if I detect red and blue, so what I know that I have the photon were both reflected. If I detect the blue and red, they were both transmitted, okay? So in that case, so please anyway, stop me if there is anything is not clear, you know, it's spontaneous. So
what about when
oh,
one
right.
is transmitted and one is reflected?
One is reflected. So we can expand to also to that case, but I want to keep things simple. But the same physics apply, as Andrew was saying, in situation where the two photon bunch in one same detector or bunch in the other detector. Also in that case, you can have blue and red or red and blue. But I have not infinite time, so let's stick on this, and then maybe we have all night to speak about all possible cases.
Frequencies are different, right?
The colors are different colors, yeah.
But they are different
frequencies. Yeah, there's frequencies, different frequencies. Yeah. So I have two possibilities for this type of choice measurement. I'm choosing to measure the color. The two photons act as independent particles, either both reflected or independent particle both transmitted. Independent in the sense because when I do make the choice, the outcome of the measurement, that is 50%, 50%, it tells me, it distinguishes the two photons. So they are really separate entities. There is no correlation anymore, the entanglement anymore, yes.
Something wrong with the picture.
What did I do?
The second picture, the same.
Oh, I did the same. Okay, see, look, very good. Thank you. So this will be the transmission. Yes, yeah. Thank you, Paolo. Yes, it's good that I have a friend that helped me to. So this is double refresh and double transmission. Yeah. So this is why I need to prepare more in advance at all. Yes.
Since we chose, you are looking for small changes.
Okay.
Red should have a different frequency.
Yeah, all right. This is experimentalist. Look, it's very very good. All right, thank you. Actually, it's good. We're gonna do like all right, so this was one choice, right? To measure the two different colors, right? I can do another choice, right? Instead of measuring the colors, I measure the time of arrival of the photon. Okay? What happens if I do that? So if I do that, the things becomes interesting. I do the experiment. This is an experiment. Instead of having like either, you know, the two possibility, 50%, 50%. Now, if I look at the coincidence, the one photon here, one photon here, as a function of the relative time, the time the clock tick, then I see interference. You know, as interfere, there is all the behavior before is gone, you know? The choice, so the different choice I make on the same system, it now brings me to interfere. This is the experiment result. So we need to understand that, right? So there are random relative detection time outcomes, but according to a quantum bits probability distribution. It's very interesting. I will not get into detail. Yes.
Different times. Is it because you're transmitting the two particles?
Good question. Yes. So maybe yes.
Different length.
So let me just say a photon. What is a photon? Because I didn't to say what the photon is we say wave packet. So there is in itself is in a superposition within a given coherence time of any possible time to be emitted, right? So at the output, I don't have a fixed time that I can get it. If I resolve time, I have all the possible times within that wave packet. In the sense, the photon has not a delta function in time,
Okay,
right?
it's not delta
Physically, this is in the lab. And so I can have random value between the wave packet, right? But I don't know, it can be anything. Now I'm looking all the possible random time values, but the difference. And then I see the quantum interference. Thank you. So now I have, when I measure time, what happened is that, you know, we spoke about before the Heisenberg uncertainty, but this is already, you can see the classical verb. But the way you can understand is that you have, the better you measure time, the more the detector are blind to the colors, to distinguish the colors, okay? So if by measuring the time now, the detector do not know now anymore which photon is which. So you can have two possibilities, right? So they can be either both reflected or both transmitted. So the measurement does not distinguish. Well, before I have just two cases, two outcomes. Now that quantum interference that I observe comes from the fact that these two possible two photon paths not being distinguished by the detector, because I'm looking at the complementary value, conjugate value, as in the lecture of Andrew before. Yes, please.
These are single photons or?
No, these are two single photons. I'm doing we do very simple things. So I have a simple mind. I need to do step by step. Yes. So we have two single photons that interfere.
Repeat the experiment many times.
Quantum mechanics, you need to repeat. There is no, it's a probabilistic theory. So the only way we can infer information is that doing the experiment over and over and over. And as I said before, this is the result of the experiment. Yeah, so the result were after a lot of time, these are dots, you get this quantum interference. The same way we did the double slit before. But here the physics is different. No? By measuring time, I'm erasing information about the path, and therefore I observe interference, okay? So I have, so you really have now a two photon hole behavior. So the two photons behave like a single entangled whole entity. While before, and again, we are the same two photons after the beam splitter. I'd made two different choices, and now I have instead a behavior where they behave as an entangled whole, as two quantum waves, but these are two photon quantum waves. So this cannot be done, cannot be understood classical anymore, like the Young double slit. You have a wave, a whole, of two photon entangled, they behave as a wave, and that these two waves associated to the two paths interfere. This is the way. This is the picture to give you an idea. You have two quantum waves, two photon quantum waves that interfere and give a kind of interference that resembles the Young double slit, but is fully quantum because it's at the two photon level. These two photons behave as entangled. So just to wrap up what I said so far. So you have a deterministic evolution. As we said before, the only, in quantum mechanics, the probabilistic part comes only from the measurement, okay? So the evolution through the beam splitter is deterministic. Then I, as an rational observer, I make a choice of a type of measurement, right? I have two possibilities here. Either I detect the color, or I detect the time. This is a rational choice of myself, of the observer. This is a choice, doesn't mean that I am the macroscopic setup that interact with the two systems. It's just my rational free will choice to do the possible. And depending on which choice I do, I have either the same two photon after the beam splitter either behave as independent particle that are distinct between each other, or behave as a two photon hole where there is entanglement. So it's quite fascinating because you're speaking about the same system, right? So I'll just give some initial insight, and hopefully, would be lovely to work together some of the philosophy insight on this. So it seems to me that the physical state of the two quantum particle can be predisposed to two potentially possible behavior, right? So we have a classical behavior. So these are predisposed, they depend on the choice. This then can be actualized by the rational choice of the observer, right? But there is a predisposition either to a classical behavior where the particles are distinguished, or a fully quantum behavior where they behave as a two-particle entangled wall, and where the two photons are correlated and they behave as a wave. So such potential behavior actualized in a mutually exclusive way. These are completely different behavior, as I showed to you, by the type of observation choice of a free rational observer. So myself as a free rational observer can actualize any of these predispositions in the sense that of the choice of which apparatus I use to actualize any of this behavior. And the two possible outcomes for each choice-dependent interaction measurement are described then by quantum probability distribution that are completely different. I saw before we have just 50% just double reflection, double transmission, or a quantum waves behavior. So this is what it comes from here. So in a sense, what we can think about, importing, the insights from Aquinas, where we have, what happened is that you have now a different manifestation of second-order causation, right? So God is the first cause, right? But he acts also through secondary causes. But it's interesting that now this type of experiment seems to me to shed light to this order of secondary causation. What do I mean with that? We have a secondary causation associated with the objective quantum nature of the particle. So the state of the particle after the beam splitter is objective real, right? And has a real disposition now to different measurement choices on the side of the rational observer. Then we have the observer too, ourselves, whoever is doing the experiment, act as a free secondary cause now that is a rational cause, who chooses particular manifestation of nature, in this case, the two-particle system, from the possibility it was predisposed, right? So predisposed, of course, by God as the first cause, but through the laws of quantum mechanics that we act secondarily. And then you have, of course, the secondary, once the choice is measurement, there is an apparatus that you use to implement that choice. And this apparatus is dependent on, is the chosen apparatus from the experimentalist, and interact with the system, and therefore act also as a secondary cause that gives me the probability from which then I get all the different probability distribution. So of course, the open question is, what do the observed outcome probability distribution associated with each particular measurement choice tell us about the ontology and epistemology of the objective reality associated to the system that is manifested, of course, through this order of causality that is established by God as the first cause. So these are open, open question, open areas of research. So this is the fundamental physics of two-photon interference. And so this, I think this some of the philosophical insight that it would be that I thought it would be very interesting to develop. But then the further question is, okay, I have a choice. So the system is predisposed to two possible choices within its objective reality, okay? Can we exploit this quantum, calling quotation mark, this quantum disposition, this potentiality to be actualized by our possible human choice through our rational measurement choice? And the answer is yes, and that's what we do. This is what is all about quantum technology. So we choose the best measurement that enable us to retrieve from the same objective physical system the maximum quantum information for that given quantum system. So what we say, we could say that is quantum technology emerged from human rational secondary causation. So it's all about quantum. It's a fascinating thing because quantum mechanics is not just about the objective physical state that is there. It's objective, it's not ideal, it's a real thing, but it's also about the choice, the disposition of the system to possible choices of the rational observer that act as a rational secondary causation. And that's how quantum computers comes across, how we can develop device that have an exponential speed up, quantum simulators that can simulate complex systems in nature using quantum mechanics, quantum communication that is secure. We even think about quantum internet. And also we work a lot on quantum. So I don't have the whole time of my life to show you everything we do, but we'll focus on quantum sensor, just to give you an example, because it's very related to the quantum interference. What is sensor? Is that you want to use a device, you used to use this quantum interference effect to achieve the best precision possible in nature to measure given parameters. And this is what we did. So this is a sensor of colors. You come back to the same experiment, right? So before I show you the fundamental physics, I show you that you can have, a red and a blue photon. And if I measure in time, I have a quantum interference. So that's my choice, right? If I choose to measure the color, this would not work. But if I choose to measure the time, what happened, as I said before, we have quantum interference between the two possible two-photon path, double reflection, double transmission, because the detector erases the distinguishability in the color. But fun enough, when you do this over and over and over again, actually, this type of measurement is the best measurement to actually measure the colors. So at each given single run, the detector, the type of measure that I do that is time resolved, erase any distinguishability in the color, and that's how quantum interference comes across. But when you do this over and over and over, you remember these quantum bits that I got, the period of this bit actually depends on the difference in the color. So it acts as a quantum sensor. Not only that, it's the best way I can measure the difference in the color in quantum mechanics. Similarly, I can measure time. I do the same thing. Now I have two photons at different time coming in the beam splitter. I mean, you can guess. What do I do now to make them interfere? I measure the conical value. Now I measure the color. Before I had different color and I measure in time. Now I have different time and I measure the colors. When I measure the colors, or the photon, since you asked, Andrew, they can either come in the same detector or in, we call bunching, or what I showed to you so far, just for simplicity, when they come in separate detector. But of course, if you take into account of everything, you get more information. When you measure the color, you don't know which photon is which because you erase the distinguishability in time, but nonetheless, when you do this over and over and over, this system is the best to measure the relative time. I will not, I'm giving you insight, but this is of course important in synchronization of clock. This was the paper with my two students, also the paper before. I need to give credits all to the young people. We are here all for the young people anyway, because we want to make them strive also in this interdisciplinary dialogue. So this was a bachelor student, a PhD student with me. This is, and you can see, you can use this in imaging, nanoengineering, synchronization of clock. And this is not just theory. We did in the lab, this is a collaboration with the Alessandro Fredizzi about University. This is the paper that in the lab, we can go even further. So we can just measure position. Same thing, right? So you have now two photons in a different position. What's the conjugate variable of the position? We call it the transverse momentum. And so you go at the output, now you resolve the transverse momentum, it's a conjugate value, it's the same physics, and we show that this is the best sensor to localize an object based on the measurement choice, rational measurement choice of the observer, that maximize the quantum information out of the system relative to the parameter that is the position. So this was done in the lab too. It was in a collaboration with Jingyi Fan in Southern University of Science and Technology in China. You can use this for localization of emitter, neuron, molecules, astrophysical objects. So this is, you see also how we spoke about quantum science, philosophy, and theology intersection, but the technological parts comes very, very much in. And finally, we did this, we can do 3D quantum imaging. So here we can really resolve in 3D a given object by using this type of quantum interference. And just to conclude, so I give you the first take-home message of open insight on philosophy I'm looking forward to discuss with everyone on the fundamental physics. Here is about how we use that in quantum technology. So it looks to me that God enables us to responsibly take advantage of this quantum disposition of nature. So what I mean the quantum disposition is the potentiality with respect to the possible rational observational choices. And this is nothing else than quantum technology. So quantum technology that we try to build for the benefit of our society are developed through ad hoc choices of measurement. But measurement envisioned by a human agent, our human intelligence. So as we are used in a sense by God, and within our own freedom, as rational secondary causes that allow to interact with nature to build up technologies. And we can do so through our human intelligence and implement that through our own human will, which are the two main faculty of the soul. Anyway, thank you for your attention. But let me thank also the many collaborators.
Okay, thank you, Vincenzo. And we have time for a question or two. Why don't we start with Ibrahim?
Yeah, so thank you, Vincenzo. Thank you very much. When it comes to the or multi-particle interference effect, so statistics is playing role significantly.
Yes.
So I can go with the same experiment that you propose, and I will destroy the interference actually, and I will get the two photons to will exit from different port always. So you know that.
Yeah.
So this is what we call the fermionic statistic.
Yeah.
This is not the same as the Young double slit. Young double slit, you can repeat the experiment with the photon, the electrons, neutrons, atoms. It will give you exactly the same situation, which is coming from the entangling the double slit with the photons or with the particle that you have it. But this is not the case for the case of biphoton. The case of biphoton is statistically independent. If you create a fermionic state, it will be a different statistic. If you go with the bosonic state, it will be a different statistic.
It's a statistic dependent. Yes.
That is a little bit, delicate to be handled with the questions that you added there.
Yes, well, I mean, in a sense, the secondary causation of nature depends upon the intrinsic. We learned from Father Ambrose before, there are intrinsic properties that depends also the statistics and the symmetries. And
don't get confused. Well, I'm not saying to repeat that with electrons. It's a different situation.
Yes,
I'll get you the photonic state, which is acting as a fermions, and then you will get completely different situation.
Yes. So there would be a different predisposition of that particular system. But my point here is that given the given system, and this is a fixed system, I just give an example. Of course, you can do with any system, and the predisposition to measurement, for example, the system is not different there. But here I'm fixing the particular physical system after the bin splitter, and afterwards I have these two possible predispositions. Yes.
It's important to stress something very important. The photons that are coming in are independent photons. They are not entangled photons. And when they go into the beam splitter, they don't interact with the beam splitter either.
No.
The only time that there's any kind of influence is the fact that when you detect them, you can't distinguish them.
Yes, that's right.
That's the critical physical effect.
Well, I mean, after the beam splitter, the photon, if you look at the actual photon state, two photon state, it is entangled.
Yes.
But of course, that doesn't mean anything until you know, it's a measurement.
Until you measure it.
Yeah, but one can see the physical state after the beam is
We're getting excited. All right, another question?
Well, I could go for a few, but.
Yes, let's go with you.
Very nice talk. Thank you. I just wanted to make sure that I understood your framing of the like rational observer.
Oh, good, yeah.
Because if you go back to the choice of
Yeah.
what you measure.
Yes.
If you change the rational observer for say like a quantum, I don't know, random generator, does that change the results?
Of course,
Does
if instead of being a human observer that by the power of his will decide either one measure or the other, I just use a machine that basically randomly pick up either one choice of measurement or the other, then the whole thing will be messed up because you will have you cannot pinpoint anymore one behavior with respect of to the other, because one time the machine is going to choose to resolve in time, another time with the frequency. So you will have a statistical mixture between the two behavior, and therefore all the properties.
Statistical mixture, if you say had to pick each time, but let's say the random choice is about picking the next, some number of statistical significant measurements. The behavior of the photons is not going to change because it was a conscious agent who made the decision.
Yes, and that's why I don't have anymore the particularity of that behavior, because it's
I just
another
wanted
mix.
to make sure, because otherwise, yeah.
No, that's true. Yes, if I make a random choice that a machine can do, this is gone. So that's why you need a rational choice of choosing one or the other.
Yes.
Why can't you have an automated laboratory where the machine says, I'm going to measure a certain thing and I'm going to use this method of measuring the thing?
I will be the one to tell the machine. So what I'm trying to say, we need if we want to envision a quantum technologies, okay, there needs to be we need to envision what's the best way to measure. Then the implementation is done with a classical machine. So there is no, reason in the machine that the detector does not need is not a rational observer, right? It's just what I'm trying to say is the technology that comes from our type of choice. So as experimentalists, we need to envision what is the best way.
I guess what I'm saying is, I don't see how quantum mechanics. Yes, if you're going to have some sort of organized activity which has some purpose and goal.
Yes.
You talk about some rational actor there. There's nothing to do with quantum mechanics. It could have
it's
be any kind of whether I'm going to start a business or something, I can have a rational actor making decisions of how to achieve some goal in some intelligent way. I think somehow I don't see what quantum mechanics has any kind of rational activity.
So you need to make a choice of measurements. So that's the only thing I'm emphasizing. There are different aspects. There is the objective reality of the system. There is a human being that make a choice of the type of measurements to do. And then there is an apparatus that is a classical apparatus that is used to implement that measurement. So these are different order of causation.
Yeah, I think his point is that depending on what you choose to do, the kind of physical behavior is very different. That's your point.
That's my point.
All right, Luis, you have a question?
Yes, so if you change the resolution of your measurement, you are in some way lessing vector backing information, right?
Yes.
So you can, with changing the vector B, you can go from one limit to
that's another decision that I can make, resolve the full information in time or integrating over that. And the less the precision I have in time, the more I don't see anything.
So you are losing information.
So they are losing information. But the information is there in the system. It's a matter for me to be able to come out, to retrieve it with the best choice of measurement. I cannot just put a random apparatus there that does the job for me.
Okay, let me transition real quick into my role as organizer. Well, we have, in principle, if you'd like to participate in Eucharistic adoration, that's going to be happening. We've pushed it back to around 5:30 in the chapel we were at this morning. If you want to attend, you're welcome to. And with that announcement, let's just thank Vincenzo again and all the speakers of today. Very nice. Yeah, and then we will resume tomorrow at 8 a.m. again with mass, followed by the first talk at 9:30. So see you then.
How do you move from making the choice to acting? Like, what happens after you make the choice?
What's the
What is keeping you up right speed? Are you diverting photons, or are you the same machine that you're hitting a switch on?
They're not mentioned. That's what I need. Just for the phone.
So you're
just type of that text.
Right, but what I'm saying is the choice involves. Yeah.
It's on campus.
There's a big roundabout, and that's called the Orange Circle, and I think it'd be the restaurant. It would be about a 15-minute walk.
So you're not.
Yeah, so you might want to drive.
After. What are the photons playing after those zones?
But the just, but that's the thing, I think the choice is not made.
And so if I could drive over to church now, would that be better? Leave here, drive over to.
Are you gonna go to adoration for a bit? I would, yeah, that's on the way, so I would drive. This is the campus, come to the adoration.
I'm just curious about.
If you guys are all the same route.
Drive over there and then drive first there and then drive.
Yeah. But again, it is here. Yeah, let's do it. You wanna go adoration at all? Yeah. Okay.
So maybe.